Yeah, I mean, so the whole USB thing, I'm just using my laptop, but your stuff's on there too. I think we should start. Here we go. All right, hey everyone, we're going to get started. All right. Can you all hear me okay? Yeah? All right, hey everyone. I'm Amit Talwalkar. I'm the general chair for SysML 19, and this is the other organizers for this year. So what we wanted to do in this first talk is first welcome everybody here, tell you a little bit about what we've been up to for the last year and kind of what to expect for the next few days. So I think we all agree that we're here because we're excited at research at the intersection of systems and machine learning. There's been a growing community around SysML for the last several years. That's both the case in terms of overlapping topics at leading conferences on machine learning and systems, as well as workshops at these various conferences. So that led us last year to start SysML Conference. It was, I think pretty well received. We had over 200 submissions. We lightly reviewed them. They were non-archival. The community seemed to be really excited about participating in the conference. We had nearly 300 people attend from 78 organizations. Registration sold out really quickly. It was organized by the organizing committee, many of the folks that I listed on the previous slide, as well as with a lot of help from Stanford Conferences, who was again helping us this year. But so sort of motivated by our experiences last year, there were some changes we wanted to make this year. And so what I'd like to talk about for the next few minutes is kind of what we've been working on to implement these changes this year. So first, in terms of the program, we wanted to move towards a formal review process with archival proceedings for accepted papers, and to encourage that we had high quality papers and that we were able to communicate between this interdisciplinary machine learning and systems community. We also had an in-person PC review meeting back in December. In terms of community, we decided to write a white paper collectively among various folks in the community to describe SysML the conference and more broadly the field of SysML. We also wanted to increase participation in the sense that registration sold out so quickly last year. We wanted to make sure we could have more people come this time around. And finally, while doing that, we still wanted to continue to target researchers, as SysML is fundamentally a research conference. And then finally, in terms of organization, we wanted to formalize the structure of SysML to set it up for future success. That both meant thinking more about the internal organization of SysML, as well as potentially finding a partner organization to help us run and organize the conference moving forward. So Matej, one of the program chairs, is going to be talking more about the program right after me, so I'll leave the details of the program to him, but I want to say a little bit more about the community and organization efforts. So first, as I mentioned, we worked on this white paper. I'm happy to say that we just released it, I think 2 days ago. It's on the website. Still has not been accepted to archive. There's like 50 plus authors. That might have confused the folks on archive, I'm not sure. But yeah, it's a white paper. It's a short paper describing the field and the conference and authored by the majority of folks on the steering, organizing, and last year and this year's program committees. So I encourage you to check it out. In terms of participation, there's 515 and I think a few more people signed up walk-in. 500 people registered for the conference. That's nearly double last year. From 140 organizations, again, that's nearly double from last year. And I think it's really cool that 23% of the attendees are international. Again, that's way up from last year, and it's just kind of nice to see such diversity geographically. In terms of academia versus industry, we unsurprisingly have a strong industry presence. And given the amazing research being done in industry, especially in an area like SysML, again, this is kind of what you'd expect. I do think that the majority of the folks here really would self-identify as being part of the research community, though, and that was kind of one of the core focuses when organizing the conference. In terms of organization, there was two big things that we made progress on this year. The first was formalizing our organizational structure and bylaws. And the underlying idea here is that we just as an organization need to know how we make decisions. What is the process for picking new venues, picking new chairs? What are the roles of each of the chairs each year? So we all know what we're expected to do and not expected to do. And so working closely with the rest of the organizing committee and the steering committee, we converge on a set of bylaws, which again I think will help us make decisions more smoothly moving forward. And the second big piece related to organization, which I'm really excited about, is that we decided to partner with the NERBS Foundation moving forward. So for those of you who don't know, the NERBS Foundation, they run and manage NERBS and ICML, which are two of the oldest and most prominent machine learning conferences. They also organize iClear, which is a newer conference, maybe 7-ish years old, but it's also a top-tier machine learning conference. And starting next year, they'll be helping us run SysML. And this is really exciting for us in the sense that they have a huge amount of experience running conferences. Myself having attended all these other conferences, they're well-oiled machines. They're really, they allow the organizers to focus, more on the technical content, and they do a better job than we could possibly hope to do organizing, kind of the logistical aspects of things. So we're really, really excited to be working with them moving forward. So with that, before I turn it over to Matej, I'd like to just thank, there's a lot of people to thank to put on this conference, and kind of it starts with everyone here in this audience, right? So the point of this conference is to bring this community together, so the fact that you guys are all here is really, really exciting. Showing up, submitting papers, publicizing the event, so it's great that we're all here in the same room. Next, I want to thank the steering and the program committees, so the steering committee for providing high-level guidance, helping publicize the conference. The program committee, they worked really hard to, for the review process, including many folks flying out to Montreal in December for this in-person PC meeting. So we're really appreciative of all their hard work. Next, at Stanford conferences, Bridget Neff has really helped a bunch with local arrangements. As I mentioned, the NERBS Foundation, they're not technically working with us until next year, but they've been incredibly generous with their time so far. And so I want to thank Mary Ellen and Lee, who are sitting in the back left over there, as well as David Kirkpatrick, who is a legal advisor of ours. And next, the Artifact Evaluation Committee. So from the start, and again, Matej is going to talk more about this, but from the start, reproducibility has been really an important component of SysML. And the Artifact Evaluation Committee sort of did the work to execute on that vision. And again, Matej will talk more about it, but thank you guys for your hard work. All right, so a few more thanks. So the organizing committee, right, these are folks that I mentioned in my first slide, right? There's been a lot of work, lots of moving parts to put this conference together. This year, we took on a lot more than we did last year, right? And the conference wouldn't have happened without the hard work of all these people. So that's, Demetrius is our publication chair, Sid was our website chair, Alex and Vivian were our publicity chairs, Theo and Say were our demo chairs, Grigory and Gennady were our artifact evaluation chairs, Sarah was sponsorship chair, and Alex and Chris as our white paper chairs. So there's a few people on the organizing committee that I think deserve special thanks for their hard work, and that's our program chairs, Virginia Smith and Matej Zaharia, as well as our local chair, Erica Strandberg. So these three worked incredibly hard to put this conference together, and from the program chairs, from Virginia and Matej's point of view, in addition to working really hard, they had to be really thoughtful about how to put this program together such that it was interesting and appropriate for a pretty diverse and interdisciplinary community. And not only did they have to organize the main conference, they also had to organize this in-person PC meeting, which for half of the people coming from the ML community, they had pretty much no experience with this, and there was a lot of learning and organization involved there, and they did an absolutely amazing job. In terms of Erica, right, organizing a conference of, executing on a conference of 500 plus people is incredibly hard, and not only did she do it a really, really good job at it, she just, she always had a smile on her face. It was very pleasant to work with her, and she just, she just absolutely hit it out of the park. So I think we should thank all three of them for just an incredible effort. All right, and last, we're incredibly grateful for our sponsors for this year. Right, we have, it won't be possible to be where we are, to sort of put on the event that is being put on for these next few days, including the banquet last night, without really, really generous support from our sponsors. Many of these sponsors have booths and booths outside, and for the next few days, I'd encourage you to talk with them, check out what they're doing in the SysML space, and just to thank them for their generosity. Great, so with that, I will turn it over to Mate.
All right. So I'm Mate Zaharia. I'm just going to give a little bit of background on how we put together the program that you're going to see at this conference. And I was one of the co-PC chairs together with Virginia Smith. So she couldn't be here for this talk, but it's very much, it's a joint effort with both of us to get this together. So let's start by talking about the papers themselves that people will be speaking about and the review process. We had 189 submissions to SysML this year, and we put together 60 program committee members, about half of them from systems and half from machine learning. And we really looked for PC members who would be, reviewers at sort of the top conferences in either field to make sure that we have a really great program. We also did something special in that we tried to have at least one systems and one machine learning reviewer per paper. So whatever your paper is about, someone in each of these fields has to find it, somewhat interesting. And we wanted to make sure that we don't get stuff that's, just systems but is irrelevant to ML or the other way around. And so that led to a lot of interesting conversation. A lot of these folks, of course, had not reviewed any papers together in the past. We had an author response period for people to get information back, and then we had this in-person PC meeting to discuss the top approximately 60 papers. And this was also pretty cool because, again, a lot of the reviewers, especially from the different fields, might not have met each other, and it's also just kind of a good networking event for them to get to know each other and also see what they think about, sort of more or less the whole program, the parts that they're not conflicted with. And then in the end, we ended up accepting 32 of the papers, which is about 16.9%. So hopefully, these are really great papers and everyone will enjoy the presentations. In addition to papers, we wanted to give a lighter weight way to participate, so we put together demos. So Theo and Sir Zhang ran this process with demos. We had 34 demo submissions, and we accepted 15 of them. And the demos will be this evening during the same session as the poster session and the reception. So you'll be able to see these nice interactive demos in the evening, and we're excited about those. And as Amit said, we were also really concerned about promoting reproducibility in these fields, and so we wanted to put in an artifact evaluation process from sort of this first full-size SysML conference. So the problem basically is it's often difficult to reproduce results in both systems and machine learning research. And in response to that, there's been this trend to add artifact evaluation in a lot of top conferences. So PLDI, PPOP, CGO, supercomputing, these are all conferences that have adopted this. And the ACM has this process where you can do artifact evaluation and you can get these badges on the paper. So there's artifact available, which is just did you share the code and the data and so on for the paper in a way that people can easily get to. Then there's evaluated, which is, can someone else run it? Does it sort of do what you said it will do? And then the final tier is this replicated level. We didn't evaluate things to this level this year, but it's also something that you can do, and we might do it in future versions of the conference. We had two great artifact evaluation chairs, Gennady Pahimen and Grigory Fursen. They ran this process this year. They put together, a small committee of people to do this, and 5 of our papers participated in this after they were accepted, so they all got these badges, and you can see them online. And we'd love to get more feedback about artifact evaluation, so Gennady and Grigory are organizing this little mini session during lunch tomorrow, and we encourage you to show up if you have questions or input into how to make this easier for people. Finally, we have two really great keynotes. We have Ofer Dekel from Microsoft Research, who will talk about compiling AI for the edge, and Maya Gupta from Google AI, who will talk about making AI fair. And these are right after lunch both days, so we're really excited to have them here. So other than that, you can find the conference schedule online. Basically, today we have, talks all the way to 6 p.m., and then we have the demo previews and the posters and reception. So basically, it's a packed day of SysML. And then tomorrow, sessions go from 9 to 6, and we'll have some closing remarks, and we also have the artifact evaluation meeting during part of lunch. Okay, so just to thank everyone involved in the program again, keynote speakers, AE chairs, the program committee who did a ton of reviewing and a ton of discussion, and the artifact evaluation committee. And then most importantly, we should also thank Amit, the general chair. He was also general chair last year, and it's a huge amount of work to put together this kind of conference, and it wouldn't have happened without him. So thanks.
I'm a researcher from Microsoft Research New York City, and I have the honor of kicking the program off with while I do that, so the first session is on parallel and distributed learning, and the format are going to be 22-minute talks. We have 18 minutes, okay, and after that we're going to have 3 or 4 minutes of questions. And so what I've asked our AV staff to do is put mics along the aisles. So after the talk, if you have questions, please line up behind the mics. This is something we often do in systems conferences. I don't know if we do it in ML conferences too, but this will make it really easy for you to convey your question to the speaker, and also it'll be picked up by our live stream. In particular, if you do not use the mic, then no one will hear your question in the live stream. Okay, so our first speaker, without further ado, is, let me stand here, sorry, is Hadi Hashemi. And he is a 5th-year PhD candidate at UIUC, working on optimizing distributed machine learning systems. He's also currently on the industrial job market. And he's going to tell us about a system called TIC-TAC for accelerating distributed DNN training by intelligently scheduling your parameters updates.
Hello, everyone. Happy April 1st. I promise you nothing here is April's Fool. I'm so honored to be here. Since I'm talking in SysML, I ignore all of the background about why machine learning or deep learning is important and why we have so many frameworks, machine learning frameworks in the recent years. Instead, I'll focus about what's common characteristics of all of these systems. So all of these modern machine learning systems are designed for iterative workload, where you define one step and you do it over and over and over again to optimize a certain set of parameters. And also because of the popularity of deep learning, the design principle in developing these frameworks is we are dealing with the compute-intensive workloads, and using some kind of accelerator, SIMD accelerator, is a first-class citizen in these systems. And lastly, these systems are designed for rapid experimentation. As a result, the default representation of the workload in this system is a DAG, where nodes are a predefined ops, hiding the difficulty of coding for GPU or TPU or whatever you may have, and make them portable. And also, there is much emphasis on how would you speed up this process so a researcher get to the next round of refining their model or their result. So it has been long gone the time that deep learning could be a state-of-the-art deep learning model could be trained on a single machine has been gone, and distributed training is a normal in any AI pipeline. There are many paradigms you can do the distribution. One, for example, in the data parallel, each worker will have a copy of the model, and the input data, whatever it is, will be divided between all of these workers. And these workers in each iteration tries to synchronize their changes to the parameters and go to the next iteration. So $1 million or $1 billion question is why distribution does not scale. And there has been a lot of works on why this happens. To explain it simply and in an abstract fashion, I'm going to explain it through the DAG structure. So in a simplified baseline deep learning model, we have the forward pass, which reads each parameters individually, and in the backward pass, we update these parameters. And the order of reading and writing is almost reverse. In this picture, I recorded 2 iterations from training ResNet on TensorFlow. The x-axis shows the time, and each of these arrows shows the time when a parameter is being updated in backward pass, and end of the arrow shows when the parameter is being read in the next iteration. As long as machine learning system can synchronize these parameters before the end of the array, we wouldn't have any slowdown on the distributed execution compared to a single machine execution. But if this doesn't happen, we have a slowdown which could potentially limit our scale-out performance. There are generally 2 reasons why we may miss the deadline. The first one is easy. If your network is not fast enough, you cannot deliver the data in a timely fashion. The second reason, which is usually overlooked in the literature, is the order of transfers. You may have a fast enough network, but if you deliver this transfer in the wrong order, you are missing a lot of deadlines, even though you could do better. And since all of these orders are reversed, you get the parameter updates in the reverse order of using them, it's easy to actually miss these deadlines. So let me give you an example. In this simple DAG, each blue rectangle represents a computation all up, and the red circles represent a network transfer. So this being a DAG, we can execute it in any topological sort. In one sort, we can start with A, finish the A, and do the B later, and we get the best performance. Or we could start from B, and at the end of the B, we don't have anything to compute, so the computation will be blocked until we finish A. And this computational blockage is really easily observable on the trace of distributed training. So this is an example of training in Inception v3 on TensorFlow with 4 workers and 1 parameter server. And as you can see, we have 2 different types of computation blockage in this timeline. So we either have a bad order of transfer, which blocks us at the beginning of the training, or we are fast enough, or we were lucky enough, but we had to wait for someone else with a bad training at the end. So to fully study this effect and show how different approaches target this problem, we propose this performance model of computation utilization. Deep learning being a compute-intensive workload, we want to use as much computation as we can to speed up things. In this model, we have 2 components. The first component is communication to computation ratio. In one iteration, you have to do a certain transfer and you have to do a certain computation, and the ratio of this tells you like how well you can do. If you have a lot of communication, you will underutilizing your GPU anyway. And the second component, we call it overlap coefficient. Overlap coefficient shows how well you overlap everything. 0 means that you didn't overlap anything, and you technically sequentially do computation. And 1 means you had a perfect overlap. And clearly, we want to be on the top left of this picture anyway. In the example I showed you, we are roughly here. So we didn't have we had a chance to fully utilize the GPU because we had more computation to do, but because of the blockage, we didn't have the overlap. And the goal of Tic-Tac, the system I'm proposing in this paper, is to move this point to the higher level, to the better overlap. For the comparison, most of the optimizing distributed works focus on network to computation ratio. They either do it by increasing the computational time, mostly by increasing the batch size per worker, or decreasing the communication time by decreasing the number of transfer needed in each step, size of the transfers to extreme of 1 bit, or do a system optimization to make everything faster on the transfer size. There are a few works on the overlapping. Most of this work focus on the cases where best order is trivial, and surprisingly, some of this work get away with applying the worst order possible and still beating the baseline. So in our solution, we make some additional component to the current systems. So in a typical system, we have a base model. We convert this base model to a distributed model, and we send this model to execution engine. In a Tic-Tac, we add 2 more components. We have a component that takes the base model and find the best order of transfers. The best order is represented as a priority list. We give this priority list to an enforcement module, which works with execution engine to enforce this transfer. And we take advantage of iterative nature of this system, so we find the best order offline before the execution started, and we use this priority over and over in this step online. And yeah. So how to find the best order? Finding the best order essentially is a scheduling problem when you have multiple resources on a worker, and this resource is supposed to run a set of operations which have a DAG-like dependencies, and each operation can be executed only on the certain class of resources. And our goal is to find the minimum make span through the better network transfer priority assignment. This problem specifically is known to be open problem. The simpler version of this problem has been proven to be NP hard, has been shown to be NP hard, and as to the best of our knowledge, there is no approximation with guaranteed boundaries to solve this problem. So we cannot find the optimal one, so we try to approximate one. We took 2 approaches. In the first approach, we start relaxing the constraint to the degree that it becomes solvable in polynomial time. And to do so, we assume that all of the computation ops takes 0 seconds, essentially removing them from the DAG. And we assume that all of the network transfer only takes a unit time. And by doing this, we could find the best order in this relaxed problem by doing a simple critical path analysis. And in the second approach, we didn't relax anything. We use a simple dynamic list scheduling algorithm. It's dynamic, still on the offline board. And we use a heuristic to find the best one. Go to the paper to see the details. To our surprise, both of these methods work nearly identical, and both of them could achieve empirically the good result. I'll get to it later, but we didn't really differentiate the result because they were identical. The second problem to solve is enforcing the order. So when you request a transfer in this system, you essentially send a request to whoever has this data. In our example, a worker to the parameter server. Parameter server, if has the data, create a response and send it back. One way to enforce the order, one may wonder, is to add the control dependencies to the DAG. And if we do that, we wouldn't need to make any changes to framework, whatever it might be. However, this caused a huge underutilization network because it takes time to send a request to a server over the network and get the result back. And when we did that, the whole point of ordering thing simply vanished because of the underutilized network. The alternative is just to enforce it just before we send a response from the server. The biggest problem is it requires framework modification, but grad students are cheap, so we did it anyway. And one other problem is still we have the underutilized network problem, especially when a lower priority transfer is ready to be sent, but it's waiting for higher priority transfer. And there is this small time where we are not using the network. So in summary, this is how the tic-tac result look like. On the left side, you see the picture I showed you earlier, where we had gaps either at the beginning or the end. And on the right side, you see how tic-tac removed these gaps by doing a better communication ordering. We also experimented beyond like the visualization. So we use Microsoft Azure as our test bed. We tried 2 different workloads, one training with SGD, and the other one is inferencing using a parameter server, pretty similar to how it's being done in some of the reinforcement learning setups. We tested a number of convolutional neural networks, and to keep the evaluation fair, we use the original per worker batch size reported in the original paper. So the first noticeable result we had is the performance consistency. On the left side, you see the overlap coefficient of execution, or one sample execution. And as you can see, the red dots represent tag, and we are pretty close to the best possible order. On the right side, you see the normalized step time, and as you can see, the variance of tag is much smaller than vanilla TensorFlow. I guess I forgot to mention we tested it on TensorFlow. So in this picture, I show the throughput gain in terms of sample per second of using tag compared to vanilla TensorFlow. In most cases, we have a performance gain, in some cases significant. And for the simpler models with lower number of parameters, we didn't actually have a significant speed up. In fact, in some cases, we had slowdown because of the network underutilization I mentioned. The other interesting observation we had is, at least in the context of parameter server architecture, increasing the number of workers does not significantly change the gain we are getting, since every worker is independent. One other observation we had, which is obvious here, but I digest it for you here, is as the DAG become more complicated, the number of ops increases, we can clearly see a correlation between performance gain and number of ops. So I'm going to finish this talk with talking about limitation of this work and the future work. So tic-tac or any other computational ordering matters if you are in the reasonable realm of network to computation ratio. And the picture I cleverly show you it shows the good region. If you go to the extreme regions, there is not much point in ordering anything because the gain is so minimum, you don't want to add extra overhead. One example is Deep Lab over Summit system. It's the first system ever that break the exaflop barrier a few months ago. And in this system, the ratio is about 5%, and you don't see any benefit of actually doing any ordering. And another example is when you have a huge communication to computation ratio, which basically make your job network bounded instead of compute bounded. So it doesn't really matter if you put any ordering there. So I lied a little bit. There is a third reason you may miss your deadline, and that's network efficiency. Then the machine learning job, especially with parameter server, are a great source of network congestion. And network congestion make you to use less of the bandwidth than that's available to you. And one way to fix this problem is to use reduce. We compare our system to Horowat with MPI, which specifically try to fix this problem. An interesting observation is even if MPI on a non-high-performance network, I should say, has almost half the communication cost, it ends up performing worse, specifically because it doesn't do overlapping well. More about it, hopefully, in next SysML. Thank you so much for your attention. I'll take any question you may have.
Thanks, Hadi. Okay, so please come up and ask your questions. Don't be shy. There's 2 mics. I know they're far from you, but we won't look while you walk up. So please come and ask any questions, and we'll just alternate between the mics. Yes, go ahead. Oh, if you could, by the way, just say your name and maybe your affiliation before you ask the question. I think that'll be helpful.
Sure. Mark Tomby, Microsoft. So it seems like your speed-ups are higher for inference than training. Any insight into that?
Sure. The question is why inference gain more throughput, more speed up than full training. One of the reasons is like the overlapping is being done automatically on the backward pass. Like you generate the transfer automatically when you are doing the backward pass. So your gain or your loss because of the overlapping will be amortized by a perfectly overlap part of the training. And depends on your model, you may have between 20% to around 50% of the time allocated to backward pass, and this is exactly what we are seeing on the speed up numbers.
Thanks.
Hi, this is Rick Caillé with Microsoft as well. So it wasn't quite clear to me, maybe you've stated it. If network latency were 0, what's the absolute performance improvement you would get over the baseline? I'm just trying to understand, is it 50% overhead, 75%, 200?
Yeah, so latency actually didn't really matter in this work, but it depends on your ratio and number of parameter server. In the best case scenario, you'll get like 50% when your ratio, like network to communication ratio is 1, and you are doing inference, and about half of it when you are doing the full training. However, I should mention it's a free speed up. It's a time you are wasting because of the wrong transfer. It's not like we are compromising something in exchange for this speed up.
Hi, my name is Priya. I'm from Google. So you mentioned the already used case at the end. Do you expect was that using Tic-Tac, and do you expect Tic-Tac to benefit in those cases?
On the parameter servers, the question is about this picture. So on the parameter side, we use Tic-Tac. That's why it's near 1. On the MPI side, we use vanilla TensorFlow with Horowat, with OpenMPI on Azure.
And do you expect Tic-Tac to help with this if it could work?
So actually, it's a project that we are wrapping up right now. We use Tic-Tac in some part of the project, but we had to come up with a few other algorithms to improve further. One of the biggest problems with MPI is at least in the current implementation, it only happens on the backward pass, and we are not using the 40% time in the forward pass to do any network transfer, and we had to do something about it.
Okay, let's thank the speaker. Thank you, Hadi. Again.
Thank you so much.
Okay, our next speaker is Anand Jayarajan. He's a second-year master's student from the University of British Columbia, working with Alexandra Fedorova and Gennady Pakimenko. He's currently working on distributed machine learning optimizations. And today he's also going to tell us about how to optimize distributed DNN training by playing around with the representation granularity and synchronization of individual parameters. Okay. Thanks.
Yeah, thank you for the introduction. Good morning, everyone. Today I'm presenting priority-based parameter propagation for distributed deep neural network training. And this is a collaborative project between UBC, CMU, Vector Institute, and University of Toronto. So let me start by giving you an overall summary of this entire work. So as you all know, data parallel training is a popular strategy for scaling deep neural network training on a large cluster. But the problem is the performance benefits are highly bounded by the communication-heavy parameter synchronization operation. In this work, we make this key observation that the parameter synchronization can be scheduled better to reduce the communication overhead by taking advantage of the domain-specific knowledge that we have about the training algorithm. So based on this observation, we propose a new parameter synchronization mechanism called priority-based parameter propagation, or simply called P3. So P3 implements two key optimization. First one is parameter slicing, which synchronizes parameters at a finer granularity. And second one is priority-based update, which synchronizes parameters based on their priority. And with P3, we managed to improve the training performance of VGG19 by as much as 66%, a sequence-to-sequence-based model, Sockeye by 38%, and ResNet50 by 25%. Next, let me give you a little bit of background and motivation for this work. So neural network training on a single GPU is extremely time-consuming. These are 4 different machine learning models and their corresponding training time on a single P100 GPU. So as you can see, the training time takes about tens of hours to days, or sometimes even weeks to finish. And this happens because of 3 key reasons. First one is the high degree of computational complexity associated with the training algorithm. Second one is the training algorithm has to tune large number of training parameters, usually of the order of hundreds of millions or even billions. And finally, and most importantly, the algorithm has to process large data sets to achieve reasonable accuracy. Now, fortunately, the training algorithm is highly data parallel and can be taken advantage of and then scale on a larger cluster and improve the training performance. So one of the most common method used to implement data parallel training is to use parameter server architecture with synchronous HTD algorithm. So in this paradigm, there are multiple workers training a shared neural network, and the large data set is equally distributed among these worker machines. So during the training process, each worker machines compute gradients for the parameters in the neural network by sampling input from their own data shards. And then they synchronize these parameter updates by sending the gradients to the parameter server. Parameter server then aggregates these gradients and updates the parameters using optimization algorithm like stochastic gradient descent. And then finally broadcast these updated parameters back to the worker machines. Now the problem with this approach is the parameter synchronization, especially sending gradients to the parameter server and receiving the updated parameters back, usually has to go through a network, which is extremely communication-heavy operation. So just to give you a sense, it takes about, on an average, hundreds of megabytes that need to be transferred on every few hundreds of milliseconds. So because of that, the performance benefits out of data parallel training is highly bounded on this parameter synchronization step. So next, we conducted a case study on a popular machine learning framework, MXNet. And we trained ResNet50 on a 4-machine cluster, each with P4000 GPU. And we measured the training throughput while artificially limiting the network bandwidth. So in this graph, it's a bandwidth versus training throughput graph. And as you can see, the training throughput start to drop from 6 Gbps onwards. And it drops by more than 25% at 4 Gbps. So this means the training throughput suffers drastically if the network bandwidth is insufficient. Now, at the same time, if you look at the network utilization graph at this point, the network stays idle 20 to 30% of the time. This means even though the network bandwidth was insufficient for training, the framework ended up underutilizing the network and then pays more penalty on the training throughput. Next, we analyze the network utilization of heavier models, for example, VGG19. So in this graph, you can see the network is still idle considerable amount of the time during the training. But on top of that, the inbound and outbound traffic are not overlapped very well. This means the bidirectional bandwidth is not efficiently utilized. And in order to understand why this happens, let me give you a little bit of background about how parameter synchronization is actually implemented in these modern machine learning frameworks. So frameworks like MXNet and TensorFlow, they try to reduce the communication overhead by overlapping communication with the computation. The way they do is by taking advantage of the layered structure of the neural network. And you can see how the communication and computation is overlapped in the timeline graph. So the bottom row, I'll show the computation trace, and the top 3 rows, I'll show the communication trace with respect to individual layers. So during backward propagation, which starts at the final layer, and it progresses to the second layer. So while computing the gradients for the second layer, the frameworks issue synchronization for the previous layer, which is L3, by sending the gradients to the parameter server. And this continues to the first layer as well. So while computing the gradients of first layer, framework sends the gradients for the second layer, but at the same time, it receives the updated parameters for the third layer. And this happens until the parameters for the first layer has updated. And once this is done, we can start the next iteration by issuing the forward propagation. So as you can see, by doing this method of parameter synchronization, you can overlap the communication mostly with the backward propagation. And the delay between the 2 iterations is only limited by the synchronization for the first layer. But in this work, we make this key observation that this type of synchronization is not suitable for many neural networks. So our first key observation is regarding the underutilization of bidirectional bandwidth, and we propose a solution called parameter slicing. So if you look at the heavy models like VGG19, this is the parameter distribution graph of VGG19 layer index versus number of parameters on each layer. So you can see there is one single layer which contains more than 70% of the parameters in the whole neural network. So because of the presence of such considerably heavy layers, the parameter synchronization actually is dominated by that particular layer. So let me go back to that 3-layered neural network example. And in this case, the second layer, L2, takes thrice as much time to synchronize parameters compared to first and third layer. So because of that, during the highlighted time periods, the traffic flows only in one direction. That means the other direction, the network stays idle. So this is weighted network bandwidth that we can actually utilize to improve the communication overhead. So in order to solve this, we propose a solution called parameter slicing. The idea is to slice the layer into smaller pieces and then synchronize each slice independent to each other. So by doing so, as you can see, the layer 2 is split into 3 equal pieces and synchronize them independently. So the inbound and outbound traffic are perfectly overlapped, and the communication between the delay between the 2 iterations has reduced by more than 30%. Next observation is regarding the network idle time that we observed in the graphs, and we propose a solution called priority-based update. So if you look at the parameter distribution of image classification models like ResNet-50, so there is a uneven parameter distribution in this graph, in the sense that the initial layers are usually lighter convolution layers, and the final layers are heavier, fully connected layers. So because of this uneven distribution, the final layers takes too much time to communicate compared to the initial ones. So as you can see in this timeline graph, during backward propagation, we issue the synchronization for the final layer in first, and then progresses towards the initial layers. So because it takes too much time to communicate, it can induce additional queuing delay onto the lighter initial layers, and it can further delay the next iteration. So in this example, the last 2 layers, L3 and L2, takes twice as much time to synchronize compared to the lighter initial layer, L1. So because of that, even though the gradients for L1 was computed much earlier, The parameter synchronization for that layer has to be delayed until the network gets freed up. On top of that, so the delay between the two iterations has increased. So on top of that, during forward propagation, the network stays completely idle. So this is the idle time that you're observing in the network utilization graphs. Now, if you look at the per layer communication overhead, the initial layer is L1. The gradients for L1 is computed at the end of the backward propagation and is immediately consumed at the beginning of the next forward propagation. So it's very critical to synchronize parameters of L1 as soon as possible. But at the same time, for final layers, we can afford much higher communication delay. So in this example, L3, the gradients for L3 is computed at the end of the, at the beginning of the backward propagation and is only consumed at the end of the forward propagation. So based on this observation, we assign priorities to each layer. So the initial layers get the highest priority, and it decreases moving towards the end of the neural network, and the final layer gets the lowest priority. And after that, we synchronize the parameters based on this priority of layers. So we always allocate the network cycles for the highest priority, the currently available highest priority layer. And by doing so, the communication is evenly overlapped with both backward and forward propagation. And also the delay between two iterations has reduced by more than half. So to summarize, so basically, the iteration time is considerably reduced because of this even overlap between communication and computation. So based on these two optimizations, we propose a new parameter synchronization mechanism called P3, or priority-based parameter propagation, which is a combination of parameter slicing optimization and priority-based update. And we implemented P3 on top of MXNet by modifying the KV store module, and which took only like about 200 lines of code change. And P3 is open source, and if you want to know more about the implementation part, you can attend the poster session or you can read the paper. So we evaluated P3. We compared P3 against MXNet version 1.1 as the main baseline. And we used two image classification models, VGG19 and ResNet50, and one LSTM-based model, Sokai, as the main benchmarks. And in the evaluations, we use training throughput as the main evaluation metric. Now, according to MLPerf standard, the ideal evaluation metric should be the time to achieve a certain accuracy. But in this case, we can afford to use training throughput because both baseline and P3 always sends the full gradients, and they follow the same training curve. And we conducted this experiment in two different setups. So first one is on a private cluster on a tightly controlled environment where we have 4 machines and each equipped with a P4000 GPU and interconnected with 100 Gbps InfiniBand. And we also conducted experiments on real-world cloud-based clusters, which is AWS G3.4x class machines. So the first experiment is to measure the training throughput. And we conducted this experiment in 2 steps. So the first one is to analyze how the benefits out of parameter slicing optimization alone. And as you can see, we get about 50% improvement on VGG19 on top of the baseline performance. And with full P3, which incorporates both parameter slicing and priority-based update optimization, the performance benefits has increased to up to 66%. We see similar observations in other models like Sokai as well. With parameter slicing, we get about 30% improvement over baseline, and with P3, it further increased to about 38%. And for ResNet50, with P3, we get 25% improvement. Now, it's interesting that we don't see much benefits from parameter slicing optimization alone in this case. The main reason is ResNet50 is a comparatively lighter model, and there is no disproportionately heavy layer which could dominate the parameter synchronization and underutilize the bidirectional bandwidth. So as I explained, the P3 actually improves the communication overhead by better utilizing the available network bandwidth. So this is an example of training of Sokai on the same 4-machine cluster. So you can see compared to baseline, P3 is utilizing the network bandwidth more efficiently, and both incoming and outgoing traffic are efficiently overlapped. So finally, we measure the scalability of P3 compared to baseline. This is done on an AWS cluster with G3.4x large machines and 10 Gbps network bandwidth. We measured this training throughput by increasing the cluster size from 1 to 16. So as you can see, P3 actually scales much better than baseline with about 61% more performance compared to the baseline system. So we have more results from the paper. We compared P3 against TensorFlow and Poseidon, which is like state-of-the-art frameworks. And we also compared P3 against gradient compression techniques like deep gradient compression, and also with asynchronous SGD methods. So to conclude, so in this work, we try to target the communication overhead of parameter synchronization step and try to find ways to optimize that. And based on this problem, we propose a new parameter synchronization mechanism called P3, which implements 2 key optimizations. First one is parameter slicing, which synchronizes parameters at a finer granularity than it's been done right now. And we also consider the priority of the layers and then synchronize them according to that, which is priority-based updates optimization. And with P3, we managed to get about 66% improvement over VGG19, and 38% improvement on Sokai, and 25% improvement on Resent 50. So finally, P3 source code is open, and we have also validated the results and the source code using a SysML artifact evaluation method. And if you want to reproduce the results, the instructions are available in the appendix of the paper. Thank you.
Okay, thanks, Anand. We're open for questions. If anyone has a question, please come up to the mics and ask your question. No questions? I'm going to have to ask a really hard question if you guys don't ask questions.
So this is Anusha from NetApp. I was wondering, like, this priority, doesn't it need a lot of information about what model you are going to train, or is it independent, like can work in generic fashion?
Okay, so there are 2 ways to answer that question. So most of the neural network has this static computation graph. So you can actually do static analysis on top of this DAG and then prepare this priority. But some of the modern neural networks contain dynamic control flows, and it's very difficult to do static analysis and compute the prioritization for all the layers. So currently we do static analysis and prioritize the layers, but there's an interesting future work to do on dynamic control computation graphs.
Thank you.
Hi, Leon from McKinsey. My first question would be, so does your parameter slicing assume independence of the parameters? And also, what's the impact of this approach on the classification rate versus a non-parameter slicing approach?
Impact on classification?
So the actual classification rate, like the model performance.
Did you say classification? I can't hear.
Yeah.
Okay. Yeah. So parameter slicing optimization actually is useful only for like heavy models that I shown for like VGG19 or Sokai, which contains like huge layers which can dominate this parameter synchronization process. So the main advantage is coming from utilizing both channels, the incoming and outgoing channels at the same time, and pipelining the traffic really well. Yeah.
Yeah.
Dave Anderson, Carnegie Mellon. So I'm curious about one thing, which is the previous talk showed that they were getting a performance speed up on ResNet. and you showed that the performance speedup kind of stopped on ResNet. Can you, I realize you're only the author of one of these two papers, but can you speculate on why there's a difference?
So for ResNet, yeah, so as you can see in the graphs, let me just pull that. This one, right?
Yep.
Yeah, so in this graph, when you have enough bandwidth, like more than 6 Gbps, you have enough network bandwidth and the communication is no longer the bottleneck. But if you have...
And that totally matches my intuition, but I'm curious
Yes.
because the previous paper showed that they were able to get training speedups, at least in their TensorFlow parameter server thing, on ResNet.
Yeah, I'm not sure what experiments they have conducted and what was the parameters used, but this is the results that we are getting.
Okay, thanks.
Yeah.
Thanks, Dave. Okay. Any other questions? Okay, let's thank the speaker one more time. Okay, our next speaker is Min-Sik Cho. He's from IBM Research, and he's interested in systems and algorithms for training and inference. And he's going to tell us about a system called Blue Connect, which decomposes... sorry. Good to test. Which decomposes all reduce operations in smart scatter and gather ways to improve performance. Okay, go ahead, Min-Sik.
Okay, thank you. So good morning, everyone. So my name is Min-Sik Cho from IBM, and today I'm going to talk about how to decompose or reduce for deep learning on heterogeneous network hierarchy. So this is a joiner with the doctors Uli Finkler, David Kung, Hilary Hunter, all from IBM. So we love large-scale deep learning because that's the way to speed up training. Once we can speed up training, there are many good things, right? We can explore different architectures, so we can try different hyperparameter tuning, so there are many good things. So for example, if there is a job which may take 9 days on a single GPU, as long as you know how to do large batch size and hyperparameter tuning, it's possible that we can finish the same training task in hours, like with many GPUs, right? But the problem I see here is that we love large-scale deep learning, but there is an obvious bottleneck coming up in the future. So if we take a look at technology advancements in the last 3 years from 2015 to 2018, think about technology from M company. So they increased the bandwidth by 2x over 3 years for single port. But if you think of, let's say, the technology from N company, they were able to increase, let's say, the props by X times if we want to use like F16. So in last 3 years, competition is getting better very fast, but meanwhile, network bandwidth is not catching up. And actually, this is new. I mean, we have seen this trend in microarchitecture for last multiple decades, and then the same thing is going to happen to large-scale deep learning as well. So this really motivates why we need to have a better algorithm for communication and the infrastructure. So thanks to previous two talks, I don't think I need to spend that much time on this slide. So if we want to do large-scale deep learning, there are a few ways. The first thing is the model-level parallelism. So we will partition the models, and then each piece will go to different devices to speed up the training itself. Or we can use like a large batch size to enable data-level parallelism. I mean, one obvious approach is, as in the previous two talks, somebody can use a parameter server. But these days, actually, we are more interested in like a data parallelism based on all-reduce technology. Actually, all-reduce is not a new technology. I mean, this is a concept that has been there for 2 decades in HPC community. But for your background, I mean, this is like kind of what I say, the picture I copied from mpitutorial.com. So this is like a tutorial level stuff. So what it does is that every learner will have, let's say, the number array, and then this all-reduce operation will add up numbers like element by element, and then share the final result across all the runners in the picture. So this is a very natural mapping to stochastic gradient descent, right? Every runner will generate local gradient, and then we want to do all reduce over those local gradients so that everybody can have a gradient, global gradient for the parameter update, right? So obviously, this has been already like discussed in prior art. I mean, Baidu started using this technology in deep learning around like February 2017, and then this is their animation. So let me like go through these steps. So I have 5 GPUs here, and then I want to do all reduce. The typical technology to do all reduce is having reduce scatter followed by all gather. So here I have 5 GPUs. That's the reason why each number array, I mean, in this case, this is a gradient. Each gradient array is partitioned into 5 pieces. Then now I'm going to propagate those numbers through the neighbors so that I can have final sum at the end of the scatter. First, you can see that. You can follow like the boxes. Now I have like an intermediate sum here. Then in the next cycle, I'm going to send my result to my neighbor again and again and again. So after 5 cycles, everybody will have one piece of the final result. And then this is like a result from like a reduced scatter. So this is why this is called a reduced scatter, because the result is reduced, but it is scattered. So next step here is, now we want to do all gather. So all gather is simply a broadcasting step. So now I have a final result, but this is only partial result. So I want to broadcast my result across all the runners in the picture to get the all results done. So now I have a global gradient, so I'm ready to do parameter update. This ring-based algorithm has been already discussed in HPC community around like 2005. You can easily like Google the paper. This is a bandwidth optimal algorithm. So you cannot do any better, only if you have a uniform bandwidth distribution. Everybody has the same bandwidth everywhere, then this is a king. But the problem here is that once you start having some kind of, let's say, the poor bandwidth somewhere in the system, there will be your bottleneck, because everybody needs to wait for the data to be transferred over the slow link. That's the problem. So somewhere, sometimes your bandwidth will be underutilized. And then remember that to enable these steps, I need to do like 10 steps, from 5 from the reduced scatter, 5 from the all gather to complete the all reduce when I have 5 GPUs. But imagine that you have like 1,000 GPUs or 10,000 GPUs. Then easily your latency will be added up. Another key problem in this algorithm is that it has a linear dependency in terms of number of GPUs for latency. So if you have many GPUs, the latency will be your problem. Obviously, we are smart. So people have been thinking about how to address this latency problem. So last year, around July, Tencent proposed this idea for their experiments. So their idea is that I have many boxes, and then I'm going to pick master GPU per box. And the first step is I'm going to reduce my gradient to the master guy, and the master guy will perform reduce among master guys only. Then I will share my result back to all my friends in the same boxes. So this is the obvious approach, but you can see that still this is kind of what I said, the linear flavor kind of algorithm. So in fact, Horvath has exactly the same implementation in their source code around, let's say, October 2018. So what it shows here is that, so it would do reduce scatter, then reduce to the master. And then it will do MPI all reduce to all reduce across masters, then all gather, and then broadcast. What I'm going to show in Blue Connect is that actually this is not optimal traffic pattern. We can do better than this. So essentially, I'm going to say that actually we don't need to have those 2 steps, which is as expensive as other steps in this flow. The problem with this approach is that, first of all, even though you can like reduce the number of steps by 4, still that's a linear complexity. And then traffic pattern is not optimal. And then you spend multi-$1,000s on GPUs, but in this picture, only master GPU will be active at a moment. So which is like kind of like wasting money. Sony 2018, around November, proposed like a different kind of all reduce. I name it as a Torus all reduce, because this is based on like a Torus architecture. So what they have done here is that they did a reduce scatter, and then all reduce, and then all gather, and then that's the end of all reduce operation. You will realize that actually this is kind of like similar to what I'm going to propose here, but in fact, the Blue Connect is a kind of a generalization scheme of this is Sony's approach. And then I can claim that we had this idea long time before like Sony came up with this idea because we already have a patent around the 2017 June timeframe. So what I'm going to propose here is that this is a different way of doing all reduce based on like a decomposition. So before getting into like the details, the benefit from decomposing all reduce into multiple pieces is that it's easier to map your operation to different network fabrics. And then this will enable us to explore like a various trade-off between latency and bandwidth. And then from the like engineering perspective, we can do mix and match various algorithms and implementations from different vendors. So let me show you like what is the trick here. So already it is known that all reduce can be done by calling reduce scalar and all-gather. But what is not known so far is that if the total number of all the runners can form some kind of hypercube, actually we can further decompose reduce scalar and all-gather into multi-stages and then parallelizable reduce scalars and then all-gather operations. So there is some kind of like a graph theory behind this, but I will skip that about it. So I have a concrete example on how it works. So let's take a look at here. So let's say that I have a hypothetical, let's say the cloud environment where I have only 4 machines, and then each machine has a different colors, and then each machine has now 3 GPUs, and then those GPUs are kind of like linked to the, let's say, the PCI Express, which is kind of a high bandwidth. And then 2 machines are like in the single rack, and then I have a 1 directed switch. So this is kind of like a 3-level network hierarchy. And then let's assume that each level has a very different kind of a network bandwidth. So now, because I have in total 12 GPUs, I can think of various hypercubes, right? So I can have like a 12 by 1, which is kind of a 1-dimensional hypercube, which is kind of like a ring, right, in this case. And then if I make a day choice, the total latency is 24 because there are 12 GPUs. But if I can think of, let's say, different hypercube setting, like a 2 by 6, 4 by 3, or 3 by 2 by 2, as long as it is factorizable, you can think of various kind of hypercubes. And then they do have a different latency. And then they do have a different chemistry to your network infrastructure. So in this case, my obvious choice is that, okay, this is my best like chemistry to the network topology, because this is how I can avoid using poor bandwidth as late as possible. The key idea is that I want to do as many operations as possible with a higher bandwidth first before touching up any, let's say, the poor bandwidth up in the higher level in the network architecture. So because I decide to have, let's say, the 3-dimensional hypercube, I have 3 steps for reduced scalars, and then I have 3 steps for the all-gather. You can see that they are symmetric. And then at each stage of a reduced scalar and all-gathers, I'm going to have a multiple rings. And then size of a ring is based on like a dimension of that hypercube. So now you can see that I'm trying to use my neighbor GPUs first before touching up any like a remote GPUs to utilize like a higher bandwidth better to avoid having bottleneck from the poor bandwidth during the ring operation. So this is like a topology where all is decomposition. So now let me show you like what is going to happen inside this algorithm. So now I have, let's say, that like 12 GPUs here, and then in the first dimension, I'm going to have, let's say, the 4 independent like reduced scale operations in parallel. So here, because everybody knows only, let's say, that 2 other neighbors, the partition size is 4. Then I'm going to call, let's say, the reduced scalar to finish like a reduced scalar on all the machines. Then now I'm going to change the direction, and then we look at like my neighbor under the same rack, and then we'll do the, let's say, the reduced scalar again. So in this case, the actual, let's say, the communication volume is half because I have already done some work in the first step, and then I will just talk to my neighbor in the same rack. And then here, I'm going to run like 6 concurrent like reduced scalars. In the last step, now the data volume is like now 1, and then I have 2 neighbors, and then I'm going to now talk to my neighbor across the rack to minimize the impact from the poor bandwidth. So if I continue doing this, at the end of the day, I will have a reduced scalar done in this way, and then for all gather, I can take exactly the same step in a reverse order to finish the all reduced operation. So this is a kind of like a big picture from one step back. So I decompose, let's say, the single or reduced operation into multiple multi-stages and then parallelizable reduced scalar and then OR-gate operations. And then because they are like independent reduced scalar operations, it is possible to use different implementations, different algorithms from different vendors. For example, I can use like, let's say, the tree-based algorithm if that works for me. But in the second stage, I can use, let's say, the library from Mellanox because that's like a best library from vendor. So at the end of the day, I can do mix and match to deliver the best end-to-end performance based on variable options. So this is kind of what I say, the mix and match to deliver the best performance. So this is a result. So we compared this like all use operation against, let's say, the NICO 2.3 on 2 different platforms. So this is like IBM Power Systems. So you may know that IBM is a kind of a numeral machine. So between GPUs, they already have a network hierarchy. So even though I have what I say, the all reduced within box, because this algorithm knows how to take advantage of in-system topology, we can deliver much better throughput than NICO. If we cross the boxes, then obviously there is like already network hierarchy again, and then we can deliver better performance than NICO 2.3. So in this case, I use like 2 IBM systems and then 10 gigabyte per second InfiniBand. Then what about x86? Because x86 doesn't have a hierarchy because this is a kind of a symmetric PCI Express tree. So in this case, we don't have any advantage because there is no network hierarchy. But as soon as you leave the systems and then heating up the, let's say, the network bottleneck, then it can perform better than NICO. So in this case, I use like 2 x86 systems with a P100, and then the connection is a 10 gigabit Ethernet. So this is like a grand scale experiments I have done. So I was able to secure like 48 IBM P9 systems. And so the configuration is that I have 16 machines per rack, and then I have 3 racks, and then they are hooked through the director switch. So when I integrated Blue Connect into Caffe 2, I was able to compare against like different implementations based on like a data parallelism for all reduce. So I compared with MPI all reduce and then Glue from Facebook, which is based on NICO and then IBBird, and then Blue Connect algorithm. So now you can see that Blue Connect delivers like a best scalability across different kind of different let's say the level of hierarchies with a different number of GPUs. So this shows that if we understand cluster, and then if we know how to decompose the all reduce into different hypercubes, there is a way to make our all reduced throughput better. So this is a kind of what I say the final summary slide. So MPI, I mean, typical, let's say the ring-based all reduced algorithm is kind of universal, and then it works for all the cases, which is good. But the problem is that once you have a network hierarchy, once you have a different bandwidth at different level of your infrastructure, then it will be throttled by the worst case bandwidth, which is not good. But in Blue Connect cannot avoid that worst case bandwidth. But the trick here is that we will try to use like a higher bandwidth as much as possible, and then we'll do as much as what we can do before hitting that like worst case bandwidth to minimize the impact. In terms of latency, ring algorithm has a linear complexity. So think of, let's say, that 27,000 GPUs from some computer. If we want to do ring-based or reduce, this will take a very long time because you will get suffocated by the, like a very high latency overhead. But in Blue Connected case, you have choices now. You can try different decompositions to find a good balance between bandwidth utilization and the latency overhead. So Blue Connect provides a kind of, let's say, that user control the knob to play the like trade-off between bandwidth and latency overhead. But there is obvious limitations. The first limitation is that you have to understand your system architecture. That's the first thing. Otherwise, you cannot build your hypercube. Second thing is that this is applicable if number of GPU is factorizable. For example, I have 17 GPUs, which is a prime number. Then this is not going to work, obviously. And then another like limitation here is now I have multiple independent steps and then can use a different vendor libraries, but that means that I need to do some kind of a context switching, which will have some kind of impact in terms of like implementation efficiency. Okay, that's all I have. Thank you.
Okay, do we have any questions? Again, please line up at the mics if you do. I think I should give incentives for asking questions like candy or something, because it really is helpful when you do that. So let me kick things off. So Vincent, you mentioned so you're commenting on how you can improve things by making it more of a hierarchical approach, right?
Yeah.
So in the limit, that could look like a tree, which wouldn't be linear, right? That would be like a logarithmic thing. Are you saying that in practice, because these hierarchies and these trees are very flat, it effectively is like a linear thing?
So first of all, this is not tree, because you can see that as it goes up, the partition size is smaller.
Okay.
So that's a very key difference from tree, right? In tree, everything is the same size at every level. But here, the size is getting smaller. That was like my first answer to your question. What was the second thing?
No, that's fine. I just was wondering why you were referring to that as still a very linear approach. Yeah. So I see you're saying that in a tree-based approach, as you go up, it's still a constant amount or the same amount at every level, and here it's reducing.
Of course, I mean, total information we exchange it across the network doesn't change, because that's like a minimum thing we need to do for all reduce. But here it is like a volume is smaller, and then we increase the number of connections across the network switch to really like fill up the bandwidth.
Okay, there's a question over there.
Hi, my name is Priya. I have a question. So in a heterogeneous system, would BlueConnect try out different configurations and figure out the optimal, or does the user have to do that?
So question is that whether we will try out different configurations for a given system. Is that the question? Yes. So the catch here is that, I mean, for example, I need to know my system beforehand, and then I need to try like different configurations and then vendor libraries to get the best performance. And then that was like a given before actual training is done. So yes, we need to understand systems, and then we need to find out like a best configuration beforehand, before starting the actual training job.
But by we, you mean like BlueConnect will figure this out, or?
Yeah, no, we have, I mean, in practice, we have some kind of, what I say, the test, like a binary to try out different configurations, and then through the process, we will find out the best configuration in a try and error manner.
Thank you.
Okay, any other questions? Oh, I had one last question.
Yeah.
This prime number issue, is that really a big deal? Can you just ignore some of the GPUs and do the work on the rest of them so it's not a prime number?
Well, actually, this is a big deal, because once I cannot build the hypercube, I mean, everything will break. So we are working on different kind of algorithm, which is kind of generalized approach of this thing. But for now, in current BlueConnect, the factorization is like a minimum requirement.
Okay, let's thank the speaker one more time. Okay, our final speaker for this session is Jihao Jia, and he's a student at Stanford, a PhD student working with Matej Zaharia and Alex Eichen on systems optimizations for DNN computations. And he's going to take us beyond data and model parallelism with an approach called SOAP, where each letter stands for something that you can parallelize. Thanks, Jihao.
Yep. Hi, thanks for the introduction. So my name is Zhihao Jia, and I'm a PhD student working with Matej and Alex. So today I would like to present some of our recent work on optimizing DN training by using strategies that go beyond data and model parallelism. So parallelizing deep neural network training is a hard problem, and I think previous talks has already explained why this is such a hard problem. So most existing approaches have been focusing on using data and model parallelism to distribute your training. So for example, data parallelism is the default choice in most existing frameworks. And also people have introduced manually designed strategies that try to combine data and model parallelism to accelerate some specific deep neural networks. And previous work have also introduced automatic generated strategies. For example, Google have proposed this colloq RL, which uses reinforcement learning to find device placement in model parallelism. So we found that previous work have been focusing on parallelizing using dimension data and model dimensions, but we found exploring additional dimensions that go beyond data and model parallelism can further accelerate your DNA training performance. So in our experiments, we show that we can further increase your training throughput by up to 3.3 times by using additional dimensions that go beyond data and model parallelism. So in this work, we proposed a search-based approach to address the problem. So first, we define a new search space of potential parallelization strategies. So we call it the SOAP search space. So it includes all existing approaches as special cases in our search space, and we also consider much more different strategies. And second, we build a cost model and a search algorithm to efficiently explore the SOAP search space. And by combining these two techniques, we are able to find optimized strategies that outperform existing approaches. So first, I would like to talk about the SOAP search space, which considers the sample, operator, attributes, and parameter dimensions to parallelize training. So the sample dimension considers how to partition your training samples across devices. So this has been widely used by data parallelism. So the bottom figure shows parallelism in the sample dimension for 1D convolution. So the left cube shows computations defined in 1D convolution. So you have different samples. And so the second dimension is parameter dimension that indicates different activations involved within a sample. And we also have a pixel dimension that represents computations related to different pixels in your 1D convolution. So using the sample dimension, you will end up assigning different samples to different GPU devices. So the second dimension we considered is operator dimension, which try to partition different gene operators across different devices. So the bottom figure shows one example of model parallelism that assign different convolution operators to different GPU devices. And the third dimension we considered in SOAP is the attribute dimension, which try to partition different attributes within a sample to different devices. So you can think of attributes as pixels in your image. So that the idea is that if you have a high-resolution image, you can assign different sub-image to different devices to parallelize your computation. So the last dimension we considered here is the parameter dimension, which try to partition parameters within an operator on different GPU devices. So as a result, different GPU will end up computing gradients for disjoint subset of parameters. So this can help you avoid any parameter synchronization. So in SOAP, we also consider hybrid parallelism that use any combination of the SOAP dimension to hybrid your training process. So the left two shows two example hybrid parallelism strategies for 1D convolution. And in our design of the SOAP search space, it is guaranteed that different strategies will perform the exact same computation. So you can get the same model accuracy regardless of which exact strategy you choose to parallelize training. So this allows us to focus on the runtime performance of your training process. So this table summarizes the SOAP dimensions that has been used by previous work. As you can see that most previous work are trying to parallelize training by using a single or two dimensions in the SOAP search space. And in this work, we are the first paper that tried to parallelize in all SOAP dimensions. And we show that by considering a larger search space of parallelization strategies, we are able to find better solutions. So to give you a visualization example, so this figure shows how to parallelize an inception model in data parallelism. So each box shows parallelization for one operator. So the horizontal dimension is the parameter dimension, and the vertical dimension is the sample dimension. And different colors shows assignments to different GPU devices. So the top figure shows data parallelism that always use the sample dimension to parallelize training. And the bottom figure shows one example among many others in the SOAP search space. So first, you can use data parallelism for some layers. You can use model parallelism for some other layers. And you can also choose hybrid parallelism for intermediate layers. And in SOAP, we also consider different degree of parallelism. So different operators can have different parallelism degrees. So these are all considered in our SOAP search space. So once we have defined a space of parallelization strategies, the next question is how can you find an optimized solution in this large search space? So we build a cost model and a search algorithm for this to complete this task. So we implement our idea in a system we call flex flow. So this figure shows an overview of flex flow. So we take as inputs 2 graphs. So one is an operator graph that describes the computation in your deep neural network model. And we also take a device topology graph that describes the set of available devices you would like to use for training, and also the interconnections between devices. And 2 graphs are sent to an execution optimizer, which will try to find an optimized solution in the SOAP search space. So we use MCMC Markov chain Monte Carlo search algorithm in our execution optimizer. And we build an execution simulator as the cost model. So the MCMC search algorithm will iteratively generate candidate strategies that try to parallelize your operator graph on your device topology. So the candidate parallelization strategies are sent to the simulator, which will simulate the execution of this strategy and send the simulated performance back to the search algorithm. So this feedback will be used for generating future candidates. So once this search procedure is completed, the best found strategy will be sent to a distributed runtime and will be used to parallelize training. So to build a cost model, the main challenge is that measuring distributed execution on real hardware is very slow and expensive. So for example, if you would like to launch and measure a distributed execution, it may take seconds or up to minutes just to measure a single execution. And we also found 2 interesting observations for DNA training. First is that the performance of DNA operators is actually highly predictable. This is because most DNA operators are using dense linear algebra. And our second observation is that DNA models, although they have a huge amount of parameters, operators, but only a small number of them are distinct operators. So you have a lot of redundant operators. So for example, consider a neural machine translation model which has hundreds of operators. Only 4 of them are distinct. So based on these observations, we propose an execution simulator. The idea is that we just need to measure each distinct operator once on the actual device you would like to use. And we can use our initial measurements to estimate the performance of different parallelization strategies. So this figure shows an example operator graph, which is a very simple recurrent neural network model. And the bottom table shows one example parallelization strategies, so which describes how to partition every operator and how to assign the partitioned task to actual devices. So in this example, we decide to partition the first 4 operators to each to 2 subtasks by using a parallelism in the sample dimension. And we decide to partition the last 2 operators to a single task. And by analyzing this parallelization strategy, the execution simulator will build a task graph, which will include all computations defined in these parallelization strategies. And in this task graph, we can estimate the runtime of these tasks by using our initial measurements on the operators. And we can also fill in the data transfer between tasks by analyzing the dependencies in your original operator graph. So each edge in the task graph shows data transfer between different devices. And we estimate the data transfer time by assuming that the underlying channel between the 2 devices can be fully utilized. So this data transfer time is proportional to the size of the data being transferred. So this task graph will allow us to estimate the performance of a parallelization strategy. And to further accelerate the simulation procedure, we also proposed what we call the delta simulation algorithm. The idea is that you don't have to build the task graph from scratch over and over again. So this is because the Markov chain Monte Carlo search algorithm used in FlexFlow. So it tried to propose a new strategy by changing a single operator in the original strategy. So as a result, most part of the task graph do not change from one strategy to the next strategy. So our solution is that we can simulate a new strategy by using incremental updates to the original strategy. So, for example, this is the simulation we have seen in previous slides. And if you would like to change how we partition or how we parallelize the third operator, so instead of building a new task graph from scratch, you just need to recompute the operators in this gray area. So this can accelerate the simulation procedure. So this figure compares the performance of the delta and full simulation. So we are trying to find an optimized strategy for parallelizing the neural machine translation model on 16 P100 GPUs on 4 nodes. So the x-axis shows the search time, and the y-axis shows the performance of the best found solution. So you can see that our search algorithm is able to gradually find better and better solutions by using more search time. And we terminate the search procedure if we cannot find any better solution in half of the search time. So for this example, our delta simulation is 2.3 times faster than the full simulation algorithms. So in our experiments, we found that in general, the delta simulation can reduce the search time by 2 to 7 times. And as a result, by using the delta simulation algorithm, so our our end-to-end search procedure only take a few minutes, so which is negligible compared to your training time, which generally take hours or even days. So this makes our search very efficient to use. So in order to evaluate the performance of the best found strategy by FlexFlow, so we compare it with existing approaches on 2 GPU clusters with different generation of GPU and also different connections between GPU devices. We also evaluate our implementation on 6 DN benchmarks, including 3 CNNs for image classifications, and also 3 recurrent neural networks for different language tasks. So this figure compares the training throughput of Google's neural machine translation model by using different parallelization strategies. So the x-axis shows the different number of machines, and the y-axis shows the training throughput. And as you can see that FlexFlow is able to find more efficient strategies, and which is 1.7 times faster than the best baseline. And we also do the same experiments on up to 6 DNs. And so this table shows the speed up we can achieve. And in general, FlexFlow is able to accelerate your training procedure by up to 3.3 times. So one question you may have is why the best found strategy found by FlexFlow is faster than baseline. So in order to answer this question, we also do a case study on the best discovered strategy for parallelizing Google's neural machine translation model on 4 P100 GPUs. So this figure shows the best found strategy. Again, each square shows how to parallelize a single operator. And the difference between this recurrent neural network and previous CNNs is that you can see the green large rectangles. So the operators different operators in the same green box, so they share parameters. So you also need to synchronize gradients among different operators in the same green box. So we try to analyze why this is faster than the existing baseline. So and here is some insights we have discovered. So first is that for the embedding layers, the embedding layers involves very heavy communication, but only very light-weighted computation. So as a result, FlexFlow decides to assign all operators within the same embedding layer to a single device. The benefit is that you no longer have to do any communication because all gradients are computed on a single device. So for the last softmax layer, it involves very heavy communication, but also very heavy computation. So you cannot assign all operators to a single device because that will result in significant workload imbalance. So to solve this, FlexFlow decided to explore parallelism in the parameter dimension. so that you can get balanced workload distribution. And also by exploring the parameter dimension, we can also reduce your data transfer costs. So finally, for the intermediate recurrent LSTM layers, it involves light communication, but very heavy computation. So as a result, FlexFlow decides to use hybrid parallelism in both the sample and operator dimensions to parallelize training. So to conclude, we have presented, so first we have presented FlexFlow, the SOAP search space, and we found that by exploring the SOAP search space, can find faster parallelization strategies that outperform existing approaches by up to 3.3 times. And we also implement our idea in a distributed runtime called FlexFlow that can automatically find efficient strategies in the SOAP search space. So this will conclude my talk, and I'm happy to take any questions. Thank you.
Go ahead.
Marco Canini from Cast. Thank you. This is very interesting work. So my question is with regard to, say, these case studies, and when you actually analyze the best solutions that you found, my question relates as to whether you have observed particularly homogeneity in the solution that you found or heterogeneity with respect to, say, the various parallelism dimensions. And if you have observed high levels of homogeneity, then the follow-up question would be whether that came up as a natural observation. Okay, given that characteristics, it actually makes sense to have this solution, or whether you found something particularly surprising.
I'm thinking about how should I summarize the question. That's a very good question. I think the question is, do you find some common pattern in your best found discovered solutions, or they are just special cases for special architectures? And I think so. My observation is that so the best found strategy is different on different devices. So I think this is because the search algorithm try to do local optimizations that try to make that local subgraph perform better on the actual hardware. So if you look at the entire graph, it's hard to extract patterns. But you can still, from a high-level perspective, you can still get some high-level insights about the solutions of the best found. And we also have some other interesting case study on other networks in the paper, but I don't have time to include them in the talk.
Thank you.
Thank you.
Good, and from the other mic.
Hi, Amir Sadoui from Amazon. I was wondering, how do you go about building the device topology graph, and does it take into account like host memory and like device memory?
All right, so the question is, how do you model the device topology? So we build a device topology by considering the devices you have for training, and also the connections between devices. So in the device topology graph, each node is a device, is a GPU device in our example, and each edge is a link between different GPU devices. And the weight of the link is just the bandwidth of the channel between devices.
Okay, so
yes,
it's not constrained on the memory then?
No, it's not considering. We do not consider memory constraints in our search.
Hi, Tomer from Google here. Mm-hmm. So it seems like there is a fairly strong conceptual relationship between attributes and parameters. Did you find that there's a distinct benefit to including them as two separate dimensions in your search space? Or did you at any point try out only having three dimensions?
Yep. So the question is, what's the difference between attributes and parameter dimensions? So if you parallelize in the parameter dimension, you don't have to. So that will result in partitioned parameters. So you don't have to communicate parameters if you try to parallelize in parameter dimension. But for attributes, you still need to communicate parameters even if you parallelize in the attributes dimension. So that's the difference.
Right, but did you find that there's cases where you would possibly want to have different combinations of attribute and parameter, or did it always end up being if you were doing parameter parallelization, you would also be doing attribute
Right. So we found that the attributes dimension is very important for convolutional neural networks. The reason is because if you partition over the attributes dimension, it will result in better layout for the underlying GPU. So in our paper, we found that if you partition over the attribute dimension, the GPU kernel will be faster than if you use the sample dimension. So that there are some, we have some more discussions in the paper to talk about the benefit of the attributes dimension.
Thanks.
Thank you.
Thanks. Go ahead.
Hi, Leon from McKinsey. You said that you typically run MCMC for 2 to 3 minutes to sample from your search space, right?
Mm-hmm.
But do you feel like you'll get extensive coverage in 2 to 3 minutes of the entire search space given that amount of time? Or like, do you feel like you've sampled everything within that? Because the search space is quite complex.
Right.
It's quite high dimensional. Do you think that it might benefit from like Hamiltonian Monte Carlo as well?
Right. That's a very good question. So so the search space is very large, and why do you choose MCMC, not the others? So we think in terms our idea is that once you have this search space, you need to find some specific search algorithm, and MCMC is our choice, but we didn't say that MCMC is the best one. And one interesting work is, can you use some heterogeneous or hierarchical search algorithm to accelerate this search? And this is one of our future work, and we are currently working on this direction to use some more efficient search algorithm to accelerate the search and hopefully find better solution.
Thanks.
Thank you.
Junior Wei from Carnegie Mellon.
Hey.
This very interesting work. So my question is about, because you have many different dimensions partitioning the operator, so this means there are many different ways of parallelizing it. Does this mean that framework developers have to manually provide manual implementation of all those operators corresponding to different parallelization, or is there a way for FlexFlow to automate this?
You mean automate the implementation of using different...
Partitioning, like each single operator corresponding to different partitioning dependencies.
Oh, right. So in our implementation, we use, the distributed runtime is built on our previous work called Legion. And so in terms of the actual kernel implementation, we use existing CUDA libraries to implement. And we found that in cases, if there is no existing implementation for particular partitioning, we also do write several kernels. But in most cases, there are existing kernels available for us to directly use, regardless of how you parallelize the operator.
I see. Okay. Thank you.
Thank you.
This is Rudy from Carnegie Mellon. So this is a very interesting work. My question is, like, your motivation was the search space in prior only has like data and parameter.
Mm-hmm.
Have you considered using your search algorithm on those search space and compare with the extra search space? How does that improve? That's the first question. And the second question is, how does accuracy of the cost model affect your search results?
Okay, so the first question is, have you tried to run your search algorithm by just considering data and model dimensions? So we haven't. This is a very interesting experiment to do, but we haven't done it. Yeah, but it's very interesting to try. So the second question, I forgot, sorry.
How does the cost model of your performance cost model
I see.
affect?
So how accurate is your cost model? Yeah, so actually we have a backup slides. So in general, our cost model is very accurate and also preserve. So this is the slide. So this compares the simulated and actual performance. And as you can see that we are very accurate. And we also preserve the ordering. So this means the simulated is a very good metric to compare different solutions.
Thanks. Okay. Let's go to the last question.
Hi, Yitzhak Lackerman, Bloomberg LP. Mm-hmm. I was wondering if when you start doing all this reordering in order to do the parallelization, do you start getting numeric errors start popping up? Or do you start getting limitations to saying you're requiring to use float 32 instead of float 16 or float 64 in order to prevent the errors?
You mean the precision or the...
So I mean, basically if you're reorganizing and reparallelizing many operations, or splitting operations and then letting them go indeterminately, do you start getting numerical errors popping up?
Oh, right. So in our training, we observe the exact same training accuracy, but numerically, because you reorder some arithmetic operations, so you may still get some floating difference. So that's true. But we have verified that we can achieve the same model accuracy by using our optimized strategy. Yeah.
Okay. Thank you. Let's thank Jihao again. Thank you very much.
Thank you.
Okay, so that concludes the first session. I want to thank all 4 speakers for giving very clear and great talks and sticking to the time constraint, and also for the audience for asking questions. Let's try to keep that up for the next sessions. We have a coffee break now for half an hour, and we'll see you at 11 a.m. for another session on distributed and parallel learning.
Oh, okay. Looks good. Yeah, yeah, yeah.
Okay. If you want to try and go full screen, we'll just make sure that it keeps the setting.
Yeah.
All right, perfect. So I haven't seen the person in front of you yet, but so I don't know what kind of computer they have, but whatever it is, if you just plug that back in, as soon as you see it here, and I have a preview back there, I can see the same thing. So as soon as I see you put it full screen here, then I'll switch it to the screen up here.
Okay, sounds good. Great, great. Thank you.
You don't have any sound from your computer, right? No,
I don't have any sound.
Okay, cool. Okay, cool. Yeah, cool. What kind of output do you have?
HDMI.
Okay, perfect.
Okay.
Cool.
This works. Thank you.
Cool. So as soon as you put it full screen like that, then I'll switch it up here.
Oh, sorry. You mean?
Yeah, you'll see it here first. So as soon as you put it full screen and I see it's full screen here, then I'll switch it to the
Oh,
main
okay.
screen.
Okay.
You have sound from your computer? No videos or anything like that?
Oh, yeah. No,
Okay.
I won't.
Okay, cool.
Question HDMI. Yeah.
Do you have any sound from your computer?
No.
Videos or
Thanks.
I haven't seen them yet.
So it should be.
You won't see it there. It's just here for now.
Okay,
Yeah.
but
So if you-
why doesn't it?
Are you doing? Is it PowerPoint or no? That's
Just PDF file.
okay.
yeah.
Yeah, go back to where it's mirroring, so it's showing the same thing on both of them. I think that's what you're on now. If you go back to the one that says mirror, I think it was this one here. Cool. Now
Okay.
you can put that full screen. Perfect.
Okay, so that should work.
Yeah.
Okay, thanks.
Yeah, so as soon as you plug it in, well, since you're first, I haven't tested the fourth person, so we might have to unplug yours to test theirs. But
Mhm.
if they don't show up, then we could just leave yours plugged in if you want.
Okay, so we can. I can just leave it like that then.
Yeah, we'll see. If this person shows up to test, then I'll try theirs first. But other than that,
Okay.
we're good to go.
Thanks.
Thank you. Oh, are you the last speaker in the session? Okay, cool. Let's test yours real quick.
Yeah, for sure.
Oop.
So if you want to put, yeah, it's on the other side, I guess. Yep.
There it is.
Seems good.
So after the person in front of you, when they unplug, just plug it back in. Once I see you got it full screen here, then I'll switch it.
Yep.
Up here.
Okay.
So, cool. Good to go.
Thanks. Can I test out the laser? Just one second.
Sure. Yeah.
Seems going. Cool. Thanks, man.
Yep.
Hello. Hey, everyone. We're going to be starting the Parallel and Distributed Learning 2 session in about a minute. So if everyone can take their seats. So I want to make sure I'm saying your name correctly. It's Miguel Carrera Perpignan. Perpignan? Yeah, that's fine. Should I say both? Okay, if everyone could please take their seats, we're going to get started. Cool. So everyone please take your seats. There are a bunch of seats up here. Don't be shy. Okay, so we'll go ahead and get started. So this is the second parallel and distributed learning session. I didn't see all of the first, but I can confidently say it's going to be twice as exciting. So our first speaker is Miguel Carrera Perpignan. He's a professor. Sorry?
Oh, okay, no, it's fine.
Cool. It's up there. Great. So he's a professor in electrical engineering and computer science at UC Merced. Recently, he's been doing a lot of stuff around machine learning and optimization, including around basically optimizing nested functions, which is going to be the focus of the talk today. He's received NSF Career, Google Faculty Awards, Best Student Paper at AI Stats and Interspeech, and we're really excited to hear about his work in the SysML area today.
Thank you very much. Okay, so the topic of this presentation, the contribution, really is going to be the last topic here in this list, this distributed optimization algorithm for nested systems. But before introducing that, I need to introduce some background about what a nested system is and what the method of auxiliary coordinates is and how to use it for a particular case of binary autoencoders. Okay, so I consider a nested system a function that is mathematically nested in the mathematical sense, like this one here. So you have an input x. To this you apply a function f1, to this you apply a function f2, and so on. If you look in machine learning, there are a number of such nested functions all over the place. The most well-known now perhaps are neural nets, obviously where you have multiple layers, one after another doing some computations, but there are actually many other of these nested systems. You have pipelines in object recognition, in computer vision, in phone classification, in speech processing. Also, when you apply PCA to an image and then you apply a classifier to that, that's also a pipeline which involves a nested function. And the idea is that to optimize that, you would like to optimize the parameters of every one of these layers. Okay, so the most straightforward way of doing this, if you have derivatives, is the chain rule. You compute derivatives, partial derivatives for every layer, and then you apply an optimizer to that, and only an optimizer. This works very well and is very widespread for some examples, for some problems, but it isn't always the right thing to do, the best thing to do. It is difficult to parallelize because you have to compute the derivatives layer after layer sequentially, and also, obviously, it requires differentiable layers. Okay, so I'm going to talk about a different way of optimizing this kind of systems, which I introduced a few years ago, which is called the method of auxiliary coordinates. It does not use the chain rule. What it tries to do is reformulate the problem in a way that we have a number of sub-problems that arise, and in doing so, we don't need to use derivatives, and we don't need to, we get a lot of parallelism for free, essentially. It will allow you to train the layers of the system, the nested systems, independently from each other. And the basic idea is the following design pattern. I'm going to explain it first in general, and then I give you an example. So you take your nested problem. This is your objective function that you want to optimize, and it is nested. And what we're going to do is, by introducing in a certain way that depends on the problem, new variables called auxiliary coordinates, we are going to decouple the layers in the nested function and turn the problem into an unnested problem, but constrained, where the constraints are given by these new variables that we introduced. Then after that, what we're going to do is optimize this constraint problem, and we're going to do so using a penalty method, such as the augmented Lagrangian or the quadratic penalty. And then this penalized function, we are going to optimize it finally, and this gives the resulting algorithm using alternative optimization over the original parameters, the ones that we had from the beginning. And I call this the submodels step, because it is going to result in a number of independent small problems that we can train using existing algorithms. And then we have to alternate that with another step over the coordinates, which I call set here. These are the new parameters that we introduce, which we need to optimize over as well. And the solution of this subproblem depends on each case. Okay, so let's look at a simple example, which is the one that we implemented in our experiments here, which is a binary autoencoder. Okay, now in a binary autoencoder, you have the standard reconstruction error objective function here, and you have an encoder H and a decoder F, with the peculiarity that the encoder outputs binary values here. That's why it is a binary autoencoder. The application for this, originally, the motivation was doing binary hashing for fast search in image databases. Okay, so you want to optimize this objective function here. You can notice that there is indeed nesting here, because I have to apply first the encoder to my input to my input X, and then I get some codes there which are binary, and to that I apply the decoder, and then I try to get back the original image, the original input, and I minimize that reconstruction error. Okay, so this problem is difficult to optimize because the binary codes in the middle of the bottleneck layer make the function non-differentiable, and this problem is generally NP-complete. Obviously, we cannot apply the chain rule directly here because the derivatives don't make any sense. Okay, so then let's apply the design pattern that I just mentioned. The first thing that we're going to do is identify the nesting here and break it by introducing some auxiliary coordinates. There is one such auxiliary coordinate per data point. And what it does is introduce a constraint here that captures the output of the first nested function, the first function. So this is the encoder and its output, which is going to be this binary vector of values. We make it a constraint, and we take it out, so that now the problem is this constraint problem, which is equivalent to the one we had before. And now the second step is to optimize this by using a penalty function. Typically, you would use the augmented Lagrangian, but here, for simplicity, I will introduce the quadratic penalty, which what it does is bring these constraints here back into the objective, squared, so that you want to make that as small as possible. And what you're going to do is optimize this this unconstrained penalized function by driving this penalty parameter mu to infinity, little by little. Okay, so then the last step is now to optimize this penalized function. You apply alternative optimization over the original parameters, which are the parameters of your encoder H and your decoder F, and you alternate that with optimizing over the coordinate set. And now, if you look at the form of this, you will realize why all of this, in appearance, complicated procedure makes sense, which is that the original problem here that was nested becomes unnested, and the F decouples from the H, so you can train those independently from each other if you fix the coordinate set, and vice versa. If you fix F and H, then you can train over the coordinates, but separately for each one, for every data point, because it is an additive sum over all the training points. So in that case, the final algorithm looks like this. You have these two steps, the W step and the set step. The W step is the step that really trains parameters. I call them submodels. There is one such submodel per unit, hidden or output unit in the binary autoencoder. We have, for the encoder, it's actually multiple decoders, one per output bit. So we have L of them, and all of these can be trained as a binary classifier each. And then for the decoders, we have one per output dimension, which is D. So we have D different mappings. Each one is a regression. You can train them all also using existing algorithms. Okay, so in this step here, what you can see is that we end up having L plus D submodels, which all of them are independent and they can be trained in parallel. And then you have to alternate that with the step set over the coordinates. There is one per data point. And as I said before, if you look at the objective function, you notice that they are summed here. So optimizing over them is the same as optimizing independently over each one for every data point. And you have to solve this problem in some way. In the case of the binary autoencoder, you can do that easily by enumeration or by alternating optimization itself, coordinate descent, over the bits of each code. Because this is a small vector, you can do that relatively efficiently. Okay, so what you see here then is that indeed, without the need for any derivatives, what we are doing is optimizing this problem, at least approximately, in a way that alternates two steps, both of which have considerable parallelism that did not occur in the original problem. We have introduced that with these coordinates. Okay, the final algorithm here, so that you see what actually gets implemented, looks like this. We're going to iterate, increasing this penalty parameter slowly from small to large. And what we're going to do is, in the W step, which is these two par4 loops here, we're going to train in parallel all these L classifiers, binary classifiers, and all these D linear regressors, which you can do in various ways, for example, with SGD, or you can solve a linear system or whatever. But these are simple problems. And then you are going to alternate that with this other step where you optimize over the coordinates, one per data point, and you have n separate subproblems there that you also have to optimize in a way that I don't have time to describe here, which is not very complicated. Okay, and then you just keep repeating this until you stop. Okay, so I described this method of auxiliary coordinates just for this particular case, but you can apply this much more generally. All that you have to do is recognize in your nested function possible sub-expressions there that you may be interested in eliminating and decoupling the problem. So I will not go into the details of anything like this, just to mention that the final algorithm depends on the problem and on how you introduce these coordinates and on how you optimize these sub-problems. It's a little bit like the EM algorithm. The EM algorithm is not an algorithm, it's a way to generate a specific algorithm for a model. So this method of auxiliary coordinates also is a technique for generating a specific algorithm for a given nested system, and it depends exactly on how you do things. But what you generally can expect with this kind of ideas is that among other advantages, you will be able to handle non-differentiable problems because you will not need to use derivatives, and you will introduce significant parallelism, which is the topic of this presentation and what I'm going to talk about more in detail in a second. Okay, so even if you didn't follow in detail all these manipulations here, all that you have to keep in mind now for the rest of the presentation is that we're going to have, in order to train one of these nested systems, what we're going to have is these two steps that alternate. And in both of the steps, there are problems that are independent and that need to be solved. So we want to implement this now in a large-scale problem where we have a large data set which is stored over P machines, and we assume that each machine contains n divided by P points. So just the fact that the algorithm, the method of auxiliary coordinates, has this inherent parallelism does not mean that it will translate in practice into actual efficient speedups, because there is some communication. And if we are not careful in handling the communication, then we may destroy all the advantages of the algorithm. Okay, so let's keep in mind then that even though the algorithm varies from problem to problem, in the set step, there are always going to be n independent subproblems, one per data point, and these subproblems depend on the current model, the parameters of the model. And then in the W step, there are going to be m independent submodels where m depends on the problem. In the case of the binary autoencoder I described, it is the L encoders and the D decoders. In the case of a neural net, if you implemented this using coordinates at every single layer, every vector of every hidden unit becomes a separate subproblem. One of these submodels. And the submodels depend on the data and the coordinates. Okay, so in order to control the communication in a way that it doesn't obliterate the advantages of the parallelism that we have to be careful because communication is way more costly than computation. So the basic idea in what I call ParMac for parallel Mac is this distributed implementation of this generic algorithm I just mentioned, is that we are never going to communicate any training data or coordinates because those are the ones that take most space. So each machine of the P machines that we have is going to keep a disjoint portion of the data and the coordinates, and what is going to happen is that then the model parameters need to move from machine to machine. We're going to do this assuming a circular topology, which I will show in a second that it essentially implements SGD, but in an implicit way. Okay, so the picture is as follows. It's very simple. So here are 4 machines, and what happens is that each machine contains a subset of the training points. They are here, for example. The first one contains 10 training points and the corresponding auxiliary coordinates here. The second one contains the next 10 points, and so on. And each machine here in the yellow part contains all the model. So all of the submodels that we have, each machine contains them. So what we're going to do now is that we are going to see how, using this structure and assuming this communication topology, which is circular, how do the 2 steps, W and set step, behave? Okay, so the set step is very simple because since the problems are independent and there is no communication between them, then you just go and run. Each machine here is going to run training the set coordinates independently from each other and without communication with any other machine. Okay, so there is no problem there, and this has an enormous parallelism already. The W step is the one that is a little more subtle, because that is the one that does have communication in it. So what happens is that I don't have time to explain this in detail, but the easier way to understand this is assuming a synchronous version of the algorithm, which is not what we implement. We implement it asynchronously. But in the synchronous version, what happens is that the models are going to be moving from machine to machine. So essentially, submodel 1, for example, is going to be trained here for a while, and then it is going to move to this machine, train here for a while, and so on. And this is going to be repeated. And it is going to be done in parallel for all of these submodels, so that the machines are working permanently. What happens is that each machine is working on a different collection of submodels at any given time. So if you look at this from a synchronous point of view, what happens then is that at the beginning, for example, in the first tick of the clock, there are these 3 submodels being trained in the first machine, the next 3 submodels being trained on the second machine, and so on. And when they are done with that, then they're going to send the submodels to the next machine, the successor machine in the topology, and this is what will happen. Then they train again, each one on its own submodels, send to the next one, and so on. And by the time that they have gone all the way to each submodel has visited every single machine, then they are back to the beginning, and we have effectively done one epoch of SGD, because if you think about what is going on here is that the machines the submodels are flying from machine to machine, and every time that they touch one machine, they get trained there directly. And you update the model, then you move to the next one. That's basically a coarse form of SGD. Okay, so we could repeat this for various epochs if we want to. At some point, then the submodel will have visited every single machine, and then we have to do at the very end another epoch, so to speak, of communication only, so that the machines all have the final submodels at the end, which is the situation here. Okay, so just think about the submodels simply moving from machine to machine like that. Okay, so there are other issues interesting issues that we have in the paper, such as convergence, extensions, to load balancing and things like that, and comparison with other topologies, but you can find that in the paper. Here I will just focus on what I described, and also I will mention that we can analyze the theoretical speed up that we would achieve with this PARMAC model. To do that, we compute the runtime as a function of the number of machines, number of data points, number of submodels, and epochs that we do in the W step. The formula for the speed up comes out to be like this, which can be understood in terms of some ratios of computation and communication, which depend on the problem. In the typical case where you have communication dominates computation and you have a large data set, then things simplify in a very nice way, as shown here, which essentially tell you the following. Here is a picture of that. This is the speed up that you have, and this is the ideal speed up that you would like to have, which is perfect speed up, P machines, speed up P. And what happens is that as long as the number of machines is smaller or equal than the number of submodels, then you're going to be in this situation where the speed up is nearly perfect. And past that point, then the speed up continues increasing, peaks with diminishing returns, and then from that point on, it gets worse. Okay, so we would like to be in general in this area here. Okay, so I will tell you now about some experiments that we did on implementing binary autoencoders in a distributed system, which was the UCSD Triton computing cluster here. From there, we used up to 128 processors. You can see the details here about the machines or in the paper. We implemented this using MPI and applied it to various image retrieval data sets, CIFAR and SIFT. The largest one has 100 million images. And the autoencoders are here. They have a number of bits going from 16 to 64 bits. Okay, and then they are either linear or kernel machines. So here is the basic result, which shows you what the speedup was. A few things to notice. Below here, you have the theoretical speedup computed by our model, and above the actual speedup measured for different data sets. And the thing to notice immediately is that the theoretical model matches quite well the experimental results. Another thing to notice is that indeed, if you look closely at the number of machines here and the number of submodels, which is here, then as long as the number of machines is smaller or equal than the number of submodels, indeed the speedup is quite close to perfect. So for example, here it is almost 32 using 32 machines, and here it is for 128 machines, it is 100. And for this case here, which is the one with 100 million points, we could not run it in a single machine to compute the actual speedup, but we predict it to be approximately 128, so that is almost perfect. Okay, so there are more details to speak about here, but suffice it to say that essentially we do achieve the speedup that is predicted by the theoretical model. And in summary, what I have told you about here is that we have a technique called MAC, the method of auxiliary coordinates, which creates parallelism by introducing auxiliary coordinates in a nested system. And then what I have also told you is how to translate this algorithm, which already incorporates considerable parallelism, how to make it actually work in a distributed system by using both data and model parallelism on a circular topology. The parallel speedup that we achieve with large data sets is nearly perfect if we have fewer or equal machines than submodels, and eventually it saturates as you increase the number of machines. And with this, I will conclude. Thank you very much.
Okay, so we'll do about 3 minutes of questions now, and I'd ask that anyone who has a question come up to the mic so it gets captured by the live stream.
Hi, Rick Caillé with Microsoft. Thanks for your talk. I'm sorry, I'm keying in on the last 2 words of your slide, fault tolerance. Can you speak to what are we going to see with fault tolerance from this scheme?
So the idea there is that when you have a large number of machines running for a long time, then sooner or later things are going to break down. And if you want to recover more or less gracefully from there, you will have to do something. So we didn't implement anything of this kind here. It is all a theoretical argument, but given the way the algorithm works and the circular topology, there are various ways that you can correct for when one machine dies. Basically, you can remove it, and you just lose the data for that machine, and what you may have to do a little bit carefully is go back to one of the machines that has one of the older copies of the submodels so that you don't lose that. So the details are a bit complicated, but essentially it is something that I think should be doable. And did you ask just the last 2, did you say? Okay.
Hi, I'm Alex from Google. I'm a little curious, how does this compare in terms of optimization quality, like accuracy and generalization, with just doing a normal continuous relaxation of your problem and using stochastic gradient descent?
So in this case, with the binary autoencoder, you cannot apply stochastic gradient descent because there are...
That's why I said a continuous relaxation of your
problem.
Sorry,
I didn't hear that.
Let Z be any real number between 0 and 1, and then you can do SGD. Then what happens?
True. You can do SGD. So it is hard exactly to know what the answer to that is because it depends on the problem and on how you introduce the coordinates. We haven't done that particular experiment because if you do that, the accuracy that you get with a continuous autoencoder is much worse than the one that you get with a binary autoencoder. But we have done that with other problems, for example, learning features for an SVM. Both the problems there are continuous. And in general, the algorithm is very competitive, particularly, of course, if you can capitalize on parallel optimization. The behavior of this type of algorithms typically is that at the end of the day, it's an alternative optimization. So these kind of algorithms, generally speaking, what they tend to do is that they decrease a lot the training error in the first few iterations, and then they start going more slowly towards convergence.
Okay, I think we have time for one more question if anyone wants to hop up. I have a really simple one. So when you say number of submodels, is that equivalent to the number of layers or the number of latent or intermediate variables Z?
So it depends. It depends on how you introduce the coordinates. In general, if you really wanted to, you could introduce coordinates at every layer, and then basically every hidden unit, every vector of every hidden unit would be one submodel. So every hidden unit, it's an independent subproblem, which is what was happening here. Yeah.
And have you ever experimented with doing it recursively, where you could have more interesting, hierarchical parallelization schemes, or?
What do you mean, recursively?
I mean, you could split, layers recursively.
Yeah, so there are all sorts of things that you can actually do. You can even change the coordinates over time. I mean, during iterations, you can get rid of some coordinates and eliminate them or introduce them. There are lots of variations that can happen. Yeah.
Cool. Well, why don't we thank the speaker, and we'll start the next talk. Okay, so our next speaker is Hyung-Taek Lim, from Google Brain. So he's a research scientist at Google. Previously received his PhD at CMU in 2015, working with David Anderson and others. And he's going to be talking about lightweight and effective traffic compression for distributed ML today. Before, right? System preferences. Let's see if you can force it. Do you have another port that's the same thing? Or is it? What type is it? Is it USB-C or? USB-C.
Okay, thank you for your patience. I'm Hyun-Taek. In this talk, I'm going to talk about 3SC, a lightweight and effective traffic compression scheme for distributed machine learning. This is joint work with David Anderson and Michael Kamsky. So as shown earlier, the parameter server architecture is a well-known approach to train a model using multiple workers. The parameter server has a global model, and the model is replicated over multiple workers, and workers also have data sets. They generate local gradients, and they push the gradients to the parameter servers for aggregation. And the parameter servers uses an optimizer to update the model, and this updated model is put by the workers for the next training iteration. And pushing the gradient and putting the model is done over the network. There's a growing concern of the constrained network bandwidth. So we are seeing more examples of wide area training, such as federated learning, where the upload bandwidth could be as low as 10 megabps. And often the network is metered, meaning as you create more traffic, you have to pay more. Also in data centers, there's an interesting trend in computation power growth and communication bandwidth growth. So if you compare GPUs released between 2014 and 2017, we are seeing up to 25 times increase in the computational power, while the interconnect bandwidth has grown by only up to 15 times. So we are seeing less communication bandwidth for the same amount of communication. So 3AC is one solution to this problem. With 3AC, workers push compressed gradients to the parameter servers, and parameter servers prepares model data, which is the difference between the updated model and the previous model. And workers put compressed model data. So as you can see here, the network only send and receive the compressed data. So using 3AC, we can reduce the traffic by up to 107 times while maintaining similar test accuracy of the trained model. So in the rest of the talk, I'm going to talk about design considerations in making 3AC and talk about the design details of 3AC. And then we'll briefly go about the evaluation results. So first, since we are building a compression method, loss compression method, we have to understand what's the characteristics of the input data, and so we can look at the properties of gradients and the model data we are compressing. People have shown that we can tolerate this input data can tolerate some noise during training. So even if you don't send the exact data, actually you can train high-performance models. And also, it has been noted that this data contains lots of values centered around 0, so there are only a few values that are far from 0. So people have capitalized on these properties by using quantization and sparsification. So quantization uses a few number of bits to represent real numbers, and sparsification chooses a few elements from the input tensor to reduce the data size. The quantization is usually good at reducing the computational void by employing lots of vectorized operation, while sparsification can perform very aggressive compression to reduce the network traffic size, and this leverages distribution of the input data. So now the question is how we can combine the strength of these two methods and avoid their weaknesses. Also, we are seeing many techniques called gradient compression. They are very good at achieving effective compression. And one interesting aspect we can find here is that to achieve good model performance, they often change the machine learning algorithms. So often the optimizer uses a modified momentum calculation, or the momentum calculation is done at the worker side. So here, this scheme works very well, but one question is what happens when the optimizer changes or we have different models. So we might have to devise different compression algorithms for different machine learning algorithms. So how about stepping back and think about some compression algorithms that is effective, even if we don't modify the machine learning algorithms. So 3AC takes the following approach. We compress point-to-point traffic between parameter servers and workers, and we do not add any additional communication rounds or change the existing traffic communication patterns. And we process the per layer tensors and use unmodified machine learning algorithms. And this sounds like very restrictive setting, but actually we can still achieve lightweight and effective loss compression by combining simple transformations and by exploiting synergies between them. The 3AC has three components: three-value quantization with sparsity multiplication, base 3 to 5 encoding, and also 0-1 encoding. Outgoing tensors will go through these three transformations, and data received from the network will take the reverse process. So I'm going to show you the details of these three components. The first transformation is three-value quantization with sparsity multiplication. So this is a very simple quantization scheme. You find the maximum value from the input tensor, and which is denoted as m, and divide the input tensor by m and apply the round function. So very simple. So, and also you can see that the output value of this quantization will be only one of -1, 0, and 1. So this is ternary quantization. And also you can see that the most output values will be 0 because we are compressing gradients and model data where many values were close to 0. Dequantization is even simpler, so we multiply the quantized tensor by m. And there are two things to note here. The first, when we are applying the round function, we use fast deterministic rounding. So we don't use stochastic rounding that were used in recent quantization schemes. But we let the quantization errors occur, and then we accumulate the errors locally and add them to the input data in the next training step so that we can correct the quantization errors over time. So this is a well-known technique called error accumulation. And we found that empirically, error accumulation gives better model performance compared to stochastic rounding without memory. And the second thing to notice is that, as its name implies, we have a new term called sparsity multiplier, which increases the value of M. And this sparsity multiplier has multiple roles, as we'll see soon. So this slide shows the output result of quantization using different sparsity multipliers of 1 and 1.75. You can easily notice that by changing the sparsity multiplier, we are changing M, which determines the threshold of the round function. So as a result, we have different number of zeros and -1 and 1 as the result of the quantization. So in other words, by changing the sparsity multiplier, we can change the sparsity in the quantized tensor. And by changing S, we are also scaling the output value after the quantization. So this has an interesting effect because as we apply aggressive sparsification, we are increasing the number of zeros, and we are actually decreasing the magnitude of the input tensor after the quantization. But by increasing the sparsity multiplier, actually we are recovering some of the magnitude lost by additional sparsification. So once we have three values as the output of the quantization, we actually need to store them in compact storage. A naive encoding scheme would be to use 2 bits per 3 value, but we can do better by using base 3 to the 5 encoding, which is the second transformation step in 3SC. So we take the quantized tensor and then add 1 to make values unsigned, and then partition tensor into 5 equal-sized pieces. And use a simple polynomial expression to combine them into 1. So essentially, we are gathering 3 values and putting them in a single byte, achieving 1.6 bits per value of space consumption. So you can note that well, this is better than using 2 bits per value, and still, we are not using some byte values in this encoding scheme. But the unused byte values are used in the final transformation, which is zero-run encoding. So motivation of this encoding is as follows. So when we look at the data, the output of the base 3 to the 5 encoding, we are seeing many 121s. So 121s are very common because that's the result of having 5 zeros in the quantized tensor. And when you apply base 3 to the 5 encoding, we see many 121s. And this is very common, and it's so common that we have consecutive runs of 121s at this stage. So our idea is to apply a variant of run length encoding. So we find up to 14 121s and express them using a single byte. So when encoding the run length, we use the byte value that was not used in the previous step. So you can achieve up to 200 times the compression ratio if the baseline, the original input data was using flow32 data. And compared to entropy coding and prefix code, this zero-run encoding has performance, the advantages in performance. So there's no bit manipulation, so everything is byte-aligned processing, and there's no table lookups. And in our paper, we discussed how to parallelize this design to encode very large tensors. So with a zero-run encoding, the sparsity multiplier has an additional role. With a default sparsity multiplier of 1, we are already seeing very effective zero-run encoding because the input data's characteristic. But by increasing the sparsity multiplier, we are increasing the number of zeros, and more importantly, after base 3 to the 5 encoding, we are observing longer runs of 121s that can be more effectively encoded by zero-run encoding. So to review the instruction between 3S's techniques, three-value quantization with sparsity multiplication can quantize the tensor using three values so that the base 3 to the 5 encoding can store the value compactly. And the same technique changes the sparsity in the output so that zero-run encoding can reduce the size after applying the size of the data after applying a variant of run length encoding. And base 3 to the 5 encoding can assess the efficient run length encoding by reserving some unused byte values that will be used by zero-run encoding to encode run lengths. So what's the result when we apply 3SE? So in the evaluation, we trained the original 110 for the CFR10 data set. We used a 10 worker GPU cluster, and in this talk, I'm showing two bandwidth settings, 1 gigabps per node and 10 megabps per node. We used the standard momentum optimizer and the hyperparameter settings as the original paper used. But for distributed training, we increased the batch size slightly to 320, and we used the cosine decay without restarts to obtain a good baseline. So this graph shows the total training time and the final test accuracy using 1 gigabps per node. So, so the x-axis is the total training time after the training is done, and the y-axis is the test accuracy, and the top one classification accuracy using the final model. So each line shows different schemes, and each dot on the line is independent runs. So we are not showing the runtime test accuracy, but we are plotting the final result, final runtime and the final test accuracy. So on the left side, we have 3SE shown in blue, and on the right side, we have a baseline using flow32 as the data format for gradient and the model data. So we can say that when using 100% of the standard training steps, 3SE can reduce the training time by 34% compared to the baseline. And what happens when we compare 3SE with other loss compression schemes? So it turned out that actually on 1 gigabps network, there's relatively little difference between compression schemes. So you can say that this can be a surprise, but AP quantization is very good in achieving good time to accuracy. And 1B quantization can reduce the traffic further, but it does not give the best time to accuracy. The reason is that in this setting, the resonant 110 is small enough to avoid communication bandwidth problems once we apply some amount of compression. So the two most important goals here is to have low computational overhead for compression, and also to have good model performance after training. So AP quantization preserves a large amount of information for gradient and model data, and it's also fast to implement. So as a result, AP quantization is very good in this setting. But you can also see that 3SE matches AP quantization's performance, both in terms of runtime performance and the model performance. And what happens when we change the network bandwidth to 10 megabps, which could be a setting for a wide area training? So here, I'm comparing 3SE and the baseline. And 3SE can reduce the training time by up to 23 times compared to the baseline. And let's also compare 3SE with other loss compression schemes. So now we can see more difference between quantization schemes. And as a design reduces the traffic, it can reduce the training time further. So now 1B quantization is the best among the compared schemes, while AP quantization is not as good, so we don't even show that in the graph. But compared to 1B quantization, we achieve a better performance because we actually use less than 1 bit
value, and also we are transmitting more information than one bit quantization for the same for the compressed gradient and the model data. So you can also say that stochastic ternary quantization did not perform very well. So this was a little surprise to us, but it seems that empirically the quantization schemes with quantization and sparsification schemes with memory is better than stochastic rounding without memory. So to summarize, we designed the 3SE for fast distributed training with constrained bandwidth. 3SE can compress the network traffic by up to 107 times and reduce training time by up to 23 times while maintaining similar test accuracy in our experiment. And we did not modify the machine learning algorithms to obtain this result. To achieve lightweight and effective loss compression, 3SE combines three simple transformations and explores synergies between them, effectively unifying quantization and sparsification in a single loss compression scheme. So this concludes my talk, and I'd like to take questions. Thank you for your attention.
Hi, thank you for the talk. I'm Jungwook from IBM. I just wonder how you apply this ternalization to both gradient and the model. When you tried, were there any specific differences? Like, for example, for gradient compression, people use residue to kind of accumulate all the quantization error. But do you do the same thing for the model quantization?
Yeah, in 3SE, everything is the same for gradient and model data. So in terms of the compression method is the same. The only difference is that the parameter servers can compress the model data only once, and the compressed model data can be pulled by the workers multiple times. So that part is the only difference. But if we just focus on the compression part, we do the same error accumulation and quantization and auto transformation. But there's some difference empirically when we compress the gradient and model data. So this shows the compressed size of gradient and model data. So thick red line shows the gradient size, and thin blue lines show the compressed model data size. So there's some difference in the compressed size using the same compression algorithm, but we use the same algorithm for both data. Yeah.
Just one more question. So since your model and the gradients are both quantized, do you use this ternary values for the full backward computation?
I'm sorry. So we don't quantize the model. So we only quantize the communication.
But I guess since you're sending model as a ternary.
So the model is still in using the model data uses full precision, but the model data uses quantized data. So so that's the difference. So we still maintain the weights in full precision.
Okay.
Yeah.
Thank you.
Hi, this is Rudy from Carnegie Mellon. So I have a question. If, like, you use ResNet 110 to do your evaluation, and if I remember correctly, like ResNet 56 can achieve similar accuracy, like 94 on CFAR10. And I'm wondering if you have any like comments on the capacity of the model and your like quantized gradient, how that affects things. So presumably, I think ResNet 110 is more redundant than, like I said, ResNet 56, so that after you quantize the gradient, maybe it's fine. Like, I'm just asking for comments for that.
Yeah, that's an interesting question. So what will be the relationship between the model performance when the models have different architectures? So I think, so for that part, I don't have very concrete answer, but one thing I can say is that ResNet 110 had
very small model size. So there are only 1.7 million parameters. While if you use, for instance, Resident 50 for ImageNet, actually the model size is much larger, even though there are fewer layers. And one interesting effect is that actually we observe more benefits of compressing the communication because we transfer more data for these larger models. And that's the same thing. The same thing applies to non-CNN models. So if we have models with higher communication to computation ratios, then actually we can observe more benefits from the traffic compression. And sometimes we don't have to increase the aggressiveness of compression too much before seeing some benefits of compression. Yeah.
Thank you.
Thanks.
Okay, so sorry, we're going to move on, apologies, to the next talk now to stay on schedule. So this is,
Thank you.
First of all, let's thank the speaker for the talk. So yeah, so next up is Jianyu Wang. He's a PhD student at CMU working with Gauri Joshi in the PDL lab. And he's going to be talking about adaptive communication strategies for achieving best error runtime trade-offs for local update stochastic gradient descent. So we'll give him a second to set up.
Okay. Okay, hello everyone. My name is Jianyu Wang, and I'm going to talk about this work, Adaptive Communication Strategy in Local Update SGD. This is a joint work with my advisor, Professor Gauri Joshi. We are from Carnegie Mellon University Parallel Data Lab. To start with, please let me first do a very, very brief overview of this of this work. As we know, stochastic gradient descent is a backbone of modern machine learning, and especially the backbone of deep learning. And it can efficiently find the minimum of any objective function. And when we run SGD on a single machine, what we care about is the training progress per iterations. And this is so-called error convergence. In the machine learning community, there has been a lot of work to accelerate the error convergence. For example, SGD with momentum, the adaptive method, and variance reduction method. However, nowadays, because we have larger and larger data set and deeper neural networks, so running SGD on a single machine can be prohibitively slow. So there is a critical need to parallelize SGD algorithm onto multiple machines. When it comes to the multiple machines, when it comes to the distributed setting, we not only need to care about the error convergence, but also need to care about the system's throughput. That is the iteration per workload time. And in the practice, what we really care about is actually the training progress per workload time. It's a multiplication of these two factors. And because deep neural network has so many model parameters, and in DNN training, the system's throughput can be the bottleneck. So recently, there are many distributed SGD variants are proposed to increase the system's throughput. But on the other hand, they also hurt the model quality. They will slow down the error convergence. So we can see there is a trade-off between the system throughput and the error convergence because it's an error runtime trade-off. And in this work, we try to propose some method to balance this error runtime trade-off, and we try to maximize the training progress per workload time. And this is a very brief overview of this work. So now I'm going to introduce a basic background of distributed SGD algorithm. Let's first have a look at the execution pipeline of synchronous SGD. Suppose we have total M worker nodes here, and the first step of synchronous SGD is local computation. Each of these worker nodes will locally compute their stochastic gradient with respect to the current model parameters. And these blue arrows denotes the computation time. And then after the gradient computation, we need to average the stochastic gradients across all the worker nodes. So there is a communication step. The red block denotes the communication time. And this communication can be either completed by a parameter solver or reduced operation. And it will cost some time. And the algorithm will repeat the gradient computation and the communication step again and again until convergence. And we can see from this execution pipeline, actually the communication time is nearly occupies half of the time. And if we compare it to the ideal case, where there is no communication at all, we can see in the ideal case, it finished 10 iterations in the given time. But in the practice, because we have the communication overhead, it only finished 6 iterations. So the communication overhead significantly affects the speed up offered by this program. And what makes things worse is that actually in the deep neural network training, because deep neural network has so many parameters, and the communication time can be even longer or multiple times than the computation time. And in some cases, we cannot expect any speed up provided by this parallel program. So to address this issue, previous researchers proposed a very promising solution that is periodic averaging SGD. It allowed different worker nodes to perform tau local steps before the communication. And we refer tau local steps here as a communication period. And this algorithm can be also considered as a special case of federated averaging algorithm. And we can have a look at the execution pipeline again. Instead of having the communication step after every gradient computation step, in periodic averaging SGD, it will allow some local steps. The communication happens after every tau iterations. And in this tau example, tau equals to 3. We can see previously the 6 iterations and there, and now 7th iterations and here. It greatly improves the system throughput. And basically, we will have 2 benefits of using periodic averaging strategy. The number one is communication amount will be directly reduced by tau times. And the second is the variations in computation delay are also evened out. To have a clear view of what is the benefit of periodic averaging, let's have a look at this plot. It shows the runtime distribution of different algorithms. The red histogram corresponds to periodic averaging, tau equals to 10, and the blue histogram denotes corresponds to the synchronous SGD. And basically, we run many iterations and record the runtime per iteration. We can see actually the red histogram is has a much lighter tail than the blue histogram. And the mean runtime nearly achieve a 2 times speed up than the synchronous one. So this is a benefit of using periodic averaging. But on the other hand, we also note a limitation of this method. That is, it may lead to a worse convergence. Let's have a look at this model parameter space. The yellow circle denotes the local model at worker 1, and the green circle denotes the local model at worker 2. If we use a large communication pair, that means these 2 local models will be far from each other. And it's possible that they fall into different local basins. And in that case, we cannot guarantee the average model is better than 2 individual models. And we also have some theoretical support for this statement. Theoretical results tell us that the optimization error at convergence will be bounded by these 2 terms. The blue block is identical to the error of synchronous SGD, and the red block is additional noise because of performing local updates. It's linear to the communication period tau. So, eta is a learning rate, and L is a Lipschitz constant. Sigma square is a gradient variance bound. So it tells us using periodic averaging has a higher optimization error. So to sum up, using a large communication period will help us to increase the system throughput, but it will also give a worse error convergence. So combine these 2 together, what we really care about is the training progress per workout time. There is a trade-off. To have a closer look, that means if we're using a large communication period, it will decay very fast at the beginning, but converge to a high error floor at the end. And on the other hand, if we use a small communication period, it will decay very slowly at the beginning, but converge to a better model at the end. The key observation here is that actually the best communication period varies over time. Before the intersection point of these 2 lines, a larger communication period is more preferable. But after the intersection point, a small communication period is much better. So based on this observation, our goal in this work is to design some adaptive communication strategy, which starts with a large communication period and gradually switch to a smaller one. And our approach is to use theoretical error runtime analysis to decide how to switch between different curves. Okay. Now I'm going to give an overview of our proposed scheme. And for brevity, we will first consider the fixed learning rate case. The first step of our scheme is to divide the training progress into multiple intervals. And T0 here is a time interval length. Maybe it can be several minutes, maybe 10 minutes or 20 minutes. And then, and within each time interval, the communication period is fixed. And then the second step is to estimate the best communication period for each time interval. So for the 0th time interval, we have tau 0, and the first time interval, we have tau 1, and so on and so forth. So now the question is, how can we estimate the best communication period in each time interval? And our approach is to combine the runtime and the convergence analysis. From the theoretical result, we can know the optimization error can be bounded by these 3 terms, and our approach is very simple. We just simply replace the iteration index by the work clock time. So we get the optimization error after time t. It will be bounded by these 3 terms, and if we have a closer look, the first term will be decreased along with the increase of communication period tau, but the last term will increase with increase of along with the increase of communication period. So there is a trade-off. A heuristic choice of the best communication period is to just take a derivative of this upper bound and set it to 0. And we get this adaptive communication strategy. It shows the best communication period after wall clock time capital T. But actually, it's very hard to use this adaptive strategy because there are so many unknown constants. For example, the Lipschitz constant and the sigma square. So we, in order to address this issue, we propose another strategy. Recall that actually we divide the training progress into different time intervals. So for each time interval, we can using this formula. For the first time interval, we can derive this expression, and for the else time interval, we can get this expression. So the only difference between these 2 expressions is the training loss. All other constants are equal. So what we do is very simple, just compute the ratio between these 2 communication periods. So we can see in order to determine the value of else communication period, we just need to know the training loss, and which is very easy to obtain in the training progress. And we also need to know the initial communication period tau 0. And to estimate tau 0, we just do a manually grid search at the very beginning of training. And to have an overview of our proposed scheme, let's have a look at this illustration. In the first time interval, we will estimate the tau 0 via grid search, and we train it for t0 time. And at the t0 time, we use the training loss at t0 and the initial communication period to determine the tau 1, the best communication period as the first time interval. And then we use the training loss at time 2t0 and the initial communication period to determine tau 2, the best communication period as the second time interval, and so on and so forth. We get the training process of adaptive communication strategy. And the updated rule of adaptive communication strategy can be formulated as this. And we can see the communication period will proportional to the square root of training loss. And an interesting observation here is that actually the communication period will gradually decrease along with the training loss. And this matches well with our initial intuition that using a large communication period is much more preferable at the beginning, but a small communication period is much better in the later stage of training. And another important and interesting observation is that actually we can make a connection to the learning rate decay. We have the same trade-off and the same motivation. Recall that actually when we run SGD on one single machine, what we care about is the training loss versus the iterations. And when we use a large learning rate, that means we will decay very fast at the beginning, but converge to a higher error floor at the end. But if we use a small learning rate, it will decay very slow at the beginning and converge to a better model. So based on this trade-off, we design a lot of adaptive learning rate strategies. For example, the stage-wise decay, the exponential decay, ADA-grad ADAM, and a lot of works on this direction. But in this work, because we are focused on the distributed setting, what we are care about is the training loss versus work clock time. And we observe the same trade-off as the learning rate decay case. And the difference is that what we optimize here is the training loss versus work clock time. And the learning rate case is this optimize is the training loss versus the iterations. And we feel that in this direction, there are a lot of work can be done about adaptive communication strategy in the future. And the key insight here is actually decaying communication period is in spirit similar to decaying learning rate. And also, these two schedules can also be combined together. We can, in our adaptive communications strategy, we can also incorporate with adaptive learning rate. And to do so, we just need to rescale the communication period when the learning rate is decayed. And because time is a little bit limited, I cannot tell too much detail here. So now we can have a look at the experimental results. We evaluate our adaptive communication strategy on CVAR-10 and the CVAR-100 dataset with 8 worker machines. Each machine has one Titan X GPU, and we evaluate the algorithm on 2 tasks. The first task is communication intense task. We can observe from this plot as we increase the communication period, the yellow line and the red line decays very fast at the beginning, but it will converge to a very high error floor. And on the right hand side it is a computation intense task, and we can see although we use a large communication period, but it will give a worse convergence. So even at the beginning, it cannot give us any benefit in the training loss versus work time plot. So we can have a look at our adaptive communication strategy. The black line we can achieve a win-win in this training loss versus work time plot. We can decay very fast at the beginning and achieve the same training loss as the synchronous SGD algorithm. And it's also worth to noting that our strategy is we won't monotonically decay the communication period. The communication period will have an increase when we decay the learning rate. We can see from the bottom, we can see how the communication period changes. And this is a comparison of the test accuracy. We can see our adaptive communication strategy achieve nearly the same test accuracy as synchronous SGD, and using a large communication period will hurt the test accuracy. So now I'm going to conclude this talk. First, in this work, we propose an adaptive communication strategy that can work very well in practice. We achieve up to 3 times speed up over synchronous SGD algorithm. And this strategy is conceptually similar to adaptive learning rate. And in adaptive learning rate, we have a lot of we have already a lot of existing works. And in this, when it comes to adaptive communication strategy, we feel a lot of future works can be done. And the similar trade-off, the trade between the error convergence and the runtime can also exist in other distributed SGD variants. For example, in decentralized parallel SGD, instead of controlling the communication period, we can control the connectivity of the worker network. And in synchronous SGD, we can control the number of nodes to wait at each iteration, and a lot of future works can be done in these directions. Okay, that's all. Thanks for your attention. Any questions?
This is Min-Sik from IBM. So I have I want to make sure that I understand everything correctly. So here you're suggesting that in the beginning of a training, we can use, let's say, the large running rate, and then we can have a big, let's say, the intervals between communication.
Yeah.
Is that right? And then in the later stage, we need to do it the other way.
Yes.
But this is a kind of a counterintuitive. For example, if you take a look at Facebook's 2017 paper, they started with a very tiny running rate as like a warm-up phase. And then they stated that that's a crucial technique to make sure that less than 50 can converge in an hour. And then second intuition is that in the beginning, you don't know where you are sitting on in terms of solution space. So you need to be very careful. But in the later stage, already this is kind of a done deal. You are already like deep inside the valley. So no matter what kind of a communication you do, perhaps it doesn't matter. So my intuition is that in the beginning, we need to be very careful in navigating this solution valley. That means that we need to have a very frequent communication. But in the later stage, already you are at the bottom of the solution space. So no matter what you do, it doesn't matter much. So that means that perhaps it is okay to have a very large communication interval. But your explanation is very counterintuitive to my understanding. So do you have any comment on my intuition?
Yes.
If you think I'm wrong, I'd like to get corrected as well.
Okay, thank you for your question. Yes, I would like to share with you my intuition about this problem. Actually, my insight about this is actually in the beginning of training, actually because we are using stochastic gradient design. So at the beginning of training, maybe the gradient is very accurate and the variance of gradient is very small. So at the beginning, a large derivation between local models doesn't matter. But at the end of training, the variance of gradient will dominate, and the gradient we cannot make progress because of the noise in the gradients. And so in that case, we must use a small communication pair to reduce the noise in the stochastic gradient so that we can achieve a better model quality. Yeah. Okay, we can discuss offline about this. Yeah. Okay.
My name is Ashraf. I have a question. So you said you are getting this to speed up in comparison with synchronous HTTP. My question is, how do you compare it with like a simple HTTP? Do you have any comparison with that? Because like in the beginning you said like synchronous HTTP might be even slower than a simple HTTP on a single machine because of the old communication costs and everything. But you don't have any comparison with like a simple HTTP like over here to see like how is the result over here?
Sorry, you mean the comparison to other communication efficient HTTP algorithms?
No, I'm saying like over here you're saying you're getting this speed up in comparison with synchronous HTTP. But in the beginning you said synchronous HTTP might be even slower than like having a simple like HTTP in a single machine because of all the communication costs. But I'm saying, do you have any comparison with your method and like a simple HTTP to see if you're getting any speed up or like over there?
I see. Synchronous HTTP is slower than the serial version in the worst case. Even it's only the case when the network bandwidth is very, very slow. And actually, in practice, synchronous HTTP it will be faster than the serial version. Yeah.
Okay, we could do one more quick question while Jian sets up.
Okay.
Thank you. Jungwook from IBM. I think it's very interesting result. I'm just wondering if the result can be some dependent on some hyperparameter, especially mini batch size.
I don't think so. It's you can assume it's an incremental algorithm of synchronous HTTP. You can keep the batch size as the same as synchronous HTTP. And based on that, we can apply our algorithm.
But can you increase the mini batch size and scale the learning rate in the same way that people do for distributed deep learning?
Yeah, I feel so. We can do that. And based on that, we can implement our algorithm upon that. Yeah.
Okay, thank you.
Okay, great. Let's thank the speaker. And next we have Jian Zhang from Chris Ray's lab at Stanford. He's going to be talking about a new momentum tuner called Yellowfin, which is a fantastic pun if you think about it for a second. And he has the, we'll just get set up and then we should end pretty close to 12:30 on time. We'll save a few minutes for questions.
Yep. Yeah, hi everyone. My name is Jian Zhang. I'm a fourth-year PhD student from Stanford University. And today I'm presenting Yellowfin, an automatic hyperparameter tuning, a tuner for momentum stochastic gradient descent. And this is a joint work with Yannis from Mila, University of Montreal. So in the modern deep learning and machine learning system development, hyperparameter tuning is one of the key procedures to attain strong model performance. However, this procedure can be computationally or labor-intensive. For example, for the recent language representation model BERT from Google or GPT from OpenAI, it can take up to 4 days on 16 TPUs, or 1 month on 8 GPUs to train a single model with a single hyperparameter configuration. Thus, extensively tuning these models can take ages or tens of machines. So among the different type of hyperparameters for machine learning models, one of the hyperparameter for optimizers is usually the key to the strong model performance. The de facto approach to reduce the optimizer tuning labor is using the adaptive optimizers, such as the Adam optimizer. These optimizers typically tune individual learning rates for each variable, and they don't tune the momentum values. However, recently researchers have seen that in many NLP or vision models under hand tuning, momentum stochastic gradient descent with a single learning rate and momentum can actually attain strong or better generalization performance for both synchronous and asynchronous training setting. The natural question to ask here is that can we automatically tune the momentum SGD hyperparameter so that we can achieve a similar performance as hand-tuned momentum SGD, and simultaneously we can enjoy easier hyperparameter tuning? To answer this question, in this work we proposed the yellowfin tuner to automatically tune hyperparameters for momentum SGD. And in this talk, I will show you that the yellowfin tuner can achieve competitive performance to hand-tuned momentum SGD in various types of models in our experiments. And we will also see the yellowfin tuner can achieve up to 3.28x convergence speed up comparing to hand-tuned atom optimizer. And in the asynchronous setting, we will also see we can achieve up to 2.69x speed up than hand-tuned atom optimizer for asynchronous training. So in this presentation, I will first go through the theoretical insights which inspires the design of yellowfin tuner. And after that, based on the theoretical insights, I will demonstrate how we can adapt the theoretical insights to design the tuning rule for momentum stochastic gradient descent. And at the end of the presentation, I will discuss a variant of yellowfin tuner specifically designed for asynchronous training to accelerate convergence. So to get started, I will demonstrate the theoretical insights which inspired the design of yellowfin tuner. And we'll be using a quadratic function as a running example for clarity. And using this example, I will first show you why and when momentum gradient descent can achieve better convergence performance than gradient descent without a momentum. And these theoretical insights will be shed light on how we design the yellowfin tuner. Now let's first look at a one-dimensional quadratic function. It is defined by the curvature h and the optimum point x star. And the curvature h here determines the width of the quadratic function. We would like to apply the standard gradient descent on top of the quadratic function, where we take step towards the negative gradient directions. And the convergence speed of gradient descent on the quadratic function is determined by a quantity called convergence rate, which is jointly determined by the learning rate alpha and the curvature h. At each individual step, the distance towards the optimal point will reduce or contract by a factor of rho. Thus, the smaller the convergence rate is, the faster gradient descent make progresses in the optimization process. Now in this figure, we realize the convergence rate for the one-dimensional quadratic function with different learning rate. We can see in this example, if you are lucky enough, you smartly pick the optimal learning rate, you can achieve the convergence within a single step. However, what would happen if we have a high-dimensional quadratic function, for example, a three-dimensional quadratic function? To understand the behavior of gradient descent on the high-dimensional quadratic function, let's construct a 3D example with different curvatures along the different axes or directions. As shown in the left figure, the curvature is 1 along the blue axis with the slowest changing slope. And the curvature is 4 along the green axis where the slope changes the fastest. In the right figure, we plot out the convergence rate for gradient descent along the 3 different axes on this 3-dimensional quadratic function. We can see with the same learning rate, it will demonstrate different convergence rate along the different directions. So as the overall convergence speed is determined by the slowest converging direction, the overall convergence rate is actually the maximum rate across the convergence rate of the different directions with different curvatures. The drawback here is that the convergence rate along the different directions are very unbalanced. They can never achieve the same value. And the worst or the slowest converging direction becomes the bottleneck. Actually, we found momentum gradient descent can help elevate this problem. In comparison to plain gradient descent, momentum gradient descent consider both the current gradient and the move in the last step. The influence of the last step is controlled by the hyperparameter beta, the momentum value, over the next step we want to make. And in this figure, again, we plot out the convergence rate along the different directions in the three-dimensional quadratic function achieved by momentum gradient descent. We can see that if we properly set the hyperparameter, we can achieve the same optimal convergence rate along the different directions with a different curvature value. Now let's take a comparison between gradient descent and momentum gradient descent. On the left-hand figure, we can see for gradient descent, we can never achieve the same convergence rate along the different directions with the different curvatures. And it is bottlenecked by the slowest converging direction. On the right-hand figure, we plot out the convergence rate for momentum gradient descent, where we can see if we properly set the hyperparameter, we can attain the same convergence rate along all the directions with the different curvatures. This same rate along different axes is important because it balances the convergence speed along the different directions. And if we properly set the learning rate and the momentum, we can achieve better convergence rate than the optimal convergence rate from gradient descent without momentum. Now the question is, under what condition can we achieve this same convergence rate along the different directions? Our analysis shows that we actually need to satisfy the following robustness condition. High level speaking, given the largest curvature and the smallest curvature in the quadratic function, we need to make sure the momentum value is large enough. And we also need to make sure the learning rate is within a specific range so that we can achieve the same convergence rate along different directions. To summarize in one sentence, if we want to achieve this same convergence rate for all the axes with different curvatures, we need to satisfy this robustness condition. And if we properly set the learning rate and the momentum, we would be able to achieve better convergence rate than gradient descent without momentum. So now we have demonstrated our insights on the convergence behavior of momentum gradient descent on quadratic functions. However, in the modern machine learning workloads, we use stochastic gradient descent instead of full batch gradient descent. Thus, in the next, I will demonstrate how we can adapt our theoretical insights to momentum stochastic gradient descent. So the key difference in stochastic gradient descent is that we estimate the gradient with mini-batch data stochastically, which introduce gradient variance. If the robustness condition is satisfied, the expectation of the model parameter will converge with the same convergence rate along different directions. However, the robustness condition only specifies a set of possible learning rate and momentum. Our question is, which specific value should we pick out from this set? And in our design of the yellowfin tuner, assume we are at the T step, and we select the learning rate and the momentum by minimizing the expectation of a squared distance. This squared distance describes how far away you are from the optimal point in the next step. And we choose to minimize the distance in the next step because it can give us an efficient closed-form solution so that we can efficiently update the learning rate and momentum in every iteration during the progress. So to apply the tuning rule to non-quadratic objectives, we can first measure the landscape and construct a local quadratic approximation of the landscape. And then we can tune the single learning rate and momentum at each step based on this local quadratic approximation. To evaluate the performance of the yellowfin tuner, we compare yellowfin tuner to hand-tuned atom optimizer and hand-tuned momentum stochastic gradient descent algorithm. Here we report the speed up in convergence in various different models. So in this table, we can observe yellowfin tuner can automatically achieve competitive or faster convergence than the hand-tuned momentum SGD algorithm or hand-tuned atom algorithms. For example, the yellowfin tuner can achieve up to 3.28x speed up over a hand-tuned atom optimizer in an LSTM model. And in these two exemplar figures, we also visualize the generalization performance attained by each optimizer. If we take a vertical line on these plots, we can see the yellowfin tuner can also achieve competitive or better generalization performance than hand-tuned momentum SGD or hand-tuned atom optimizer. So now we have seen the yellowfin tuner can tune the linear rate and momentum to achieve competitive performance to hand-tuned stochastic gradient descent in our experiments. In the rest of the talk, I will briefly describe how we can adapt the yellowfin for asynchronous training. Here, the yellowfin tuner can naturally fit into the situation because recent research show that asynchronous training need additional tuning for momentum, and the yellowfin tuner can tune the momentum on the fly. So in the conventional distributed training setting, we use synchronous systems where we use a synchronization lock to synchronize the parameters on each workers. And on the other hand, for the asynchronous training setting, the system removed the synchronization lock so that the parameter server and the workers can communicate model parameters or gradient in an asynchronous way without waiting. Thus, this can improve the system throughput of the training system. However, because of the asynchronous communication, the parameter server can update the model parameter with out-of-date gradient values or the stale gradient values. This makes it requiring more iterations to achieve a specific convergence criteria. And recently, research shows that asynchrony in the system induces momentum. And asynchronous training needs more iterations, partially because the mismatch of the desired algorithmic momentum value and the effective total momentum value in the system. Or more concretely, if we explicitly give a algorithmic momentum value to the system, the effective total momentum in the system would be a larger value. And because our yellowfin tuner tunes the linear rate and the momentum without explicitly consider this induced momentum, thus it can slow down the convergence speed of momentum stochastic gradient descent tuned by the yellowfin tuner. And our idea here is that we can automatically compensate for this induced momentum on the fly. So more concretely, we design a closed-form control mechanism for the yellowfin tuner. Specifically, we can measure the total momentum in the system, and we can control the algorithmic momentum as the input to the system. We close this loop with a negative feedback mechanism, and our target is to match the total momentum to the target value desired by the yellowfin tuner. As shown in this example, without the closed loop control mechanism, we can see there's originally a gap between the total momentum in the system and the targeted momentum value. By using the yellowfin tuner with the closed loop control mechanism, we can see it automatically brings down the algorithmic momentum as the input to the system. And quickly, it can match the total effective momentum to the targeted value desired by the basic yellowfin tuner. Indeed, as shown in this example, we can see the yellowfin tuner without the closed loop control mechanism will suffer from slow convergence. However, by adding this closed loop control mechanism, we can observe it significantly accelerates the yellowfin tuner in terms of convergence in the asynchronous training setting. So now, let me conclude the presentation. In this presentation, we discussed the yellowfin and automatic hyperparameter tuning, a tuner for momentum stochastic gradient descent. And to get the design of a yellowfin tuner, we have gone through the theoretical insights which guided our design of the yellowfin tuner. And we demonstrated how we can adapt our theoretical insights to design tuning rules for momentum stochastic gradient descent. And in the last part, we have also discussed a variant of the yellowfin tuner, which can accelerate the asynchronous training. That's all for today's presentation, and I'm happy to take any questions. Thank you.
Okay, so it's almost lunchtime, but I think we should pester Gian with a couple of questions. I think we have maybe three minutes or so. Sure.
Hi, Elmadi from EPFL. I saw that you validate your theoretical insights on CFAR100, so I guess your loss function is non-convex. You're doing some deep learning, right?
Yep.
One problem when you take into account curvature between different workers is that not only you will have state gradients, but you would have different local curvatures at each worker. How did you handle that? The fact that workers are in different parts of the loss function where the local curvature is not the same.
Okay, so basically...
Just before, since people are filtering out, the keynote's at 2 p.m., so everyone mark your calendars for that.
Yep. So basically, we consider a problem in the following way. So let's start from the synchronous setting, where you have a single, copy of the model parameter, and you have a single curvature description of your landscape. And in the asynchronous setting, actually, we consider the model parameters stored in the parameter server. That means actually we still have a single copy of the model parameter in the parameter server, and we actually consider measuring or approximate the landscape considering the model parameter stored in the parameter server. So in that sense, the model parameters there's only one copy. And we measure as usual as in the synchronous setting.
Okay, maybe we can
yeah, we can sync out offline.
Also, for everyone in the back, can you please refrain from talking? The session's still going on. Out of respect for the speaker, thanks.
Hi, my name is Chandan. I'm from Intel. I have one question. So Adam is essentially like a superset of momentum, right? So is there any reason you didn't consider applying this to Adam?
Yeah, so the question is that Adam optimizer also have a momentum hyperparameter. So any of the insights or approach we apply here can be applied to Adam optimizer. Yeah, so basically we have done some experiments on the momentum tuning side of things. For example, for the asynchronous experiments, it is generally true that no matter which optimizer you are using, if you have a momentum term, the total momentum is actually enlarged by the asynchrony in the system. And we have done some experiment that we also grid search the momentum we use as the input to the system for Adam optimizers. We have seen that tuning the momentum there is also relevant to the performance. So I think one of the key points can be applied to Adam is that you also need to carefully tune the momentum for Adam optimizer if you are considering an asynchronous streaming setting. Yeah.
Great. Thank you, John. Let's thank the speaker.
Thanks, Alex.
Okay, we'll wrap up the session now, and it resumes with the keynote at 2 p.m. Thanks. Thanks so much. Great talk.
Okay, let's see. I have a bunch of things here. I have USB-C, which is great. Yeah? Yep. Just plug it in and see if it works. So, and let me check the timing.
I have signed and check-in, or not a check-in, but this morning.
Sorry?
You mean signing?
No, timing.
Ah.
Yeah, so the total time is 22 minutes, but it's 18 for like the actual duration of the talk.
Yep.
And I think this thing will start playing. There's a little timer down there.
Mhm.
Yeah, so whenever it goes up, that's it. You guys gotta, yeah. So then there's gonna be like a few questions.
Sorry,
Yeah.
I needed this.
Yeah, there might be one here, but I can check that. I don't have a laptop with me, but I can check.
Alright,
I can check
this
back with
one
the.
now, I remember this one.
Okay. Okay, we can try it out. Yeah.
I'm wondering whether this guy remembers that I'm in mirror mode.
All right.
Seems.
Okay. Huh?
Yep, seems to
Okay.
remember. Good.
And then is the timer going to run? Yep. So there's the 18 plus 4 or just the 18?
18 plus 4.
Okay,
so
perfect.
8 at the end of 18 for the talk, and then 4 minutes for Q&A.
And then they're going to see that down here, right?
Yep.
Okay, perfect.
Yeah.
All right, so that works.
Timer's at 18 initialized.
Yeah,
or
18 for the
22.
talk.
Total is 22. And that
So the
includes
timer's
Q&A.
initialized for 22.
It'll be 18 and then 4 for Q&A.
Okay,
They're
the
separate.
timer counts on the actual speaker time.
Yeah.
All right. Perfect.
So when are you speaking?
The first.
First one.
Yes.
Okay.
Yes,
Great.
yes. Thank you so much. All right, that works.
Interesting.
Oh, they have.
Do they have the?
Yep. There you go.
Awesome save.
Right, I got the BGM.
I'm too old school.
Yep. There you are.
Just let me make sure.
All right. Oh. Awesome. Make sure to get your little. Oh,
What? Short? Short and sweet? built is just experienced, old school, low level kind of hackers. Don't want you to not know. No, I'm good. I'm on the. No, but you're not on there. Yeah, but they have me. But how did? Okay, so they just need to switch something, right? Yeah, it's him. He can do it. I think they're waiting for you. Oh, are they? Okay. All right, hey everybody. So we have our first guest speaker of the conference. It's a real pleasure to have Ofer Deckel here. He's a principal research manager at Microsoft Research AI. He manages the machine learning and optimization research group and leads the embedded learning library project. He's a world-leading theorist for machine learning, but more recently he's been working on more applied things, and he'll be talking about some of them today. So it's great to have him here. Let's give him a round of applause. Thanks so much. Thank you very much for the invitation. Yeah, so I resisted putting any math or any kind of, my tendency is to jump to the hardcore algorithms and mathy stuff. So it's going to be pretty high level. So I just want to set expectations here. I'm going to tell you a little bit about just the work that we do in our group, kind of the problems that we face, the things that dictate how we think about these types of problems and so on. And I hope hope it's interesting to you guys. AI is everywhere. It's affecting every aspect of our life. And as it becomes more ubiquitous in our lives, there's a strong desire to push it to the edge. I mean, why do we want to push AI to the edge? There are many, many different good reasons to do it. Some of them are listed up here. Bandwidth is a big one. If you look at how many processors and microcontrollers are being deployed into the world, the rate at which these things are being deployed vastly outpaces the rate at which the ingress bandwidth of clouds is growing. So we just can't push all of that data that we're sensing in the world to the clouds. Latency is a huge deal, especially in applications where safety is involved. So for example, here there's an example of maybe a smart bicycle helmet. I don't know if you appreciate my drawings here. But if you need something that has to reply, can't afford that 1 or 2 or 300 millisecond round trip to the cloud, you need to be faster than that. Reliability and availability are big deals. If you go to Costco and you see these smart security cameras for your home, one of the most asked questions is really, but I need to be connected to the cloud for this thing to detect people coming up to my doorstep if it's the UPS delivery guy or someone trying to break in. You only detect people if it's connected to the cloud, right? So if you lose your connection to the cloud, you have no security from these cameras. And if you think about a truck like this one, if it's trying to do some predictive maintenance or any kind of AI on the truck and it's going through the desert or it's going through some dead zone, I don't know if there's 4G or 5G everywhere, so you need to be able to have the AI on the edge. Privacy and compliance are huge reasons to push AI to the edge, right? I mean, think about smart toys. Think about smart buildings where you want to count how many people are in each room, and computer vision is a great way to do that, but you don't want to stream live video from your entire building into the cloud, especially if you want to maybe sense how many people are using each one of the restrooms in the building, right? A smart building, you're going to send a cleaning crew to the restroom that's being used more often. Live streaming live video from each one of the stalls seems like it would be a privacy problem. And you want to do that AI on the edge. Compliance is kind of the legal aspect of privacy. And then the last category that I think about is disconnected devices. So maybe think of an AI like a smart hearing aid that's embedded inside my ear canal. I don't know if that thing is going to even have the power budget to go off and have a 4G or a 5G radio to talk to some other device. So you want everything to happen on board. So these are the good reasons to do AI on the edge. And then we face a bunch of challenges when we do this, right? So many systems people in the room, many experts on these topics, more expertise than me. You want to talk about what happens when there's an unreliable connection to the cloud. Federated and distributed learning is this idea that you want to somehow collect all the information from all of your sensors and learn one big mega model. But then on the other hand, you want to personalize. You want each one of these devices to be able to personalize. There's a warm start problem when new devices enter your ecosystem. Privacy, again, is a big deal. You want to do private inference. You want to do private training. Many, many different challenges, but the one that I'd like to talk to you about today is the one that I've been working on for the past couple of years, which is this idea of compressing the AI model. So a lot of our edge devices are resource-constrained devices, and our big state-of-the-art machine learning models are just too big in various senses of the word big, and we'll talk about that in a minute, to fit on these devices. So I'd like to describe my work and my group's work in this area.
we take one approach. There are various different approaches to solve this problem, so I'll tell you about what we're doing. I'll try to contrast that a little bit with the other approaches. So this is what we'll talk about. So we're building a compiler. So we're building a compiler called L. What is L? L is a cross-compiler for AI pipelines, which is specialized for resource-constrained target platforms. So this is something that takes an AI pipeline. Let's say it's an Onyx file or some description of an AI pipeline. You'll compile it. Typically, I'll do this maybe on my laptop, so not on the target device, which is really low, is a resource-constrained device. But on the other hand, I also don't want to compile it on a big cluster of giant GPUs. So maybe I'll compile it on my laptop, and this will generate some an executable, which executes that model in the target machine code of the target platform. And this is something that I'll deploy onto the target platform and run there, right? So this is kind of the very, very simple schematic of what a compiler does. Click. Just a quick kind of synopsis of the project. We've been working on this for about 3 years at Microsoft Research. It's open source. It's been open source from day one. We started by open sourcing the empty file such that our bosses will never ask us, is it a good idea to open source it? It was just open source from the beginning. This is available right now. In addition to the compiler toolchain, we also offer various tutorials and a gallery of models. The idea being that people will find it very easy to just download this and consume this and use this in their projects and so on. We do have an application focus because we need to demo our work, and we have managers at Microsoft, and just telling them about how wonderful a compiler is isn't enough. They want to see things actually work. So we did have to choose a few key scenarios. However, the compiler is a general purpose compiler. It should be able to do everything. But what we'd like to focus on, or what we've been focusing on the last couple of years, is ARM CPUs. So we're looking at the Cortex-A and Cortex-M family of ARMs, and we want to deploy AI models onto that. We're now moving to embedded GPUs. So for example, on a Raspberry Pi 3, in addition to 4 Cortex-A53 cores, CPU cores, there's also a Broadcom video core GPU on there. And we want to use everything that's available to us. So we're now also starting to adopt embedded GPUs. There's no CUDA. There's no easy way to program these things. We have to build all that for ourselves. The two application domains that we've chosen for ourselves is we're looking at computer vision style problems, ImageNet or detection style problems on the Raspberry Pi 3 and the Raspberry Pi 0. So these are kind of the high end of our resource constrained devices. And then we're also looking at audio keyword detection on Cortex-M devices. So these are the lower power. And we're moving constantly to lower power devices. This is kind of the playing field, right? So on the top end, my supercomputer is a smartphone. We barely touch those. They're too powerful. This is kind of cheating. And if you look at these numbers, this style is maybe 2 years old. So instead of smartphone, this is like a shitty smartphone. This is like an old smartphone. But still, too powerful for us. We don't really work on those. Again, we're doing computer vision on the Raspberry Pis, Pi 3 and Pi 0. And then we're looking at audio keyword detection and smaller kind of models on the other end. And what's really exciting for me, or kind of mind-boggling, is the spectrum of targets or capabilities that I'm trying to address with this compiler, right? So there are 3 orders of magnitude of compute here, and there are 5 orders of magnitude of memory, of RAM. And I want to build a cross-compiler that will be able to deploy the best model onto each one of these platforms, whatever you choose. So this is our little playing field here. This is how our compiler is designed, very, very simplistically. So we have trainers. We can train from data. Typically, we don't do the full backprop deep learning training inside our tool, but we leave that to the other tools, if it's TensorFlow or PyTorch or the other tools, and we'll import from a bunch of different formats. You'll train your model elsewhere, and we'll pull it in to our representation. We have a computation graph representation, basically an IR that we have inside our system, and then there's an optimizer that will do its thing on this internal representation and basically try to squash it down and do whatever it can to get it to run on the resources that we have on the target device. In the beginning, we spent a lot of time writing these kind of assembly level implementations of all of our different neural network AI pipelines for all the different platforms we wanted to support. But recently, we've put in a pretty big effort to build this platform abstraction layer, which kind of sits on top of our layer of emitters. So we can actually write cross-platform assembly, if you will. And then we have a set of emitters that will generate, that will lower this down to actual machine code. We use LLVM a lot. So one thing that our compiler is a front-ended to LLVM. So we'll use the fact that LLVM can generate code or machine code for a variety of different architectures, but we can also bypass LLVM and emit our code in other ways, for example, using OpenCL. And then we have a number of dependencies. So again, we have a soft dependency on LLVM, on OpenCL, on BLAST, and on other libraries. So this is typically what you'd expect from kind of an AI-specific compiler. By the way, there are quite a few nowadays other efforts to compile AI for different reasons. I think we were doing it a little bit before most of these newer efforts were doing it, but I think it's very encouraging to see other people kind of pick up on this idea of building a compiler for AI as a solution. One thing that's special to us is the idea that the compiler not only knows what the model is, so I'm getting this model and I'm compiling a specific model, I'm also compiling it for a specific target. Right? So in addition to knowing the machine language that I need to output this stuff to, I need to also know how to optimize for this platform. And the way we do this is we have this method of generating these profiles that represent each one of the targets that we want to emit our code to. And we do this offline. We basically create a database that represents each one of these targets, and then we give that to the optimizer as a hint and saying, hey, this is what works well and doesn't work well on this specific target, compile according to that. And I'll show you that. We'll talk about that. We'll come back to that in a few slides. So this is our architecture. One question that I thought would be interesting to kind of the systems people in the room is why build a compiler? Right? Most of the efforts to deploy AI in different places are building evaluation engines or AI runtimes, right? So there are Onyx runtimes and other kind of runtimes. Why build a compiler, right? So I think the trade-offs are pretty clear. There are pros and cons to both approaches. If you're a systems person, and certainly in Microsoft, when I talk to my systems friends, and they think about the Internet of Things and artificial intelligence of things, the AIoT, you think about a big ecosystem. You think about a big cloud with many, many, many different IoT devices connected to it. They're heterogeneous. They have different types of hardwares. And you have models that are trained in the cloud, and you want them to kind of move very fluently from the cloud to a device. If a device is replaced by some other kind of hardware, as long as they have something standard like Node.js or some runtime environment, you want it to seamlessly move from one device to another. Somehow models are constantly updating and flowing. And if that's what you're doing, what you really want is an AI runtime. You want something where you're basically sending a description of a model in some very high level form of description, and it just runs wherever it is. This has to do with virtualization, with VMs. And then the compiler approach is much more similar to burning new firmware into a device, right? This is a static thing. You kind of have a model, you spend a lot of time optimizing and compressing it. Now there's a representation on the microcontroller, and you just put it there, right? So I think maybe a smart appliance like a smart fridge or a smart oven. This isn't something where I can immediately think of an ecosystem of models flowing back and forth in the cloud. This is something that maybe I'll want to update the model once a year or once every few months. But really what I care about most is to optimize, is to get as much performance as I can. And that's the advantage of a compiler, right? So the compiler knows what the model is, it knows what the target platform is, and you can spend a ton of time before you deploy the model to optimize and get as much performance as you can, right? So the compiler is going to give you good performance, it's going to give you a small executable. If you have a very small flash budget, for example, because you're only deploying the code that you're actually using for that specific model. If you want that interoperability, if you want to be able to seamlessly migrate from the cloud to the device, you want a runtime. And then maybe the best of both worlds is something like a just-in-time compilation scenario, right? So if you have a just-in-time compiler, maybe you can apply the types of optimizations that a compiler will build with a runtime type of flexibility and approach. But that's not what I'm building. So we're not building a just-in-time compiler, we're building a static compiler. But this is just kind of an interesting trade-off between these two alternatives. So that's kind of one consideration. Here's a pain point. So one thing that we struggle with, there's a ton of research on this, right? There's many, many papers talking about how do we do efficient compression of models, how do we run models on resource-constrained devices. We have three main themes of papers or research themes that people use. So first, we have efficient architectures. This is maybe more in the neural network space, but that's what people like to talk about today. So we have efficient neural architectures. You have a lot of papers saying, if I have this kind of architecture versus that kind of architecture, then I can get a better cost accuracy trade-off. There are lossless acceleration techniques that talk about, hey, whatever model you give me, I know how to implement it without losing anything in terms of accuracy in a more efficient way. And typically people do this with finding mathematical ways to reformulate the problem so that it's more efficient or just better engineering. And then there are the lossy, kind of the more exotic lossy acceleration techniques like quantization, pruning, perhaps early exit, low rank approximation, and so on. So these are the three types of kind of categories that we see. And a pain point is, how do we compare these things? How do we know which combination of these techniques do we want to use, right? I'm trying to build a real system that people will use rather than just publish interesting papers on this topic. How do you do an apples-to-apples comparison? And this brings me to a little kind of gripe, a little criticism that I have for the machine learning community, which I'm a proud member of. This is what a typical paper on accelerating machine learning will look like, right? So you'll have a nice description of what here in this example, I'm talking about lossy compression techniques, but it can also be one of the other categories. So you say, hey, I have this lossy compression technique. Typically, they'll apply it to a very, very big redundant model, what we call a fat model. So rather than applying it to a bare bones model, you apply it to a big model like a VGG or something really, really fat. Usually you'll apply just one technique uniformly to the entire model, which we know is not the right way to go. And then you'll see a sentence like this. So this thing really gets me. It says, bombastic claim with an exclamation point at the end, saying something like, we only lost 1% accuracy and we got a 9x speed up. And the first number is supposed to sound very, very small. We only lost a little bit of accuracy, and we got this massive speed up. And then there's a big exclamation point. And these are sometimes true and sometimes, they're not reproducible. But even when they're reproducible, I don't know what this means. I don't know how to compare. I mean, losing 1% seems like it's a little bit, and 9x faster seems like it's a big speed up. I mean, it sounds okay. I'm kind of convinced. But I don't know, could I get the same thing with trivial approaches? Could I get something with a different approach? How do I even compare these two quantities? And I can tell you, now this is probably maybe my 4th year in a row being an area chair at ICML, and probably 5th time at NeurIPS. And because of my focus on this work, my keywords, kind of all these papers come to me. So if you're active in this field and your paper's rejected, it's probably my fault. But I'm telling you, this is what the papers look like. No one is really going for the more rigorous scientific evaluation of these things. Everyone is claiming 9x, 10x, 30x. You read a paper like this and you say, so what, you're telling me that the rest of us are idiots and you're 30 times better than we are? I mean, it's just not believable. It's really a very low standard of publication. And I think the systems folk and other folks in computer science have a much better way, much more rigorous way of evaluating, and I want to tell you about our efforts to adopt some of those ideas, right? So I think the key difficulty for machine learning people is that for years we've been competing on this one-dimensional competition, right? We've been thinking about just accuracy. So I have my accuracy, someone else comes on the same test set and has another accuracy, and basically we apply the simple argmax function, just to see who the winner is. If my accuracy is better, I win. If your accuracy is better, then you win. So right, it's very, very simple. Just report accuracies on a common benchmark, and let's just apply max. But this problem is inherently a two-dimensional problem. Right? So we have to think about it in 2 dimensions, and there's really no way to linearize it into 1 dimension. And the first step is to agree on what accuracy and what cost really mean, right? So this can be arbitrary. We don't really need to justify this as long as we agree what the playing field is. So for example, in this example, I chose a computer vision task. I told you that we like computer vision. We define accuracy as the ImageNet top 1 test score. It's a perfectly valid thing to measure. And then we also have to agree on what cost is, right? So cost can be measured in terms of wall clock speed, flops, memory, power consumption, model size, which is also a legitimate thing to try to compress. It doesn't really matter as long as we agree, right? So it's well defined. And now the nice thing is that once we agree on these 2 axes, what does cost mean and what does accuracy mean? Every model just becomes a point in this picture, right? I don't care what kind of techniques you apply, if you use this architecture or that architecture, if you compressed it this way or that way, if you did better engineering and just implemented it better, every model has a cost and has an accuracy in a very well-defined way. And as many of you, not from the machine learning community know, how do we extend this notion of argmax? Who's the winner? What's the best model? Well, again, it's not going to be 1 point. This is a 2-dimensional picture, so it's going to be a 2-dimensional kind of analog of argmax, and this is just the Pareto frontier. So we have this frontier of optimality. Everything that's on the top and the left, right, the top left corner is the best place to be. I want to spend the least cost and get the most accuracy. And if you're in this, if you're below the frontier, so every point here, for example, let's take an example, right? Every point like this one, there exists another model that's cheaper and more accurate. And then many of you may wonder why it's not a step function. Pareto frontiers often look like little step functions. Talk to me later, I'll tell you why it's, in this case, it should be convex. This is not a mistake. So now we have our playing field. And let's talk about what people do. So first of all, we have architecture search. So here, we started with the most naive things you could do, right? So we're thinking about convolutional neural networks. Maybe just give it smaller images, right? Reduce the input resolution. Play with the number of layers. Change the number of filters. Use different types of interesting blocks that people have invented. Resonant blocks, bottleneck blocks, densenet blocks. And also, this really nice idea of depth-wise separable model. So just playing and doing an architecture search. And this is how our team functions. So this kind of evaluation, this is the scorecard that we use. Basically, members, if you work on my team, you're not allowed to feel or express any form of happiness unless you have a model that kind of breaks through the line. You really want to push this thing forward. So back in January 2018, this was where our Pareto frontier was. We did architecture search and worked on it, had a little breakthrough in February, March, April. So this is basically how we operate. We only, once we define the two axes, we just push, push, push and try to move the needle. Moving on to lossless acceleration. So we've already done a bunch of architecture search. We already have kind of our current state of the art. We started working on these convolutional models, and the folklore was that, hey, use this thing called Winograd convolution. This is the best and fastest way to implement. We heard this at a bunch of conferences, a bunch of papers on this. And we actually started a very extensive study in our group on convolution techniques. So we basically implemented everything out there in the literature. We also invented a ton of new convolution techniques ourselves. All of these are mathematically equivalent, but have different types of performance. And what we saw is that actually there is no winner. We were looking for the best convolution implementation, and there is no winner. The result really dramatically depends on what your target platform is, what the shapes of the tensors are, the output tensor and the filters, how many filters you have. And then on other factors, for example, if you're relying on a BLAST implementation, which BLAST implementation it is. And we really saw huge variation with 2x, 3x, 4x differences across the different implementations of convolution. And our solution was just choose the best one for each of the convolutions in your model. How do I know which one is the best? Well, this is where our target profiles come in. Right? So we actually have this beforehand evaluation of our platform, which informs us on which convolution implementation to use. Again, lossless acceleration. This is January of this year, and we got a little bit better and better. And by March, we're here. Here you can see that the models are the same. Somehow there's only this lateral movement. You just get faster and faster with the same model. So we did a lot of work on lossless acceleration. Other techniques that we use have to do with cache efficiency, reuse of memory. This is actually where the type of algorithms that you see in systems papers come up again, right? So these are scheduling problems. These are graph coloring problems to determine memory use. If you're trying to schedule in a heterogeneous hardware environment, so maybe I have a Raspberry Pi 3, and this has 4 ARM cores, and it has a GPU. So what part of my workload do I put on that GPU? What part do I put on the cores? Well, if I'm optimizing latency, it's going to come out to be either a shortest path or a dynamic programming kind of solution. If I'm trying to optimize throughput, if rather than just trying to call the neural network once and get the quickest result, I'm trying to feed a stream of video through it, it's a completely different optimization, which looks more like a flow algorithm. And we can go into that. If anyone's interested, I can tell you the details of that work that we did. But this is really similar to some of these scheduling problems that we solve in the cloud and in data centers and when we train and so on. Virtualization, special instructions, these ARM Cortex M4s, for example, some of them don't have floating point units, but they do have other special instructions that you can take advantage of, and you want to be able to pull those things in, and we did all that stuff. Moving on to lossy compression. So this is where it gets interesting. This is actually why I wanted to get into this field, and I started working on it. Lossy compression, the techniques people, so these are like the most sensational papers. Really beautiful math, beautiful algorithms. You can do a ton of machine learning, good research in this space. Type of techniques people use, again, pruning and sparsification. These are techniques that go 20, 30 years back. More recently, low precision mathematics, quantization, binarization was big a couple years ago. Ternarization, as you saw earlier today, is also a big deal. Low rank matrix approximation is something that people use, partial evaluation and early exit. All these techniques really come down to one type of activity that we do a lot of in the team, which is an engineering machine learning code design that I'd like to talk about now. So this is kind of how we approach these problems, and I'd like to do it with a motivating example of these quantization problems. So when you think about quantization, there are a lot of papers about quantization, but really quantization could mean a bunch of different things, right? I mean, how do I understand that I want to have a few bits representing each number. It's going to be kind of discrete, kind of integer-y, but what is the semantics? What's the math that's represented by these bits? So again, binarization is something that was hot a year or so ago. The bit 0 will represent the number -1, and the bit 1 will represent the number 1, and I want to learn neural networks whose weights or activations are all -1s and 1s, but I could also have 0 represent the number 0, so I could also have the weights be 0 or 1. When I have a ternary representation, I add a 0. When I have more bits, what do those bits mean? Is it just an integer? Do they grow linearly? Are these powers of 2 that are represented by these bits? Is there some lookup and I basically have a table and I have, 2 to the k different numbers, but they can be arbitrary floats? There are many, many different solutions. If you count the different options here on the slide, there are maybe 60 different solutions. And I can choose a different representation for my weights and for my activations. So I have something like 60 square different combinations. And for each one of these, basically we'll go through 2 types of activities. One, we'll take the engineering head on and say, assume that my activations are represented with representation A, and my weights are representation B. What's the least number of instructions on this device that I care about to compute a dot product or a matrix multiplication? And we'll really try to squeeze every little bit of performance out of our instruction set that we have. And now that we've done that, we go and we put on our machine learning hat and say, well, I need to also get accuracy, right? So given that representation, how accurate can the models be? And what I want to show you, and this is what's nice about invited talks, is that I can show you negative results. It doesn't all have to be glossy and wonderful. I don't have to be accepted to anything. We're seeing a ton of failure here. So again, this is our Pareto frontier. These are our optimal models. This is what happens when I do binarization. So I'm not saying that the paper on XNOR networks and these other binarized papers are wrong. They just applied it to really, really big, fat, redundant models. When you take bare bones models, when you take models that have already gone through 2.5 or 3 years of optimization by a team like my team, this is what you get. You get some loss in accuracy, and then you get a speed up, but it's, if it would work, you'd get a new point that breaks through your Pareto frontier. Here, we're just seeing basically a failure, and this is after trying to extract the most performance and the best accuracy that we can. Here's another example with ternary weights and 8-bit activations, another one of those, 60 squared combinations that we try to get it to work. Here, it's actually not that bad. You see, the optimization kind of hugs the contour of our Pareto optimal frontier, but doesn't give me anything better than I already had with my architecture search and my lossless compression techniques. So we're still working on this. I'm optimistic. I'm hopeful that we'll be able to compress even more and push this even more with lossy compression, but who knows what'll happen. Right now, it's kind of failing. I don't really have time to tell you about a bunch of other stuff we're doing, because I think we're out of time, but we're working on a bunch of different stuff. I can tell you online if you care. Let me just finish by showing you our little clusters. So one fun thing that we do on our team is, we need to evaluate models on real hardware. And we need clusters, and it's hard to find clusters with these little devices, so we have to build them ourselves. This is our first version of our Raspberry Pi 3 cluster that we built. Now it has about 50 nodes in it. So this is a beautiful professional photograph, but the cluster is kind of hacky. We built this in our little hardware shop. This is our Pi 0 cluster. So we have a little mini cluster of Pi 0s. This is something called a banana Pi. So these has Cortex A7s. And this is just because every time that we come up with a new compilation optimization, we basically have to take our entire backlog of models that we've trained and run it through this compilation and evaluate, run data through it and see how fast it is. So we need clusters. And the last thing is that this, it's kind of made out of acrylic and cables. We recently built a new PCB for this, so we're going to build a more serious cluster. So this kind of Pepto-Bismol colored board is something that we built. These are just Pi zeros, but it's a blade. So this is something that we're going to deploy into our little data centers or into our computer room and have a proper cluster of Pi zeros. So I think that's all I have time for. Thank you very much.
So we can squeeze in one question maybe while our next speaker gets set up. So first person to sprint to the mic can ask a question. No one's running fast. All right, here we go. All right, we got our one question.
Oh, we lost the slide, man. I was going to ask a question about the slide.
Yeah, go for it.
Greg, formerly from Baidu. Yeah, so thanks for presenting that Pareto frontier comparison. I think that's the right way of doing these evaluations. Clarifying question. So one of the things that you're saying that kind of when you're in the accurate part of that, that trade-off, that seemed like it was pretty flat. So most of the things, most of those configuration points, it sounded like what you were saying was that most of them would give you a pretty huge speed up because it's so flat. I had an interesting question, like when you're in that regime, what if there's noise? So what if there's noise in your measurement? How do you know that you're not just picking the noisy outliers on the top and actually getting anything?
So first of all, I don't think that it's flat so much as I think that the x-axis should be shown in log scale. And then it won't look flat, then it'll look like it's supposed to look. So we just care about kind of the very, very, less than 1 second per frame on these Raspberry Pi. So I think it's okay to show it in linear scale. But I think that, if you think about most papers in this area, they're working on very, very big models that on something as small as a Raspberry Pi, it would take, many, many seconds to process just one input. So it flattens out, and then if you were looking at it at log scale, it wouldn't look so flat. And then noise. We're not seeing a lot of noise. So one beautiful thing about working with these Raspberry Pis is that it's a really nice, stable, standard piece of hardware. Not only that, it costs $30 and anyone can do it, right? So I think that if we're not counting flops, but we want to count real wall clock time, having a standard benchmark that anyone can buy off of Amazon.com and it'll run pretty much the same anywhere in the world, I think is really a blessing. So we're seeing actually very little noise, if that's...
So we see little noise, just to clarify, in the performance measurement on something like a Raspberry Pi. I'm also interested in the other side. Is there noise in the test sets, in the accuracy measurement?
Right. So again, I think here the important thing is just to be well defined. Here, the number that we're showing is just take the ImageNet test set, measure top one accuracy. That's a very well defined number. We can argue about whether it's meaningful. But that's a number that if I measure twice, it's exactly the same. There is no measurement because I'm not resampling or doing anything. And then because my background is from learning theory, I can agree with you that maybe it's a bullshit number, right? But at least it's something that we can decide to compete on and see who's doing better.
Okay, so at least if we're using the same test set, we can do apples to apples comparisons.
That's what I think. Yeah.
Okay,
all right, let's thank our speaker again.
Cool. Thank you.
All right, so now we'll switch gears, and this session will be about security and privacy, and we'll start with Georgios Damaskinos, who's coming from EPFL. He's a PhD student there, and he's going to talk about a new system for robust machine learning in the presence of Byzantine nodes.
Hello. So I would like to start with a question. The question is whether distributed learning nowadays is robust against arbitrary worker failures. So if I say yes, some of you might think that this is too good to be true, or even worse, this is another bad joke given today's April Fools. But what I will try to do in the next 20 minutes is convince you that this is not a joke, and we actually take a nice step towards answering yes to this quite challenging problem. And we do that with Aggregator. Aggregator is a new system that does Byzantine machine learning with a technique called robust gradient aggregation. My name is Georgios Damaskinos, and this is a work we did all together at EPFL with Mehdi El-Hamdi, Rashid Geraoui, Arsanis Girgis, and Sebastian Ruold. Mehdi, Arsani, and Sebastian are also here with us today. And let's start. So what is the problem that we are considering in a more concrete way? So we're also working on distributed learning. There was two sessions in the morning that talk about scalability and accelerating learning by employing multiple nodes. So this is one of the main motivations for distributed learning. There is another one that is going to be presented right after me. It's focusing more on the federated learning setup, where these devices, the workers that can be seen as, also mentioned as workers, they might have some decentralized data that is better kept private and local on the device. So what we talk about here is, what if some of these devices that send updates to a centralized server, namely the parameter server architecture, and the centralized server uses these updates to create a new version of the global model and repeat the procedure in an iterative manner. So what if one of these workers undergoes an arbitrary failure? All right, so by arbitrary failure, I would like to borrow the term from the distributed computing field, namely the Byzantine failure. So a Byzantine failure captures the worst case scenario. Here I have some examples of some Byzantine failures. So for example, a worker can have some software bug in the code that is running, or there can be some corrupted data, or even worse, some malicious user adversarially putting some update, or if you want to see it in gradient descent, which is a popular optimization algorithm, it will try to poison through a poisonous gradient the learning. So how would TensorFlow react into some, let's call it, mild form of Byzantine failure? So what we did here is we have 19 workers, and one of them we simply scale the input. So we have a form of corrupted data. And we notice that even with this simple form of failure, learning doesn't work. So here we have a benchmark classification task for CIFAR 10. You have 10 classes. So you can see that even with a single worker having an issue, the learning is kind of critically damaged. And why is this in a high-level description the case? So you have most of the gradients following some true gradient estimation, and then you have this Byzantine node that is pulling your model towards a completely different direction, and this kind of blows out. So why should we care about this? So there has been many recent kind of adversarial failures, let's call them like that, where you have a majority of let's say workers or people who are giving correct, let's say, tweets, and then there are a few Byzantine ones that give Byzantine tweets, and in the case of Tay, which is a chatbot from Microsoft, the chatbot was not able to distinguish among the two, so it got poisoned by the data of the, let's call them not correct workers. So let's define our threat model a bit more carefully. So here we have an assumption about the workers being omniscient in the sense that they can have access to any information. The data of all the other workers, the protocol that the server is using, the exchange information, everything. But of course they cannot be omnipotent in the sense that they can only affect the learning through their response, so they cannot go and change the gradient responses of other workers. And we also have an assumption that the server is non-Byzantine, so the server is trusted. And given this threat model, there has been a recent line of research, which in our paper we kind of classify into two classes. So the first class, we call it weak Byzantine resilient algorithms, and these algorithms, they ensure that learning converges. The second class, we call it strong Byzantine resilience, and it ensures that the learning converges to a state that would be exactly the same as the one that would have been updated if there were no actual Byzantine failures. Now, for practical cases that you don't have very, very strong adversaries with a lot of computing power, the weak Byzantine resilience can be practical, but the strong one gives you more guarantees with an additional cost, of course. So, given this context, there are some important challenges regarding these algorithms. So, what we want really is we want some system support to be able to scale these algorithms into multiple nodes and to be able to compare these algorithms and test new ones, and of course to have some compatibility with tools that we know how to use and will accelerate things. So given these challenges, I would like to present you our proposal here. So Aggregator. Aggregator is a new system that enables scalable Byzantine learning. It's compatible with any application built on top of TensorFlow that uses synchronous stochastic gradient descent. And it employs a component in the networking layer that enables a convergence boost in terms of time that I will talk a bit more in the next part. So let's, this is a high-level overview of Aggregator in a layered manner. So as you can see here, Aggregator is a system built around TensorFlow. So we tried to keep the same APIs, the same low-level and mid-level APIs with TensorFlow. We have compatibility with the library and the ecosystem of TensorFlow. And the gray parts are kind of the main modifications that the main differences that we have with vanilla TensorFlow. So I will talk a bit more about them. So let's first start with the aggregation layer, where this is kind of where all the magic happens and we are able to kind of tolerate these failures. So what is the aggregation layer? The aggregation layer gathers n responses given n workers and gradients, and that's why we have an assumption about using synchronous stochastic gradient descent, and somehow it computes a single gradient that it pushes to the application layer that then employs it to perform the descent operation, create a new version of the model, and so on. So vanilla TensorFlow, by default, employs averaging inside this aggregation layer. So if we wanted to implement the same algorithm as vanilla TensorFlow. So it just simply creates an average of the gradients. So what we do is we introduce a filtering component before the averaging. So this component, we are able to prove that ensures weak Byzantine resilience. And the design goal of this component is to be able to have accelerated convergence comparing to the alternative Byzantine resilience schemes. We have an assumption on the number of workers, total number of workers, namely n, and f, namely the bound on the workers that can be Byzantine. So f is somehow capturing the level of pessimism that we have about our system. So how does the filtering component works in a nutshell? So for each gradient, it creates a neighborhood. So it gathers the n minus f minus 2 gradients, which are closest L2 distance-wise to the gradient, and then it assigns a score. This score is the distance, the L2 distance with these neighbors. And in the final step, it selects the n minus f minus 2 gradients with the smallest scores. So it somehow wants to keep gradients that look close to their neighborhood. So it somehow wants to capture this majority of responses and filter out some outliers if you want to see it like that. I encourage you to check our paper for the proofs for the convergence and how the assumptions are important for ensuring the weak Byzantine resilience. The second part I would like to talk to you about is the loss MPI. We call it loss MPI. It's a new networking option we give as an alternative to gRPC that by default TensorFlow employs. So here, what we have further up in the software stack, we have this aggregation layer that gives us somehow a safety guarantee for our algorithm. So we know that no matter what happens below, we can tolerate up to F faults, up to F arbitrary failures. So we say, why should we fix problems in the network, for example, malformed or delayed packages with TCP that by default TensorFlow employs, and not just push random values up to the application layer, and who knows, maybe it's not so important to solve these values. So this is what we do. We use timeouts, and we replace the missing values with some random ones, and we use UDP for that. And as I will show you in the experimental section, this enables us to have some notable performance boost. So aggregator has more things, and I don't have the time, unfortunately, to talk about them, but there is a lot of more detail in the paper. So we have some patches for TensorFlow runtime that prevent the workers from modifying the graph. This is vital for our algorithms to work properly. We have some automated deployment tools, and we also have a scheme for strong Byzantine resilience that we plug to this filtering component that I described before. So let's see some results. So let me come back to the kind of corrupted data attack that I described in the beginning. So as you can see here, by using aggregator with gRPC and CPUs for CFAR10 using a CovNet, again, 19 workers, one has corrupted data. Aggregator is able to mitigate this attack and converge properly. The second part is an important question, which is, so in general, in distributed computing, fault tolerance and Byzantine fault tolerance is a hard problem. So people are using state machine replication and things that are quite costly. In our case, there are some differences in machine learning that enables us to overcome this issue and actually do it with statistics and have a significantly less overhead. So here, I would like to show you the overhead by evaluating our system in an environment with no actual problem. So all the workers are computing fine, the gradients, and the system is deployed with f equals to 4, which means that we tolerate up to 4 faults. So we are over-pessimistic about our system. So here we have a TensorFlow, vanilla TensorFlow with the blue line. We have accuracy on the y-axis and the time on the x-axis. So we have our baseline, our ideal baseline as TensorFlow. We have aggregator deployed with median, which is an alternative weak Byzantine resilience algorithm, also showing the modularity of our system, the fact that you can plug in your method if it's based on the same principles of aggregating gradients. And we have our filtering component that I described before with aggregator, f equals to 4. And we have the only existing system, the only existing framework that does strong Byzantine resilience, namely Draco, again with f equals to 4. So as you can see here, for a bat size of 20, we have an overhead of 47%, and this is significantly better than the alternatives. And an interesting thing is that when we increase the bat size, this overhead reduces. And the reason behind that is the fact that the aggregation and the communication latency per update do not depend on the batch size, but the computation does depend on the batch size. You have less computations for the back propagation. So therefore, the relative overhead when you increase the batch size decreases. And I would like to show you some results regarding the throughput of our system. So again, the same story. We have the same curves here. We have throughput on the y-axis, which shows the number of updates we can do per second, and the number of workers on the x-axis. So one thing I would like to point out here is something that might appear counterintuitive at the first glance is the fact that this red curve here, which is aggregator with f equals to 4, is above the green curve, which is with f equals to 1. So in a sense, if we are more pessimistic about our system, we are able to have more updates per second, so we are faster. So the catch here is that we are actually not faster. This is not the end metric that we are measuring. We just can process more updates per second. And why is that? It's because our algorithms the filtering component becomes more selective, so it pushes to this averaging box, less gradient, so there is less processing, and the whole thing is faster. So as you can see, though, on the accuracy part, this does not necessarily translate into faster convergence. And in fact, with f equals to 1, we converge faster, which shows that the less gradients you push to the averaging box, the more noise you're going to have, so the slower you're going to converge. And for the last experiment I would like to show you is the performance boost that we can get by exploiting an unreliable communication protocol and viewing problems in the network as a form of Byzantine failure. So here we use the same setup, and we have 19 workers, 11 of them are using gRPC, and 8 are using our lossy MPI protocol that I described before. So there are 8 Byzantine workers, and as you can see, for a 10% drop rate that we artificially injected to our network, we can get up to 6 times faster than TCP-based approach. So with this, I would like to thank you for listening and give you some list of the main points of Aggregator. Namely, we have no constraints on the application, so we are fully compliant with TensorFlow. We have provable guarantees for robust aggregation. We have shown a moderate overhead and significantly better results than the alternative schemes. And we are also able to get a boost by viewing unreliable communication as a form of Byzantine behavior. I encourage you to check our code that is open sourced, and feel free to ask me any questions. Thanks a lot for listening.
We have time for a couple questions.
Hey, Dave Anderson, Carnegie Mellon. Thank you, that was fun. You motivate this in part by the federated setting, but I'm curious there because you may have a situation where there is a correlation between the data available on each worker. And I totally get how your F+2, F+3 works in the uniform setting, but if there are correlations, doesn't it seem like an attacker there exist multiple independent clusters instead of one true cluster, and you're going by the centroid of that true cluster. So if they're already fragmented into multiple clusters, doesn't an attacker get more power in that federated setting?
So this is a very legit question. So in general, we haven't addressed the case of having a non-IID distribution in the worker side. And you're right. So if the distribution has certain properties, then there are some assumptions in our algorithm regarding the variance of the gradients. And these assumptions are connected to the norm of the gradients and the variance of the gradient. So there are some constraints there. So if your distribution is really kind of weird, let's say like that, you're going to have problems, as you pointed out.
Thank you.
Sure.
Any other questions? Yeah.
One question, Vladimir, Google. Let me know if it's the same question, but maybe I'm just using different words to formulate it. Does your threat model assumes that malicious participants can collude?
Yes, it does assume that. As long as you have up to F malicious participants, they can collude and they can monitor everything and so on.
And maybe one more question for me. So I'm wondering, so this was for the setup where you had the parameter server, right? So I'm wondering whether these methods can extend to, let's say, the all reduce setup.
The all reduce. Well, you need a component that is trusted to execute these algorithms. So I'm not sure whether you can do such a thing in a non-centralized fashion. So, but it's an interesting question.
Great. Let's thank Georgios again.
Thanks a lot.
Now Wolfgang Grieskam from Google is going to talk to us about the challenges of deploying federated learning at scale.
I don't know why it doesn't work. So is it a different cable than last time? Here we go. Okay. Thank you for giving me the opportunity to speak here today. I want to talk about federated learning, but probably not in the way you may have heard about it before. So by the way, did you heard about federated learning before? It was mentioned a couple of times. So do you like to raise your hand? Quite a number of people, that's great. The focus today will be less on the theoretical aspects or the algorithms, but actually on the system, by which I mean the SDKs, the tools, and the services which are needed to implement that and actually bring it to production. So that's what I want to talk about, and there are quite a number of people which are part of this work. 3 of them are here today. It's me, Wolfgang, there's Vladimir, and there's Jakub, which are sitting over there. And as I said, quite a few more people which are actually contributed to that work. I would like to start with talking a little bit about what federated learning is, in the sense of what the purpose of it is, not the algorithms or whatever, but why do we do it? And let's start here. So this is kind of like a picture of how people did machine learning for quite a while. I call it traditional server in the loop with centralized logging. What's happening here is that we're collecting via logs examples from phones, from devices which represent training data. We upload that data to the cloud. Then we run training services and create an inference model. But now what we also do, if the user wants to have an inference step in his user experience, then we actually upload the features required for that at the moment of inference to the cloud and resolve them and give the result back. So everything essentially happens in the cloud. That is quite convenient in certain senses for engineering the stuff, because you can actually do everything in your cloud service. You don't have the extra overhead of distributing and deploying code to devices and so on. However, it obviously has some serious problem if it comes to privacy of data. In the last couple of years, what has become more common is to do the following, which is an improvement from the previous diagram. So now we are still uploading data to the cloud. We are doing training in the cloud. We are learning inference models. But then we distribute that inference models to devices and then do the inference locally. This is already better because the features which are required for the inference step never leave the device. It also has an obvious advantage that the device doesn't need to be online in order to do the inference, and that it might be more quicker and more responsive. But it still has the privacy challenges I was talking about. Now, in order to train from representative data, we somehow have to collect this data and then do the training in the cloud. And federated learning essentially is a way to improve on that. And here's how it works. So the user creates data on his device by his interactions with this device, but this data will never leave the device. It will actually stay on the device. And now we are doing on-device training for a batch of this data. And what we upload to the cloud is not longer the original raw data, but what we call a model update, which is essentially a modification of a model which we previously downloaded to the device. So we download that model to the device with the data which is on the device, we improve it, and we upload it. Now, the important thing is we not do that just for one device, but we do that for 100 million devices. So not at the same time indeed, but so those individual model updates which come from the devices are aggregated to build the final global model. From the inference side, it's still the same like before. So the inference model will be constructed from this aggregation of the model updates which come from the devices in the cloud and will then be downloaded to the device. So this is mostly about training, to make it clear. So it's actually interesting that typically if we talk about ML, we do not differentiate that much whether we're actually talking about training or inference. What we are talking about federated learning is just training, not inference. Okay, so what are the potential advantages of this approach? So we have better and more representative data on which we can do training. We can do training on data which is really out of scope to ever upload to the cloud. There is actually lots and lots more data which we consider to be out of scope, to be uploaded. As you might know, GDPR discussions, etc., etc. So we're protecting the privacy of the data, but you can also say we are protecting the ownership of the data. The privacy and ownership are actually things which are quite related to each other. We preserve the locality of data. That means if you have large amounts of data, we don't ever need to upload it. Think about images, think about videos or stuff like this, so which has a high bandwidth impact. So we don't need to do that. So the data stays where it's created and where it belongs to. And last but not least, because the edge devices actually do the training step, they collaborate together with the cloud service. So we kind of put the edge devices to work to help to create these global trained models. There's also a way how you can put that, which I'm hearing more and more in edge computing, which I like very much. It says, bring the code to the data and not the data to the code. Because the second one is what we are doing most of the time today, but it somehow doesn't really make sense if you think about it from multiple dimensions, including privacy, efficiency, bandwidth, and so on. Okay, so that's kind of like a summary of what I want to say about what is federated learning. The remaining talk will be about the system design. As I said, the SDKs, the workflows, and the tools, and the services. And indeed, I can give only an overview here. A lot of the work which we have been doing is still preliminary, so we are applying it actually. In reality, it's ongoing. So, but we wanted to talk about it here to give a dump, essentially, of our state in hope that it's useful for the rest of the community, but it's in no way consolidated. So what I want to say, though, before I come to that, it actually works. No? So there are a couple of papers which are linked from here and also in the paper, and there is a list of links on the end of the stack about applications of the technology or the design which I'm talking here today. Most of them are in the realm of a virtual keyboard, which is very natural for this kind of thing. But there are also other applications on Pixel devices. For example, if you go to your Pixel device today, you go to the settings, you see settings is sorted in a certain way. Actually, federated learning powers this sorting of your possible settings. Okay, from the system design viewpoint, the following need to be said. So this all sounds nice and good, and so, but it's actually not simple. And the reasons for this is manifold. So first of all, the health of user devices. So user devices are not contributing to your training. It must not be compromised. This is kind of a prime directive of this kind of work. Now, if we are going to run some stuff on your phone which trains data, then it should not eat your battery. It should not cost your data if you're on metered network. It should not affect your user experience because your phone is not responsive or something like this. So this is very important. The second thing is user devices can drop out at any moment and at a high rate. That was already mentioned before here today. So like there are various reasons for that. So one reason is the user starts taking up his phone, working with it, then we need to go away. So we need to stop. We cannot continue training. But another reason is also well known. So you're losing your network connection, for example, because you're walking around or anything like this. Related to this, if something goes wrong on the devices, it's really hard to diagnose. No? So like if you run something in the cloud, then we can look at the logs, we can understand, we may be able to reproduce, but those devices, we don't have access to them. Also, there is a large heterogeneity of in particular if it comes to Android, of different versions, different OEMs and so on, so which makes failures possible, which you have never seen on a certain device kind, but now suddenly you see it. So it's hard to get that thing working. And last but not least, large and uneven scale of populations on server side. I think I better come back to that a little bit later because I have an example for this, but that is also a challenge. So developer workflow is very important for us because what you need to see, and I think I said it already, you develop and experiment your model when you do training with federated learning using real users' phones. So you actually experiment inside of a production system. And the model developer expects that he writes his model in TensorFlow as usual, push the button and it's pushed to the device and it just works. No? So, and that's what the developer workflow does. This is one component of the overall system, which you can read up more details about in the paper. What I mostly will focus on is now what we call the federated learning round protocol, because this is essentially the network protocol between devices and the cloud service, which is coordinating federated learning. And indeed, I will not just use this picture, we will go over that step by step, but this is a very good way to get the idea of what technically has to happen and what the various components do. So the federated learning round protocol, like round means, is training rounds. No? So one round from the beginning to the end, updates the global model, and repeat, and so on. And we're looking now at one of those rounds. And it starts with the so-called selection. At any point of time, think about that there are maybe 1,000, maybe 10,000 devices available which are ready for training because they meet the certain conditions, which I was talking about. They are charging, so there's no battery loss. They are on unmetered network, Wi-Fi, and they're idle. They're currently not used. But we don't really need all those devices. Actually, there are some results in McMahon et al. 17 and the original federated, or one of the original federated averaging papers, that if you go over a few hundred, it doesn't really buy you a lot. So out of those thousands of devices, we make a random selection of those that will participate in a round. By the way, we also need to have a certain amount of devices in order for certain encryption algorithms, which I will touch shortly a few slides later. So the next phase, after we have selected a subset of those devices, is to configure them. And what happens, so the server reads the global model out of a database. It is downloaded to those devices, and the devices, together with a set of hyperparameters, and sometimes also together with the actual TensorFlow graph, and the devices start training on that with their local data. And once they are done, they will send it back to the server, and that is the last step of the round protocol, the reporting. When the device is ready, it reports an encrypted model update back to the server. By the way, typically a round on device for one device is like 1 to 5 minutes, but the architecture is able to also work with 20 minutes or 30 minutes, so should that be necessary. So that's about the time how like 5 minutes are currently most of applications a round takes. And those updates, model updates, are aggregated on server side as they arrive. And here's one important aspect in place. So we use what we call secure aggregation, which is essentially a multi-party encryption protocol. So the model updates which are coming from the devices are encrypted and cannot be read by the server before they are decrypted as part of the aggregation process. This is pretty important, even though Google would not use that data, but Google cannot actually use, because of the encryption here in place, the individual model update. The Google services can only see the aggregated final result in which anonymity is guaranteed by the amount of devices which have participated under certain conditions regarding the structure of the model. And the server closes around once it has seen enough reports. All these parameters, by the way, like how long do we wait for the selection, how many devices should be selected, or range of devices, how long do we wait until they report back, how many devices are okay. If you have 100 devices in a round, then maybe 80 are already enough if 80 report back to finalize the round. If you drop under 80, we have to throw the result away. And stuff like this is all configurable via parameters, and it's actually, by the way, quite interesting. We are looking at one possibility is use actually machine learning to tune those multiple parameters of the protocol in an optimal way. I will briefly talk about the device architecture in place here and about the server architecture in the next slide. The device architecture is currently for Android only, but it probably applies to any kind of other phone. So what happens on the device, if you have an application, the application links a library from us, which it uses to collect training examples and store them persistently on the device. Because the training cannot happen at the moment the example is generated, but only, as I said, if the device is in an appropriate state for this. So it needs to be stored locally in the so-called example store. And then the federated learning runtime, which runs in a different process than the application itself, will be waking up every now and then, scheduled by the device when the conditions allow it, and draw data from that example store to do its training around, and talk to the server like I have described in the protocol before. Important is that once we have this job, this periodic job, which does the runtime, does the training running, while it is running, the conditions change, which have enabled it, charging, meter, network idle, and so on. Suddenly, maybe it's not longer idle, then we need to stop, then we need to abort. Okay, so that's happening on device in a nutshell. On the server side, it's a cloud service which consists essentially of multiple instances which are provisioned according to what they actually have to do. Per population, we call a population one federated learning project, so to say. Per population, we have one instance which owns the global state on which this population is training, the so-called coordinator. And the coordinator also configures a number of other instances which are selected, which are called selectors, which are receiving the front-end traffic of these phones and doing the selection. And the coordinator tells the selectors in a distributed protocol how to accept and reject devices. And then there are aggregators which are spawned when a training round is actually initiated, and they're ephemeral, so whereas the coordinator and the selector are long-lived and persistent. I think this is one thing I can take. So one interesting aspect of the overall architecture, there are multiple more like this, it's relatively small, but a nice thing. So I mentioned in the beginning, one challenge is that the population size is very, very much different. And why is that the case? So for some, the first reason is we have diurnal patterns for regions. You'll see this diagram here. At least if you are not working worldwide, it's kind of logical that people don't use their phones, or not that often use their phones in the night, so we have a much higher traffic during that night hours. That's one thing, but the other thing is also there are really different life cycle stages of federated learning application. While you develop, you may have just a couple of dozen devices or so, which are lying around in your lab. While you're dog fooding, you may have 1,000 devices. But when you are now in production, you have 10 million plus devices. And this leads to quite different behavior in this selection and process which I have described before. Solution to that is we call that pace steering. When a device is rejected for a training round, actually the server will tell the device a time window when to check in and try again. And that approach allows the server to actually steer the population. So to get more devices to check in if there is little traffic right now, and to slow down device check-in if there is a lot of traffic. So that's about what I wanted to say. It's really not enough time to talk about all the details, but please take a look at the paper. I mentioned there are a lot of problems open, and they are listed at the end of the paper. I also want to mention that just recently we open sourced a part of the system, basically the Python tools which allow you to build federated learning models. And they are an open source, and you are very welcome to contribute to that stuff. And if there are more questions, come to our poster or try to catch any of the three of us here. Here's a list of the publications which you may also want to check out. Thank you very much.
We have time for a couple of questions. If you have one, please come to the mic. So I have a quick question. When it comes to the models that you're training, what is like the size up to which you're sort of fine on training on device versus, you know, sort of
the
stopping?
size of the models?
Yeah, like in megabytes. Like is it like 100 or is it like?
Yeah. They are much smaller, significantly smaller than what we typically see in the data center. So a couple of megabyte, something like this. I think it's not in if you think about the parameter size, it's not in the order of 10 to the power of 12 or so, but less than that. And this is also, you need to be clear, conceptual limitation of the entire approach. What has happened in asynchronous distributed machine learning is working with parameter vectors which wouldn't fit in the memory of one machine anymore. This is not something which works well with federated learning and synchronous models.
And then in terms of like training the model, is the model trained from scratch on device, or is it already trained to some accuracy and then kind of like fine-tuned on device?
There's quite some iteration happening usually until you find the right model, until you have fine-tuned it. So that's what I had in this developer workflow. And so people trying out for like weeks or so with feedback over metrics and so on until the model is tuned and the hyperparameters are set in the right way. And that may even continue after the thing is shipped. So because the user does never actually see what's happening with training, and inference models are only pushed to devices if they're past our internal manual or human QA, experimentation is possible at any point of time.
Great. So, yeah.
Hi, thanks. Hi, this is Rick Collier with Microsoft. I was just curious, you know, these check-ins that you have every minute or every 5 minutes or so, do you have some idea or do you have some sense of the amount of data that has to come back every cycle or every round?
Yeah, so I'm sorry, but by the way, I'm wearing a hearing aid. I couldn't hear that, but maybe Vladimir or Jakub heard the question. I'm sorry, I'm kind of a little bit hearing impaired.
So I will help answering this one. So just to check in with the server, we just need to exchange literally like few bytes of data, like less than kilobyte. It's just HTTP handshake and so on. So in the case if device is rejected and not participating, it's also just a few bytes to tell when to come back. But if a device is participating in a round, we need to send basically a set of parameters, and that might be up to a few megabytes.
And then one more short question.
Have you considered allowing the framework to run over multiple populations for cases where you know you have certain biases and may be able to control for them?
Yeah, so thank you for this question. So this is actually a very important question, and feel free to join our poster session to discuss about this. So fighting bias is one of the open area where Google and a lot of partners and other institutions are working on that. And fundamentally, the system we're talking about is multi-tenant. So yes, it's designed to work with multiple populations, and there are multiple ways how both models and the system parameters can be tuned to compensate over different kinds of biases. So.
And let's thank Wolfgang again. Thanks. And now Lei from the University of Texas in Austin, who's a PhD student, is going to talk to us about how you can design discrete-based attacks for text classification problems using submodular optimization.
Thanks. Hi, I'm Lei from UT Austin, and I'm going to talk about discrete adversarial attacks and submodular optimization, and I will focus on its application to task classification. And this is joint work with Lingfei, Pingyu, and Michael, who are from IBM Research, and my advisors, Alex and Inderjit. So we know that deep learning methods have been proven very successful in many different domains. However, one problem of it is their vulnerability to adversarial attacks. So many of you must have seen similar images. Like this left image is an original input that is classified correctly as a sports car. However, by adding some small attacking noise, it is then labeled by this silly deep learning model as a toaster. And this reflects our definition of adversarial examples, which are instances with small intentional feature perturbations to make models predict incorrectly. So this phenomenon not only applies for continuous data, but also for discrete data. Take this as an example. This is a year preview about a pet shop called Scooby-Doo's. And our task is to do sentiment analysis to tell if this is positive or negative. And we can tell that from we both love Scooby-Doo's language like that, this is very positive. And the model can predict it pretty well as 100% positive. However, by conducting our adversarial attack, we can completely flip the prediction to 100% negative by simply paraphrase that one sentence from like the pricing is also cheaper than some of the big name conglomerates out there to the price is cheaper than some of the big names below. So they are basically same meanings and seems irrelevant to the topic. However, the model's prediction is completely wrong. So this also reflects the small feature perturbations we talked about. And we say that this small concept for text domain should be a human should not be able to detect if the text has been manipulated or not. And in this talk, I will actually focus on general framework of generating adversarial examples with discrete data. So apart from the document I just mentioned, it can also apply for code where we want to attack malware detection and to URL so that we want to confuse those malicious website checkers. So now let's look at how we can actually generate the adversarial attacks. So firstly, we want to find out some possible candidates to replace the words so that it meets our requirement of small feature perturbations. And we use some similar method proposed by Kuleshov, a recent work, that we can generate some candidates for each word based on their semantic and syntactic distance. Specifically, take this sentence as an example. We look at each word and we generate synonyms for all of them. But some of them may not fit in the context, and we use a language model to filter out those words. So now, for each word, we may have several possible candidates that meet our requirement of small feature perturbations. Now we want to make the model predict incorrectly. How do we do that? We want to find a combination of them. And in order to do that, we give each combination an index to represent it. So we use a vector of the same length as the input document. And here, like this 0 means for the first word, we keep it unchanged. And like this 1, it means that for the fourth word, we replace it as the first candidate. So each indexing represents a unique transformation. So now with this kind of tool, we are able to do a target attack. We can write this target attack. Let's talk about notation. So X is the input document, and TL is the word paraphrasing indexed by this L we just mentioned. And this V is the embedding that takes those discrete data to a numerical vector so that we can actually optimize on. And the C is the classifier that outputs the target label's probability. So if we want to do a target attack, we are actually trying to find this label we defined that will find the best transformation labeled by this L. That make the probability of the output probability the highest with at most m word replacement. Or otherwise, we can also write this formulation as a set function. Now this set is actually the support for this label L, which means which words we are trying to replace. So now our problem is formulated as a maximization over a set function under the constraint of under the cardinality constraint. With this form, we are able to derive some theoretical results. The first one is the problem we just mentioned is actually NP-hard. So even for some convex classifier, we can find some instances that this problem can be polynomially reduced to subset sum problem, and is hence NP-hard. And secondly, this kind of formulation to maximize a set function over a cardinality constraint remind us of this famous fact that the problem of maximizing a monotone submodular function subject to a cardinality constraint actually gave us a pretty good approximation with greedy method. And we can show that for any kind of classifier, our target function is monotone non-decreasing. So now the problem is, do there exist some non-trivial neural networks that yield some modular functions? And actually, we have found several of them. The first one is called word level CNN. This is a quite popular classifier to deal with document. And this architecture is just, we take the input document embedding to go over the convolution layer with different filters. And then we take a max over time pooling and followed by a fully connected layer. And we show that with this architecture, if the convolutional windows have no overlap, and if the final layer's weights are non-negative, then the function we defined is submodular, which means a greedy method can find 1 minus 1 over E approximation. And the second example is recurrent neural network. We know that RNN and its variants like LSTM and GRU are very popular to be used for text classification. And here we find that an RNN with arbitrary T time steps, but with single hidden nodes in each layer, and if the activation is non-decreasing concave, this function f is submodular. So apart from those theoretical results, we also want to design some attacking algorithm that is both efficient and effective. We want to do so because greedy methods are effective, but can also be very slow because it replaces one word at a time. And if we have a white box attacks and we have the gradient information, we want to use this gradient to further accelerate the greedy search. And that's what we do. We use the gradient information to guide the greedy search. Take this sentence as an example. For each time, we will look at the top 3 words with the highest gradient magnitude. And we think these words are the most important ones. And then we look at the possible replacements among those words and take the one combination that will maximize the output probability the most. And so that we can replace 3 words at a time. By only looking at these 3 words, we don't even need to look at the other words replacements. So this should be more efficient. And we verify this point by conducting some experiments. We compared these 2 recent work. The first one by Kuleshov. This is kind of the object-guided greedy because it's the greedy method that doesn't look at gradient. And the second one is actually the gradient method. It simply uses gradient to find which word to replace. And the gradient methods are like effective but slower, and the gradient methods are the opposite. And we want to show that our method can take the advantages of both of them. We use an word level CNN we mentioned before to do the attack on 3 different tasks. The first one is we try to detect if a news is fake or real. And we compare with these 2 methods, and we show the attack success rate and the time cost for all 3 methods. And we can see that our methods are able to flip slightly more samples, and using only like 1/6 of the time cost as greedy method. And the second example dataset we use is for spam filtering. And again, we are able to attack more samples with relatively low time cost. And the third one is the sentiment analysis for Yelp reviews. And again, similar result yield. To verify that our definition of like small perturbation by using small semantic and syntactic distances makes sense, we also do a human evaluation. We ask 5 people to randomly evaluate 60 tasks for each task. And this one is about human prediction accuracy. And we show that on both the emails and the YIP reviews, before or after adversarial attacks, human evaluations, human predictions have similar accuracy. And the second one is we asked people to evaluate on a scale of 1 to 5 how likely the text is human written. And again, you can see on all 3 data sets, before or after adversarial attacks, they show similar results. So to conclude, that on the theoretical part, we proved that to generate the best adversarial example is NP hard. And we also show some, find some non-trivial NLP classifiers that yield some modular set functions. This justifies greedy attack. And on the practical side, we propose a gradient-guided grading method, which has been proven both efficient and effective among some prior work on 3 different data sets. And we also use human evaluation to verify the threat model. And although not mentioned in this talk, we also use sentence paraphrasing to expand the space of attacks. And we also use adversarial training to show that we are able to improve the adversarial robustness of our model by the examples we generate. So if you are interested, please refer to our paper for it. Yeah, that's it. Then do you have questions?
All right, we have plenty of time for 2-3 questions. So I'm wondering, like, if you were to kind of like compute the running time of the algorithm as a function of the size of the state space or the sort of the word space, like how does it scale with the the size of the search space that you have, the number of words and the number of alternatives?
So like it should scale linearly to the space of to the like dimension of the input document. Yeah, because we need to loop over all the words. Yeah.
Hi, I'm Yisakal Ackerman, Bloomberg LP. I noticed in your talk that you've found certain classes of networks that make them vulnerable to your attacks. I'm wondering if your theoretical results could be applied the other way, of saying there's certain properties a network would have that would make your optimization problem untractable, and in which case would make them resistant to these types of attacks.
Are you asking if there are other neural networks that should also be vulnerable, or like what kind of property we can find to
I'm
make?
asking what type of property you could find to make them not vulnerable, to make it that we could have some more guarantees of securities versus these types of attacks of algorithms.
Yeah, so what I can think about is like if the model has more randomness, and it's harder to be attacked. And there are some many other work that says that if the model has good Lipschitz bound, and it's hard to be attacked. But in our work, it's like orthogonal to those results.
Thank you.
We can talk offline about some other properties, maybe. Yeah.
Thank you.
Thank you.
All right, let's thank Chi again. And now for our last talk in the session, Yiren Zhao from the University of Cambridge is going to tell us a little bit about what happens when you both want to be robust against adversarial examples, but you also want to compress and quantize your model.
think so.
So maybe do the mirror the screens.
Oh, it's that side. Yeah. Hello everyone, my name is Aaron. I'm from the University of Cambridge. I share equal contribution with my course Ilya in this piece of work. Until a week ago, it should have been Ilya to come here to present the talk, but apparently he cannot get his American visa. So I'm somehow happy to be here to present our work. This is a piece of empirical work looking at the interactions between adversarial attacks and neural network compression. In this talk, I will divide it into two parts. In the first part, I will show the empirical results we have. In the second part, I'm going to introduce you a defense that we developed, which is inspired by this piece of work. I hope at the end of this talk, I can persuade you that neural network compression will make adversarial attacks easier. So what's happening today is we have over 1 billion devices, and many of them have great compute and memory resources on them. So, for example, your smartphone, right? It's in both in my pocket and probably in your pocket. So, many of them are currently or will be soon running some machine learning workload. For that, we mean they will run some form of compressed neural networks. In terms of regulations here, we have some safety guarantees on those devices because your phone does not blow up easily. But in terms of security, there's pretty little or no security on them. What happens with machine learning now is machine learning is everywhere. And in machine learning, we operate based on data. If your classifier is not showing the correct accuracy, what do is we sometimes fix the neural network itself, or most likely you pump it with more data if you have the data. Then that means we're introducing a lot of noise or non-determinism into this system. Then it is really hard now to define security. So why we think adversarial attacks are possible? Our simple view is that first, your data set is very questionable. If we look at even this toy data set, the very popular MNIST data set, we have those images in our data set. To be honest, as a human, I cannot tell what numbers they are. And a lot of time also, when you're training the models, what happens is you pick your favorite checkpoint, and also you pick your favorite neural network architecture, and a lot of time our model is actually overfitting our data. So this gives the chance of adversarial samples. What do we mean by adversarial sample? Is the samples that generated from the original image and with some handcrafted noise, and now I can still tell it's a rabbit, but apparently my neural network will tell it's something else. And it suddenly opens the whole taxonomy of attackers here. We can generate samples that are, we can generate adversarial images that are pretty easy to do by using attack that's probably single-step attack. It's probably very portable in real life, but the perturbation you generated is pretty large. And also, sometimes if you apply iterative attacks, in this case, you get very small perturbation that human can hardly tell. So what's more important is that we realized those adversarials, if the adversarial samples generated can be successfully fully used on the second classifier, that pretty much means those two classifiers share similar feature space, or at least they operate on similar feature spaces. And one thing, sorry, I forgot to mention that there's also another type of attack we call reprogramming, is where the attacker plays a constant noise onto your data set, and then suddenly the whole classifier is doing something else. For example, the classifier used to be applied to recognize road signs, and I reprogrammed my neural network using adversarial samples. Now it's recognizing rabbits. Well, surely there are security concerns behind those things. And many of us will think, since I mentioned we have over 1 billion devices, surely those networks are diverse. And we have to realize that most of the time when we run models into those devices, we run slimmed down versions of them. Because the performance is a critical issue on those devices. What do we mean by compression in this case? We mean quantization. We mean quantization is to change your number representation to something simpler so that you execute in a nicer data format, for example, fixed point or even powers of 2 weights. And also pruning means we take off some unimportant connections in your neural network and then you retrain them. And also you can do low rank approximation using singular value decomposition. And also to some extreme case, people do binary and ternary weights to further save the memory and compute requirements. So what happens in real life is most of those compressed neural networks have the same ancestor model, that's what we call, or you can understand as the baseline model. And why this happens is first, data costs money, of course, and also labeling data is pretty expensive. And surely, what you do not want to do is to partition your data for different classifiers because that directly decreases the performance of those classifiers. And this raises a question for us. If you have the networks that share the same ancestor model, are they still attackable? This is the first question. And the second question we're trying to answer is, how do those adversarial samples survive from compression processes? So we consider the 2 attack scenarios in this case. In the first case, we generate adversarial samples from the ancestor model, or we call the baseline model, and then we use those adversarial samples on different compressed neural networks. And what we also do is we generate adversarial samples from different compressed models and then apply them on the baseline model. Our intuition is that if those 2 attack scenarios hold true, what that means is from an arbitrarily compressed neural network, I can now generate adversarial samples that can be successfully transferable to the networks that have the same heritage. And we generated all these compressed networks using the tool Mail we've developed. This is a tool that can help you to generate help to chain up different compression methods. And why we think this problem is important, taking like a very simple example, is if there's a CCTV camera company and they produce 2 lines of products, one's bank camera and one's cameras that's for your cats, right? And of course, like attacker might find it easy to access to a home use camera that's watching your cats. And if the CCTV camera company is using the same set of ancestor model for those 2 different cameras, and surely the adversarial sample now generated from the home use camera can successfully transfer to the bank camera. And this is a very serious security threat there. So in this case, I'm showing you some results when we apply fine-grained pruning. And fine-grained pruning is a method that takes off unimportant connections in your neural network. And it will save bandwidth and also save compute if you have a sparse matrix accelerator somewhere on your device. What we observe is we have marginal protection, meaning that the accuracy increases a bit at the preferred density. What do we mean by the preferred density is the density that your classification accuracy just starts to decay. So that's the smallest density where you can still have the acceptable, still maintain the classification accuracy there. And of course, in the red line, we see it increases because when at near 0 density, our classifier is generating garbage outputs. And if you generate adversarial sample based on those garbage outputs, surely those adversarial samples will not transfer to the baseline model. Then when you look at fixed point quantization, what we observe is literally a flat line. That means all the attacks are transferable at high precision. But we observe like a marginal increase in the accuracy when we found like when we use a bit width of 4. But when at the bit width of 4, we're decreasing the integer bit width. Effectively, what happens on your activation is those activations are clipped because now they have a very restricted numerical range. I will elaborate on that a bit later. Then, what we think really interesting is if we consider a different baseline as a model that has been trained twice with different initializations if we consider attack that's not even that transferable, which is a deep fault attack in this case. Under the net5 model, we show a changing accuracy of 93%. What does that mean is we get the accuracy on the source model where we generated the adversarial sample from, and then use that adversarial sample to be evaluated on the target model. And then this is the difference in this accuracy. And surely this attack itself is not that transferable, but it shows great transferability when we consider a baseline to both pruned and quantized model. What that means is, apparently, you may ask, how do you get the pruned and quantized models? Well, I'm telling you, we used fine-tuning. So basically, we take the model and then retrain it. And apparently, the feature space in our intuition is that it maintains to be as the same feature space. So the takeaways here is that transferability survives when the compression during the compression process, both in terms of pruning and quantization. And we observe something interesting is the clipping of your activation. When your activation clips, it turns out that we have a marginal protection. In our intuition, what happens is that most of the attacks are trying to drive some activations to some unwanted states. And if now your activations can saturate to certain value, the attack will have less chance to boost certain activations to really large value so that it can basically dominate the feature space. So then we're thinking of whether we can develop a defense based on this observed behavior. So let's take a step back and look at what does existing defense do. And we have some popular methods like adversarial training. In this case, you have lots of ray training, and you have to have some prior knowledge of your attackers. In the second case, people are working on detecting adversarial samples. Works like magnet and safety net use external classifiers on top of the existing CNN so that they can decide whether the incoming sample is adversarial or not. But on constrained devices, none of these methods really work that well because you don't really want to add additional classifier that's probably very large, or you don't want to make substantial change to your neural network architecture. So here we present the solution we had. We call this a taboo trap. What a taboo means is a hidden command that only the receiver and the sender knows. And if it is, so a give example is like you teach your kid good manner, and one day your kid suddenly start to swear to you on the dining table. You know this must come from really bad influence, also known as the attacker. So in this case, we train our neural network to behave in a certain way by avoiding certain activation range. And if we found, if a sample count and our activation falls into that range, we know this is the attacker. And this becomes really interesting because now we can use different combinations of range on different locations of your activation. Essentially, we're introducing a crypto key here. So just like as you imagine, if we have a key, we can perform many cool things. And this is just an example showing on the heat map. We're designing this restriction on activation values based on polynomial functions. And apparently different coefficients now on this second order polynomial can become your keys. What we're showing here is when two keys are very similar, the adversarial samples are transferable. But if the two keys are very different, the adversarial samples can be less transferable. So it is now a matter for you to choose the right key. And also what's interesting as in security is if we have keys now, we can do keys attribution. Meaning that if we have certain classes of devices and each of them have different key, and if I know this certain class of device has been broken down, by gathering the key and also the adversarial sample, I know exactly which is the class of devices that has been broken down. So then the vendor can issue a patch to those devices or just recall them. So this is the end of my talk. Thanks for listening.
Hi, Nicholas Carlini, Google.
Hello.
So talking about the last couple slides, you mentioned that you can use keys in this way.
Right.
So first of all, detection is actually very hard. Most people who have tried to detect have failed. Magnet and safety net don't work. Going to your question, when you have keys, how do you make sure that I can't extract the key by querying your model?
Sorry, are you talking, what do you mean by extract?
So you said like you have keys in these networks, like crypto keys?
Yeah.
When we design crypto systems, we make sure that even if I can have you do like a chosen plain text, that the key is safe.
Yeah.
How do you make sure the key is safe in this setting?
Currently, we don't have a solution. What we do right now is we just show there's a possibility of inputting a key there.
Okay.
Right.
Do you have any other questions? So I have one last question. So if, with respect to the question of transferability, if you use one of those techniques that retrain the model once you quantize, like decompression, for example, but instead of like training with mini but stochastic gradient, you were doing like robust adversarial training, where you were training on adversarial examples, do you still see that sort of transferability?
We tried that. It's not in our paper, but we tried that offline. We see some protection. But what do you mean is, do you put all the, but we didn't try to use adversarial training to include the quantized model in the line. We just tried that with the baseline model. Then in that case, it's still transferable. But I guess what you say could be something to be tried as well.
Well, any other questions? Well, before we enjoy the break, let's thank all the speakers in this session.
Thanks.
Just checking. Like 1,000 adapters, but it's HDMI.
biases. All right, let's get started. Session 4, video analytics. Ding, ding, ding. You need like the, where's my thing? All right, so everyone, this is the video analytics section. Hi everyone, I'm Vivian C. I'm a faculty member at MIT, so I'll be your session chair. So most of the talks in this session focus about how do you efficiently process visual data. Starting out, we have Christopher Cannell, who is a third-year PhD student at Carnegie Mellon, where he works on high-performance distributed systems. Chris, take it away.
Hi, everybody. Thank you for coming. I'm sorry that I brought the wonderful Pittsburgh weather to sunny California. Today, I'm going to be talking about scaling video analytics on constrained edge nodes. This is joint work with a number of my colleagues, as well as my advisors, Dave Anderson and Michael Kaminsky. As you all know, in this day and age, cameras are proliferating in smart cities. Technological advancements and economies of scale have made camera deployments ubiquitous. The point of all this observation of the world is so that computers, not people, can reason about the world. Because of the research that people like all of us are doing, the number and diversity of applications processing this data is exploding, from things like traffic analytics to customer tracking and more. My talk today is about our investigation into how to handle this explosion of video data at the edge. In this talk, I'm going to first discuss some constraints and challenges that we have encountered in our practical experience with camera deployments. We've actually worked on one of these things around Carnegie Mellon. Then, I'm going to introduce a new edge-to-cloud system called Filter Forward that addresses these challenges by enabling application-specific video filtering on the edge. And finally, I'm going to discuss a new flavor of cheap but accurate neural network filter that we call microclassifiers, which are the building blocks of the Filter Forward system. In this work, we are considering a type of deployment architecture that consists of large numbers of streaming cameras, always on, connected to some kind of local compute edge node. This edge node has a low bandwidth connection back to the data center. Complex analytics applications, bulk analytics, are running in the data center on GPUs or custom hardware accelerators. The fundamental problem here is that as the number and resolution of these cameras increases, we're generating way too much data. We can't offload all the data to the cloud for processing, where our big compute is. So we need some way to save bandwidth. And let's start by looking at a couple of straw man ideas on simple ways that we could potentially do that. One technique you might consider is to look at some part of this really big frame, and try and figure out which region applications are interested in and only transmit that region. The problem with this cropping model is that if you're only sending a little part of the frame, then you're kind of defeating the purpose of having such a wide, expansive view of the world from so many cameras. Furthermore, applications are interested in all sorts of content here, like people walking by on the sidewalk, cars driving by, trucks entering and exiting the construction site. It's hard to decide which piece of the data you'd send. So generally speaking, we don't think we can crop this data. But what if we just really heavily compress things or reduce the spatial resolution? Compression encoders like H.264, H.265 are really good these days. However, because these viewpoints are so wide, important details that applications need are typically really small and hard to see. Compression and downsampling destroy these subtle details. These applications are relying on these details for their complex processing in the cloud. Consider, for example, a person walking by the street here. Even at relatively high quality, 7 megabits per second, it's hard to see, for example, what type of clothes they're wearing if you wanted to see something about the person. If we compress down to 100K, you can't see anything at all. So generally speaking, we don't think that compression alone is the answer. So what are we going to do with all this data we have at the edge? If we can't compress it, we can't crop it. in this work, we're going to target a particular type of application that are interested in rare events, like specific makes and models of cars, particular regions, etc. If we consider this type of application, then by definition, large periods of time don't contain data that we care about. What we can then do is take the well-known idea of early discard and push it to the edge. This gives us the opportunity to realize a big bandwidth savings by discarding data that doesn't matter. However, by pushing the filtering to the edge, we introduce another challenge. Whereas cropping and compression are relatively lightweight and easy to implement in hardware, complex application-specific filtering like we want to do is not trivial and requires many more CPU resources. So by focusing on these rare events, we've opened the door for saving bandwidth, but now all of a sudden we have to worry about compute. The work that I'm going to talk about today tries to address this. And I'm going to propose a system called filter forward, which saves bandwidth by filtering relevant data at the edge while supporting scalable multi-tenancy, multiple applications. Let's dive right into an overview of the filter forward architecture. We have an edge node, we have a data center, we have user applications, complex analytics running in the data center. Our filtering is going to be happening on the edge node. That's where the interesting stuff is. We have frames coming off of one or more cameras. And then this is the part where filter forward comes in. We're going to build off the concept of modern object detectors, and we're going to use a feature extraction deep neural network. In our case, we're using MobileNet to extract semantic features about each one of these frames. We're going to look at these deep neural network activations, treat them as feature maps, and then we're going to feed these feature maps, which contain all the semantic content about what's going on in each one of these frames, into a set of custom lightweight networks called microclassifiers. The key contribution to this design is that by using a feature extractor to generate the input to these microclassifiers, we're amortizing the expensive pixel processing, which takes up most of the compute, across all of the applications. Let's look a little bit more about these microclassifiers. They are fundamentally the building blocks of the filter forward system. They are small, individually trainable neural networks that determine if a single frame is relevant. Once we have these per frame decisions, we take them and we smooth them into contiguous event detection windows, which are then re-encoded and transmitted back to the data center. Our fundamental reason for choosing a design like this is by sharing the pixel processing between all of the microclassifiers and only operating on these high-level feature maps, we're able to make this system much more computationally scalable for large numbers of applications, large numbers of microclassifiers. Now, if you recall, another thing I brought up was that it's really important that we be sensitive to fine-grained details, because with these wide-angle videos, things are really small far away. The way that we've done that is twofold. Instead of really heavily downsampling our images before we process them, like is typical in object detectors and image classifiers, we operate on full resolution frames. This, of course, gives a big computation overhead. If you're processing a 1080p image instead of something that's 224 by 224, you're doing a lot more work. However, because the microclassifiers are lightweight, we're able to amortize that away effectively. The second part is that we give them the flexibility to pull from any intermediate layer in our feature extraction network. This is a key way that we can fine-tune the microclassifiers based on the granularity of the type of task that they're operating on. Another important thing to note here is that because the microclassifiers are completely independent of each other, they're not ingrained in the same network, they are individually trainable. This is important because in real-world deployments, applications come and go all the time. If we had used a monolithic multitask network or just fine-tuned an object detector, for instance, we would then need to retrain the whole network whenever an application arrived. And from a deployment practicality point of view, that doesn't really work for us. In our paper, we propose 3 different microclassifier architectures. I'm going to talk briefly about them here. The first is just a simple 3-layer convnet, uses 1-by-1 convolutions to expose fine details in the feature maps. Unlike normal transfer learning, which keeps the fine-tuned portion of the network constant, by making custom microclassifier networks like this, we're able to specialize the types of applications that are operating on this wide-angle surveillance video. Remember that we're processing full-resolution frames, so these networks are a little bit more expensive than you'd think if you were just operating on really small 224 by 224 images. We also have a couple of other architectures that we designed. A localized binary classifier that is designed to pick out prominent objects in a localized view. So if you, for instance, if your application knows that it's interested only in content in a particular region. An important thing to note here is that we're not actually cropping the original pixels, we're cropping the feature maps. So we're still sharing the same base deep neural network with the rest of the microclassifiers to retain our scalability. And then we have a temporally windowed version of the same localized binary classifier that gives us a little bit better accuracy because we're looking at a window of frames. An important detail to remember here is that applications are allowed to mix and match these different architectures based on their requirements, what they're trying to detect. A diverse set of these applications will be running at the same time on an edge node, all sharing the feature extraction deep neural network, all extracting from different layers, different intermediate activations. And please see our paper for more details about these. I want to now give you a bit of a preview of our evaluation. Of course, more details are in the paper. We looked at a couple of real-world data sets that allowed us to demonstrate the capabilities of our microclassifiers. In the first data set, we were looking for people in this crosswalk region. So the localized classifier is helpful because we were allowed to discard parts of the frame that weren't necessary and tell the classifier that we were interested in a particular region. For the second data set, which we actually collected from our deployment near CMU, we're trying to find people with specific details in their clothing, like if they have a red shirt on or a red hat. And this was really, really hard because those details are tiny and they get destroyed really easily by compression. The pixels really, really matter a lot. In this case, the full frame object detector, the first one that I described, is really well suited to exposing these details. And the figures that I present now are going to primarily deal with the second data set. When evaluating filter forward, let's think back to the original challenge that we were trying to solve. We want to save bandwidth by dropping irrelevant frames. So first, we're going to evaluate how our event detection accuracy changes as we reduce our bandwidth usage compared to the more practical of our baselines, full stream compression. Then, because we're pushing this filtering to the edge where resources are constrained, we need to investigate filter forward's throughput scalability as we add more applications. For this, we're going to compare it to another method of designing lightweight classifiers. We looked at the NoScope paper from 2017, which proposes a cascade of various filters that protect access to an expensive base deep neural network, or expensive deep neural network. This is designed primarily for bulk analytics, but it's also applicable to edge filtering. They design lightweight binary classifiers that operate on raw pixels, and we call these lightweight classifiers discrete classifiers. The important difference to remember between these discrete classifiers and filter forward's microclassifiers that I just talked about is that the discrete classifiers are operating on raw pixels, so each one needs to do a full translation from the original input to some decision about whether a frame is important. By operating on the features extracted from a base deep neural network, our microclassifiers are much more computationally scalable. Let's first take a look at our bandwidth savings. What we're going to show is the event detection accuracy as we vary the bandwidth use. As an accuracy metric, we're using a notion of event F1 score that's based on a paper from last year's SysML. See our paper for more details about how we adapted that metric. here are the results if we compress the entire stream and run the processing in the cloud. As we increase our bandwidth that we allow the system to use, the accuracy increases as well, as you would expect. What filter forward allows us to do is take basically any point on this curve and switch it to the left by dropping unnecessary frames. In this particular case, we preserve our accuracy while using 6x less bandwidth. The 6x, however, depends a lot on the specific task. Of course, like if your target event is present in all frames, then filter forward is not going to be able to save you the bandwidth there. The real takeaway here is that if there is bandwidth left on the table by data that you don't care about, filter forward will find that and it will concentrate your bandwidth use on the data that matters, the frames that matter most. Now, before we talk about end-to-end performance, let's look specifically at the cost of each microclassifier. Here we're analyzing how computation cost in terms of multiply adds, number of multiply adds, impacts event detection accuracy. We're comparing to the pixel level discrete classifiers that I described earlier, using the same event F1 score metric as the previous graph. Microclassifiers achieve slightly higher accuracy, but have a much, much lower marginal cost. This is because they're operating on the features instead of raw pixels. They're able to be much less complex. They're just taking a semantic representation to a final decision, not pixels to a final decision. What this slightly higher accuracy shows is the benefit of being able to use a really powerful base network for our feature extraction. Using a network like MobileNet that has a lot of sensitivity would normally be just too expensive to do on every frame. But in filter forward, because we're amortizing that cost across all of our classifiers, we're able to realize that benefit. Finally, let's take a look at end-to-end performance scalability. We're looking at how the rate at which we process frames changes as we vary the number of classifiers. In addition to comparing to discrete classifiers, as before, we're also looking at a more simple baseline of just running multiple copies of a fine-tuned MobileNet, one for each application. We ran these experiments on a 4-core Intel CPU, similar to what we've actually deployed. And so the numbers on the y-axis don't really matter, it's more the trends that matter. As you would expect, running a full MobileNet for each application causes the performance to drop off pretty fast. Didn't really think that that was going to work out. The discrete classifiers, on the other hand, being much less complicated than a full MobileNet, achieve a much higher throughput up front, but because they're duplicating a lot of pixel processing, their throughput also drops off pretty quickly. Filter forward, on the other hand, incurs an upfront overhead and is slower for lower numbers of applications than the discrete classifiers because of this base deep neural network. But by the time we're running 4 classifiers, filter forward achieves the highest throughput of these systems. And by the time we get to 20 classifiers, filter forward is 4 times faster. Again, the reason for this is because each microclassifier is so lightweight that adding more and more really doesn't change your throughput all that much. The vast majority of the computation is in this shared base deep neural network. Ultimately, if you have more than a couple of applications, filter forward is going to give you a big throughput win. All right, I'm basically out of time, so I'd like to summarize. Filter forward is a new system for video analytics on the edge. We're able to save a lot of bandwidth and get much higher throughput with modest numbers of classifiers. At the core of our design is a new architecture for application-specific neural network filters called microclassifiers that have a much lower marginal cost than existing work. If you're interested in learning more, please come visit me at the poster session or check out this URL. Thank you very much.
All right, so this paper's over. Questions?
Yes, so one clarification is that here you will determine, let's say that I have n frames, and then you will determine which frame is useful to send to the data center, right?
That's
so
correct.
Conceptually, what you're doing is kind of like attention-based selection. So I'm curious why we need to have a different kind of a micro classifier when attention-based model will do the exactly the same thing, right? I mean, in the CV community, people are using attention-based model to select like a useful train, for example, to generate the captions. So can you contrast your approach against, let's say, the attention-based approach and then why yours is better?
I think I agree that there's a lot of other ways you could solve this problem in the CV community. Attention-based mechanisms are one of them. However, we approach this from the system architecture design point of view. I'm fundamentally a systems researcher, and so I looked at how can we share computation, how can we avoid doing redundant work? And that's really why we arrived at this design, but I completely agree that there are plenty of other interesting ways that we could solve this problem in the CV literature.
Thanks, Akansha from Google. I had a question on how I would go about training these microclassifiers because I would need the queries up front in some ways for me to know what I'm training for. And today, a lot of the mobile nets are trained general purpose.
Yes, excellent question. The microclassifiers themselves are trained independently by whichever entity is developing a particular application. So if I was trying to develop an application that let me know if people were wearing blue jackets, I would query the video deployment for a set of representative data from these cameras. I would go about labeling it, and then I would train the microclassifier myself. And what I give to filter forward as an application developer is the architecture of the microclassifier, frozen weights, and then a specification of which intermediate layer from the base deep neural network I want to operate on, and if I want to optionally crop that intermediate layer. So the training is handled not by the system as a whole, but as each individual user, so that they can keep the data separate.
It seems like a chicken and egg problem, right?
Yeah, it does. And it's still a developing field that we're trying to figure out all the questions just like that. Thank you very much.
Do you have any sense of how the accuracy of the mobile nets that you use compared to, say, more accurate methods such as mask RCNN with a 152-layer ResNext or something?
That's a really interesting, excellent question. In this work, we didn't particularly look at how we choose this base deep neural network. We picked MobileNet because it was pretty accurate and lightweight, and we were running on CPUs on edge nodes. I think it's a really interesting direction for future work to try different architectures. And one thing that pushing more compute resources to the edge and giving yourself more of a budget would allow you to do is play with more expensive techniques that give you better features than, say, something like MobileNet would, which is a few years old now. Thank you very much.
All right, let's thank our speaker. All right, so our next speaker is Huizi Mao, who is currently a PhD student at Stanford, advised by Bill Dally.
Looks like it's still Christopher's slide. Yeah, I don't know why. It's still Christopher's slide.
I think they're working out on
Okay.
that side. They should.
Sometimes if you plug this in first, it doesn't always.
Hi, I'm Huizi from Stanford University. Today I'm going to give a brief overview of CADET, an efficient system for video object detection. So first, what is video object detection? The goal of video object detection is essentially to locate and classify objects in a video stream. As shown in this example, there are 4 objects detected from an image, and 3 of them are pedestrians labeled in yellow boxes, and 1 of them are car in red box. And one major difficulty of video object detection is that it's rather compute intensive. For example, a very expensive GPU can only process medium-sized image 19 frames per second, while a very cheap camera can easily generate high-resolution video streams at 30 frames per second. And imagine how many cameras do we need for some real-world applications like autonomous driving? Well, it requires multiple cameras. So are we gonna stack like 10 GPU cards on every self-driving car? Hopefully not. So to make it practical for real-world applications, we need to develop some efficient algorithms for video object detection. And before delving into the details of our system design, we would like first to think about the properties of video. So there are two types of localities that exist for most of the objects in a video. The first is temporal locality, which means an existing objects tend to appear again in the near future. And the other one is spatial locality. If an object appears again, then it tends to appear in a nearby location. And these two localities are quite obvious, right? But how are we gonna exploit them to make it more efficient for video object detection? And our answer is quite simple, that we should avoid redetection and do calibration as much as possible. So redetection is expensive because we will need to run a very large detector model all over the place on the whole image, while calibration can be much cheaper because if we have already know the rough location of some objects, we can only run this convolutional neural network model on selected regions, therefore greatly reduces the computation cost. And CADAT is based on such simple concept. And we now talk about the design of CADAT system. So first, we would like to start with some standard detect-to-track pipeline. So in this pipeline, the detector takes images one by one and outputs the detections for each individual images. Here, a detection means the bounding box surrounding some physical object and the class label associated with it. And later, once the detections of multiple frames are ready, it's fed into some post-processing step, like a tracker, and the tracker links the detections into tracklets. So why are we talking about this? As we have mentioned before, we want to exploit the locality of the video by estimating the rough locations of previous objects. So we figured out that the tracker is actually a good candidate for this goal. Now think about a standard tracker. The goal is to link detections, and to do that, it will need to predict the future locations of existing objects, and then solve a matching problem. And for our tracker, it's kind of reversed. So we are trying to predict the future locations, and to do that, we will need to link detections and estimate informations like the motion and change of scale. And so the advantage of that is that we can borrow some well-studied popular tracking algorithms with little modification and directly apply it to our system. So once we have the predicted locations from the tracker ready, we only need to run the large detector model on selected regions, therefore greatly reduces the computation cost. But that comes with a problem. The problem is that if there are some new objects appearing mid of the stream, then our system is blind to it. So how are we gonna tackle this problem? Our solution is to add a small detector. And by small, it also means it's kind of inaccurate because accuracy always comes at the cost of computation. And the primary goal of that detector is to look for new objects. But when it is looking for new objects, it may also come up with some detected objects from previous tracker. And fortunately, our system is able to handle this situation because there is a step called non-maximum suppression in our big tracker, or big detector. And in this step, duplicated proposals will be filtered out. And we now put it together and name our system Cascaded Track Detector and give some new names to each component. The small detector is renamed as proposal network because it's a very small model running on the whole images. And all its detections is just proposals, which will be later calibrated by the refinement network. And the refinement network, although it shares the same parameters as the original large detector, it only runs on the part of the image and mainly does calibration. And the tracker predicts new locations from previous detections. And as you can see here, the proposal network and the tracker are both quite small compared with the original large detector, and they incur little overhead. And in this slide, we describe some details about the CADAT system. So first, we will need to mention that the design principle of the system, which is modularity. And by modularity, we mean that CADAT is designed in such a way that we can change a module without retraining the whole system. Notice that this is a little different from the popular end-to-end concept in deep learning community. By end-to-end, we mean that we can put some fancy components together and train them all together. But if you made some simple modification to any of them, then you will need to change the whole system again. And modularity is a desired property for a system because it will add great convenience for deployment and development. And it should also be able to support various detecting and tracking algorithms. So below, we show some default choice for our system, but it does not mean we are only limited to this choice. So for the tracker, we choose the sort algorithm, which is a very lightweight tracking algorithm because, as we have mentioned before, we only care about the rough location of previous objects. So we don't need it to be super accurate. And it is quite lightweight, so it can run 1,000 frames per second on a single CPU core. And for the proposal network, we choose faster RCN with a customized 10-layer ResNet, which is much smaller than a standard ResNet 50. And for refinement network, we use a standard ResNet 50, but it only selected executes on part of the image, and there's no region proposal networks because we already got proposals from the proposal network and the tracker. And it saves about 12 times number of operations on Kitty dataset. So here is an example from Kitty dataset to show how our system actually works. And so this is the last frame where we already got some detection results. And in the next frame, the tracker, by information of motion or other stuff, predicts some new locations. Notice that there are only 3 objects, and 1 object is predicted to leave the frame, so it's deleted and not shown on this image. And then the proposal network proposes some candidates as shown here in the red boxes. And it detected 2 cars and 1 cyclist, and notice that the larger car has overlap with tracker's output, but our system is able to handle it because in the final refinement step, the refinement network selected run on part of the image, which is marked in the dotted box, and then the duplicated detections and non-existent detections are deleted, and the remaining detections are calibrated. So here comes to the experiments part. So we selected 2 data sets with common urban street scenes that is ideal for autonomous driving. And the first is Kitty. Here is an example of Kitty data set. And the other is city persons. I give an example here. And both data sets are quite small compared with some popular data sets for training deep neural networks. For example, there are only 8,000 images on Kitty compared with 1.2 million images in ImageNet. So we need to overcome the training problem. So we adopt a 3-stage training pipeline, which involves pre-training the model twice. First on the ImageNet classification task, and then on the COCO detection task. And we have to say that the lack of complex and frame-by-frame annotated dataset is a general obstacle in this research field. And if anyone sitting here is willing to share 1% of your private dataset, we will be quite grateful. Yeah. And in the following slide, we will show 4 selected experiments. The first one is to show that actually our system works and temporal information is helping with detection. So here, the accuracy is measured in mean average precision, which is a common metric for object detection task. And here the cascaded system is actually cadet without the tracker. So basically no temporal information. And what about cadet without the proposal network? We tried it and it's too bad, so we didn't even bother putting it here. So as you can see here, the cascaded system achieves decent MAP on kitty dataset with less than 1% accuracy loss. But if we switch to a more difficult dataset like city persons, then the accuracy loss is non-negligible, which is more than 6%. And for our cadet system, on both datasets, it achieves little or no accuracy loss, while reduces the number of operations by about 10 times. We show that temporal information is necessary to preserve the MAP. And on our last slide, we only show the theoretical speedup, which is measured in number of operations. And on this slide, we want to show some real speedup on GPU platform, like Maxwell and Titan X. So notice that this script is implemented with PyTorch by some untrained PhD students. So we still believe there's large room for improvement. And here, as you can see, the overall time is measured frame by frame by CPU, and our cadet system is able to achieve 2 times speed up compared with the original faster RCN. And if you only measure it by GPU time, it's close to 4 times. And in this experiment, we are going to show another metric, which is delay, and show how it correlates with the number of operations and the MAP metric. So delay is defined as the average number of frames taken from an object appears to it being detected. And we adjusted the choice of proposal networks and rank it from the largest to the smallest and show how it correlates with MAP. So here is some better visualization of the previous table. So here, the green line is the MAP metric, which stays as a constant almost all the time. And the red line is the delay, which increases as the number of operations going down. So that indicates, like, for video object detectors, preserving MAP is easy, while preserving delay is more difficult. So we hope that could provide some insights for future video object detector design. And in our final experiments, we would like to show, actually we can replace some component of our cadet and it still works. So we replace the faster RCN in refinement network with RetinaNet. And RetinaNet is a popular single-stage detection algorithm, which has fewer operations than faster RCN, but also its accuracy is slightly worse. And as you can see here, with RetinaNet, the cadet system actually improves MAP and also reduces the number of operations. So it shows that our system is well decoupled, and it also works with other detection algorithms. So finally, we would like to show a tiny demo here. Okay, so here the upper one is the original faster RCN model, and while in the bottom is our cadet system, and we marked the number of operations here. And as you can see, for most of the time, it produces almost the exact detections, and sometimes it's even more stable. Okay. So in summary, CADET is an efficient video object detection system that can reduce the number of operations by about 10 times and preserve MAP well, but meanwhile sacrifice a little delay. And it can support various popular detection algorithms. And for more information, come to see our poster at the poster session. Thank you.
Paper is open for questions. Can you please state your name and affiliation before?
Yeah, Minsik Cho from IBM. So very nice work. I have one quick question here is that, so essentially you said that you use like a sort algorithm, right?
Which slide are you
for
referring?
tracker.
For tracker.
Yeah. Which is essentially like, as far as I understand, that's essentially Kalman filter-based numeric optimization. Here, right?
Yeah.
So that's essentially Kalman filter. And which has a problem when you have some kind of, let's say, the temporary obstacle in front of objects. So I'm curious why, so in computer vision community, there are other very inexpensive object trackers as well, based on some kind of very small neural network. So I'm curious why you use a Kalman filter instead of other, let's say, the DNN kind of approach, which can deliver better accuracy.
Oh, you mean why I chose Kalman filter for the tracker?
Yeah.
Okay, so as I have mentioned, we are interested in the rough estimation. So we don't need it to be super accurate. So, and the problem of running a deep neural network is that it will consume extra number of operations. So right now the tracker is almost negligible compared with other networks.
So here main reason is that for computational efficiency, you stick to Kalman filter instead of a DNN kind of approach.
Yeah.
Okay, thank you.
And actually, we used even a simpler method than Kalman filter. And with experiments, it showed that even a simple linear decay model works for the tracker.
All right, let's thank our speaker.
Okay, thank you.
So our next speaker is Rudy Chin, who is a second-year PhD student at Carnegie Mellon. He works with Professor Diana Marculescu in the area of efficient machine learning and deep learning.
Hello, everyone. So today I'm going to talk about AdaScale, tour real-time video object detection using adaptive scaling. So this is a joint work with my colleague Rizal Ding and also my advisor Diana Marculescu. And as we have heard from previous talk, that video object detection is one of the key tasks in various emerging applications. For example, autonomous cars, autonomous drones, household robots, all these kind of emerging applications actually require this video object detection capability to do more visual cognition to interact with the world. However, different application has different requirement towards accuracy and also speed requirement. So PyR actually introduced one knobs for application developers to trade off between accuracy and also speed. And that knob is on the scale of the input image. So here we show two of the prior art in object detection, trading off accuracy and speed when they downsample the images. As we can see clearly, there's a trade-off between accuracy and speed when we resize the input image. So in this work, what we found, the key observation is that scaling down an image in terms of the resolution might sometimes help for certain images. For example, we show two images here, and this is the scale that we downsample to the common used 600 in terms of the shorter side resolution, and then we feed it to a pre-trained object detector, and this is the result that we get. As you can see, there are many false positives in these images. And if we downsample these images, we find that the false positives went away. So these two images demonstrate the cases where when we downsample the image, it doesn't hurt the accuracy, but in fact, they improve the accuracy and also improve your speed. And why does this kind of effect happen? It is because when you downsample the image, you can reduce some noises toward the image, and then you can further reduce the false positive of the object detector. So the key question of our research in this work is that how do we determine which image to scale by how much? And our solution to this question is by forming this as a regression problem. So I've broadly go through the motivation of this work and also our key observation. And then I'm going to talk about how we're going to go about addressing this regression problem. And then we will talk about the AdaScale methodology. Then I'll talk about my results. So in terms of regression problem, it is really important for us to first determine what's our input and what's our output. Why are we really regressing? So what we really want is given an image and determine what is the best scale for this image so that it gets better accuracy and also speed. So this is the demonstration of we building our regressor module on top of an existing backbone convolutional neural network. So this is a convolutional neural network that used in object detector. So on top of the backbone convolutional layer, you have the RFCN, which is one object detection algorithm on top of that. So we put our regressor on top of the high-level feature of the convolutional neural networks. And what we want to regress in the end is how much to scale up or down of the current image. And we put our regressor on top of that layer because RFCN head on top of that feature can able to generate the bounding boxes of the image. So we hypothesize that they have the representation in that layer contain the scale information. And that's why we put our regressor on top of that representation. So now we know how our regressor look like. Then the question is, what's the data set we're going to use to train this scale regressor? So to generate the target labels to train these scale regressors, we generally follow two steps. First step is we first select a discrete set of scales to broadly cover the scale of interest. In our case, we select 600 with the default resolution in common object detector, and then we go down because we want to hopefully accelerate the object detector. Then the second step is that for each of the image in your training data, you want to pass through across all these discrete scales and determine with some metric which one is a better scale, and use that scale as your ground truth so that now you have an input and output pair so that you can train this scale regressor. And one thing we have to determine here is that what is the metric that we're going to use to determine which one is a better scale. And an intuitive solution is to use the accuracy, which is the mean average precision in object detection. However, we find that mean average precision is too sparse in an image level. So we will end up having multiple scale having the exact same mean average precision so that we cannot actually tell which one is a better scale. A second intuitive idea is that maybe we can use the training loss that we use to train these object detectors to determine which is a better scale. However, we find that current loss function that used to train these object detectors favors extreme scales. To further explain why this happens, let us look at the training loss that people used in training this object detector. So this loss contain two kinds of losses. One is classification loss for the prediction bounding box, and also the regression loss for the prediction bounding box. And ICE is summing up for all the bounding box that is predicted by the object detectors. And noted that we have a bracket there saying if I is in foreground, meaning if this bounding box in foreground, that's only when we have the regression loss. That means if the bounding box is in background, then we wouldn't have this regression loss. So that's what we use to train an object detector. So what determines if this bounding box is in background or foreground? Let me give you an example. So this is a predicted bounding box, assuming we have a ground truth that locates roughly similar to where it locates. And then to compute whether this is in foreground, we actually determine its intersection over union. So if this metric is larger than some threshold, defined in prior people use 0.5, and then we can say, okay, this bounding box belongs to foreground. So what we observed is that if you scale the image too small or too large, it is very likely that an bounding box will fall into background. When it falls into background, it zeroes out the later regression loss, so that we will have a case where we have lower loss for that scale, but having worse detection results. So to solving this problem, what we propose is we only consider the foreground bounding boxes when we compare the scales. So there's a tiny little trick that we adapt the current losses that we only consider the foreground bounding boxes. So let me give you an example on how we used to evaluate this metric. Assuming we have one image, 3 scales, so that we downsampling into 3 scales, and then let us denote the red box as the foreground bounding box, the gray box as the background bounding box. And then for all of them, we're going to pass them through the object detector so that we get several results. And then we only consider the foreground bounding boxes, and we first sort them in terms of the loss, and then we only consider the foreground, which are the top 2s that for all the scales. And then we can compare across scales in terms of which one is better. Now that we have a method to determine which scale is better, that means we are now equipped with a data set that has an input and output that used to train our scale regressor as here. So now we can train this scale regressor. We train this scale regressor with mean square loss, by the way. So now we know how we can generate this label and train this scale regressor. Let me just go through briefly about what is Adversarial methodology. So our methodology consists of 2 parts. One is training and one is testing. In training, we first fine-tune an existing object detector with multi-scale training so that it doesn't overfit to a single scale. Later, we use the train object detector to generate the label that I just mentioned. So now we have a lot of scale labels. With that, we use the training pairs to train our scale regressor by freezing the backbone CNNs, so that we are only training the scale regressors. So after that, now we are equipped with the scale regressors to determine the better scale for the current input image. In testing, we get a sequence of frames in video object detection. So we use as shown here, we use the frame in timestamp t, and then it will first go through the scaling module, which will scale it to a certain size. In common object detection, it is scaled to the shortest size 600, but in here, we actually have a parameterized way to scale that. So after we scale that, we'll go through the backbone CNN as usual, and then go through the object detector to produce bounding boxes for timestamp t. And on the other hand, we also go through the scale regressor to generate what's a better scale for that current image. But then we're going to use this scale for the next incoming frame, so that we are actually employing this temporal consistency assumption here that this frame might be really similar to the next frame, so that their scale might share. So with that, now we all know how this Adversarial methodology works. Let me dive into a little bit about our results. So the very first result that we're going to show is on the ImageNet video dataset. Here we plot several prior art in terms of video object detection. So on the right-hand side, we have the state-of-the-art deep feature flow, which is the fastest video object detection. And also the blue one is our baseline baseline object detector, RFCN, and also some other video object detection methods. With them, we can actually augment them with Adversarial methodology so that we can push the Pareto frontier a little bit further in terms of both accuracy and speed. I'm going to zoom into the baseline blue ones, the object detector, and also the object detector with Adversarial methodology a little bit to further discuss our work. So here we denote SS/SS as single scale training, meaning training the object detector, single scale testing. That is the baseline people use. And then multi-scale training, single-scale testing, just because we do multi-scale training, we want to understand how they contribute to the results. Later, our methodology, which is multi-scale training, Adversarial testing. So we show the result across the different categories on ImageNet video dataset. First of all, we highlight several categories that have more than 1% mean average precision improvement. So they are in the blue ones. Maybe it's hard. OK, it's good. So they are in the blue one. As you can see, there are a lot of them that get improved by more than 1% of mean average precision by this Adversarial methodology. But also, we also observed that there are several of them actually got worse. So we highlight the one that got worse in red. So there are 3 of them actually got worse when it is equipped with Adversarial methodology. And we are really curious like why that happens. And then we zoom in to see that actually we can find that when those categories being trained with multi-scale training, its accuracy will drop by a lot. Then with Adversarial testing, it gets a lot back, but it's not as good as the baseline. Up to this point, you might wonder, maybe it's because of the multi-scale training that makes this object detection better, but not Adversarial testing. So that we argue that's not the case. For all of the cases, that the multi-scale training actually doesn't help in terms of the accuracy. However, Adversarial testing helps the accuracy. So we can see, final mean average precision and also for several classes. And that's the accuracy improvement part. We also highlight the runtime improvement. So we go from 75 milliseconds down to 47 milliseconds for this baseline object detector running on our GPU 1080 Ti. So now up to this point, we know this Adversarial kind of work based on these results. And then we might be wondering why it works. So as I mentioned earlier, our intuition is that when you downsample the image, you can reduce part of the noises, so you can reduce a lot of false positives. So we look into whether it is really reducing the false positives. So we picked the top 5,000 prediction of the object detection for each of the category, and then look at how many of them are actually false positive across different methods. As we can see, the red one, which is multi-scale training, Adversarial testing, has the least number of false positives, which actually confirm our intuition that with this methodology, we can reduce false positives, which further improve mean average precision. Nonetheless, not to mention, we also improve the speed because we downsample. So up to this point, we know Adversarial works, and we want to dive in a little bit to understand this methodology further. So we do an ablation study on our multi-scale training. So first, we do it without multi-scale training because we say multi-scale training make this object detector less overfit to the single scale. But so in this case, we want to understand how that behaves. As we can see here, if we don't do multi-scale training, our accuracy doesn't get improved, but it doesn't get worse. However, we still get speed improvement. In the bottom one, we show the regress scale that is outputted by our scale regressor. We can see it is leaning toward the right-hand side of the scale, meaning it thinks the optimal scale is really belong to 600, the original scale. And if we have more multi-scale training into the object detector, and then we can gradually see Adversarial becomes better. However, we can see single-scale training actually become worse. So we can go further and further. That's, in the end, we can see a trend that if we do multi-scale training, and the object detector will be less overfitted to some single particular scale, and then that is beneficial for the Adversarial testing methodology. And also we can get further improvement in terms of speed as well. And then we can see the regress scales move from really leaning toward the right-hand side gradually toward the middle, meaning the range of the optimal scale that is thought by the scale regressor to be wider and wider. So now we know about how Adversarial methodology works with different kind of training in terms of multi-scale. Then we want to probe into the dynamics of Adversarial methodology, because as we've seen earlier, the Adversarial testing methodology is a feedback loop. So once we scale, the next frame is based on the current frame, and then the next frame based on the last frame. So it's a feedback loop. We want to understand how it works across time. So here we show a video we show several clips. The first one we show is a pretty static video with a large cat in it. We can see clearly at first, which is 600, the normal scale that you adopted in object detector, it quickly goes down to a pretty much smaller scale and stabilize, meaning the regressor learns to downsample the image if the object in the frame is large enough so that when it downsample, it doesn't really hurt. On the other hand, if we have smaller objects in the image, the object detector actually, the scale regressor learns that we have smaller objects in an image so that it downsample, but not too much. So it stays roughly in 400-ish size. Lastly, you might ask, what if I have multiple sizes of the object in a current frame? So that's what happened when we find that. So we find a jittering between 400 and 200 across time. So you might wonder, so this is really unstable. However, we know that for all of the frame, we still are able to detect what is in there. So lastly, I'm going to give you a bit qualitative analysis comparison between the baseline. So the top one is the single-scale training, single-scale testing, our baseline, and the bottom one is the AdaScale testing. As you can see clearly, for some images, it reduced false positives. For some images, it even improved true positives. With that, I'm going to conclude my talk. First, we propose AdaScale, which improves both speed and accuracy in the video object detection setting instead of trading one for the other. The second thing we achieved is that we demonstrate 1.3 and 2.7 mean average precision improvement on ImageNet video dataset, and also we use a mini YouTube bounding box dataset, which is in the paper, with 1.6x and 1.8x speed up respectively. Lastly, together with the state-of-the-art video object detection acceleration technique, which is deep feature flow, we can get even further improvement on top of that, which is another 1.25x speed up with slightly better mean average precision. So I'm conclude my work, thank you, and I'm open to questions.
This paper is open for questions. Please state your name and affiliation.
I am Paulius from NVIDIA. I had a quick question. So for the cases where you saw the accuracy improve, did you study which object sizes that improved for? Because I'm assuming if you're scaling down, maybe accuracy improved for large objects.
Mm-hmm. Yeah, so that's a great question. So commonly what we see is that if there's a huge object in the image, you can actually you can scale down it by really much without hurting the accuracy. But still, we can see, for example, the turtle case, it is actually small, but then it is still able to downsample. So I think it is not just the size of the object within the image, but also maybe the texture and the complication of the image that decides whether you can downsample or not.
Thank you.
Thanks.
One question I had would be, how would you handle the case where you have objects of different scales in the same image?
Yeah, so I think that's a really valid and good question. So as we recall that our label generation process is actually data-driven. So we didn't really constrain our input image to have a single object or actually multiple objects. So based on that, we are actually just comparing. Let's say this is how many objects we have in this image, and then we just comparing across different scales and let the data decide which one is better. So I think even if we have multiple objects in the data set, it will still help.
All right, so let's thank our speaker.
Thanks.
So our next speaker is going to be Paul Watmo, who leads research on machine learning algorithms and computer architecture at ARM ML Research Lab in Boston. Also, one quick thing is, for those of you who are doing the demo preview, can you line up during the Q&A over here to get ready for the 1 minute ad?
Great, thank you, Vivian. Good afternoon, everyone. Really excited to be here at SysML today. I think this is a really interesting conference. I also realize this is the last talk of the day, so I hope you can handle one more PowerPoint presentation. I'd like to acknowledge my co-authors at the ARM ML Research Lab in Boston. And I'll start with some motivation for this work. So this slide shows a number of new sort of applications and use cases that have emerged over the last few years, and these are all driven by computer vision on mobile platforms, albeit quite different form factors. And these things all have sort of real-time performance requirements. So for instance, augmented reality on mobile, we need to keep the frame rate quite high so that as the user moves the phone around, the image displayed is nice and smooth. And on automotive, with sort of driver assistance, we obviously need to keep the object detection latency as low as possible so we can apply the brakes or whatever is required to avoid an accident. And of course, these things are also battery powered, and the impact of that can be different depending on the form factor, but it generally means we need energy efficiency. Okay, so I think improvements in computer vision is what's enabled these emerging applications, and we've sort of over time we've moved from the older-fashioned approaches like sort of handcrafted feature descriptors and SVMs towards what we often use now, like state-of-the-art convolutional neural networks. These are great. They're way more accurate than the older techniques, maybe 2.5 times more accurate. But they don't come for free. The challenge is the increase in the compute cost. So the y-axis on this plot that compares object detection algorithms shows tera operations per second, so that's the amount of compute workload we have to get done. And if we think about the sort of the power budget for a mobile device, maybe 1 watt, and the amount of compute we can do with 1 watt, you'll see that some of these state-of-the-art CNNs exceed that compute capability. So there's a gap here in terms of the performance and the energy efficiency on these devices. So how do we close this gap on mobile platforms? So I think there's 2 things we can do. The first is we can design more efficient networks. So that usually means trying to optimize our network, not just for accuracy, but also for the amount of operations we have to do and the model size. I think we've made good progress in that. So example here, I think has been mentioned a few times today, is the mobile net architecture. It's quite widely used. We can actually do better than this now, and I think we're going to see some improvements there in the future too. On the hardware side, we can design more efficient hardware for neural network workloads. And there's lots of tricks here which I'm not going to describe. If you're interested in that, I'd recommend Ian Bratt's talk at HopChips last year, where he describes the ARM ML processor. But these are 2 things we can do, but we don't have to think about them as separate things. And I think, as in Ofer's keynote earlier, he mentioned co-designing, and that's very much something we think about as well. And that's kind of the approach we've tried to take in this paper, where we'd like to think at a system level about co-designing the network and the hardware that executes that network. Okay, so if we think about the hardware architectures that we use commonly today, say in your mobile phone, you typically have these different architectures. So we start with the CPU on the left here. This is kind of the workhorse in the system, and it tends to run the operating system and most of the application logic. And anything moving to the right is basically a specialized architecture. So a GPU was traditionally specialized for graphics workloads, and an NPU for neural networks. And the extreme of this is the sort of single function hardware accelerator. And we use this a lot for algorithms that are based around standards like video encoding and image encoding and wireless algorithms and these types of things. But it's a challenging thing because there's a very real risk of obsolescence in the hardware, because they basically do one thing well, but they literally only do one thing. So we've been trying to think in terms of sort of trying to achieve the efficiency advantage of single function hardware, but without losing the ability to sort of have flexibility and generalize to different data sets and different tasks. And one thing that we've taken inspiration from is transfer learning. So probably everybody here is pretty familiar with this. So, one view of this is if you plot the features you tend to learn in the early layers in a convolutional neural network, they tend to resemble something like this: Gabor filters, color blobs, textures, that kind of thing. And in fact, this paper from Jasinski, they basically make the remark in the paper, if you don't see these things, you've probably made a mistake. So that kind of shows that these are features that are generally useful for vision tasks. And we often use this in transfer learning, where we train a model on task A, and we transfer the weights to a new model, and we fine-tune the later layers in the model on task B. And this works really well. It means we can train more quickly, and if we don't have much data on task B, we can actually build better models. And kind of the punchline here is all around these features, so the fact that there's low-level CNN features that are useful across a variety of vision tasks. So the fixed CNN architecture is an attempt to literally sort of encode that in hardware. So this diagram shows the neural network on the top and the hardware on the bottom. And we basically split the model into two parts. So the front-end part is a set of layers where we fix the model architecture and the weights in hardware. So they're fixed and they don't change. The back-end part of the model is different for each task that we want to execute, and it can have a different architecture and sort of arbitrary weights. The front end is fixed into hardware, so we have a fixed weight feature extractor part of the front end, and the back-end classifiers run on a conventional programmable accelerator. The real benefit here in terms of energy efficiency comes from the fixed weight feature extractor. So let me talk a little bit about that. So the point here is we have a fixed architecture and weights, so we can apply a series of aggressive static optimizations. So they kind of fall into two camps. The first is data path optimizations. So here, one of the first things we can do is, because we know the weights in advance, we can actually prune any zero or small non-zero weights. So in a CNN layer, this can typically be around 50 to 70% of the weights can be pruned. So that removes an equivalent proportion of the hardware. Then if you consider this sort of long multiplication example on the right-hand slide here, we can also sort of prune the partial products as well. So we can do this because any zeros in the fixed multiplier basically always result in zero partial products, so we can remove the hardware for those as well. And then again, because we're accumulating less partial products at the end of the multiplication, we can actually optimize the precision of the result as well. And there's further things we can do as well. On the memory side, the weights are hard-coded in the logic, so there's no need to access DRAM memory to load them. And for the activations, because we have fully parallel hardware, we can actually pipeline the activations, and we only need to buffer a few rows of the output feature maps rather than calculating the whole output feature maps before moving on to the next layer. The fundamental limitation here is chip area, because every time we add a parameter to the model, that adds some hardware in the feature extractor. Okay, and to help us explore this, we implemented a tool called Deep Freeze. This is basically a hardware generating backend for TensorFlow. So you give it a neural network model in TensorFlow, and you specify a set of layers, or the whole model, and it generates a hardware accelerator in Verilog, which you can implement for sort of ASIC or even FPGA. And we've open sourced that tool. Okay, so we want to evaluate the fixed CNN architecture, and there's two main things they're interested in. One is the energy and latency improvements. And the second thing is the generalization, so the ability to use that fixed hardware across a range of tasks and data sets. Okay, so the methodology for this is to take a baseline, which is a conventional programmable CNN accelerator running MobileNet v1 network architecture. So this is not a fat model. This is a relatively efficient neural network. And we compare this against the fixed CNN architecture, which consists of two parts, the fixed front end, which we model using Deep Freeze, and the programmable part, which we model using NVIDIA DLA. Okay, and we used 16 nanometer process technology, and we set the area constraint to be the same, so it's 3 millimeters squared. Okay, so as I said earlier, the real benefits come from the fixed weight feature extractor. So this slide gives some details on this part specifically, and the plots on the left show throughput and energy efficiency for each layer of the MobileNet architecture. And you can see there's big improvements on both from the fixed versus the programmable accelerator. So in terms of throughput, there's around 8x benefit, and in terms of energy efficiency in TOPS per watt, there's around more than 68 times improvement. The plot on the right shows the cumulative circuit area as we fix an increasing number of layers. And this is kind of the fundamental limitation with this approach, which I alluded to earlier, which is that the area increases quite rapidly. The y-axis here is exponential. So for the fixie architecture, one of the challenges is balancing the benefits of fixing more layers with the costs of higher chip area and the loss of generalization as we fix more of the model. Okay, so I'll try and start to pull together sort of more of a system level analysis here. So we start here with the baseline. The plot on the left shows throughput in tera operations per second as a function of area. And the plot on the right shows energy efficiency in tera operations per second per watt, also in terms of area on the x-axis. And here we have the baseline, which is NVIDIA DLA, so we have 6 different configurations of DLA. And you see the larger configurations actually result in good improvements in throughput, but the energy efficiency is relatively flat for the bigger configurations like E and F. So now if we add a fixed front end onto each of these 6 configurations, we get the orange line here. As you can see, for larger designs, adding the fixed feature extractor gives a good benefit, but there's actually an area for smaller designs where it doesn't really improve performance very much. Now, the orange line was for 4 fixed layers. We can add bigger fixed feature extractors. They add more area, but they also add more performance and increase the energy efficiency significantly. And this sort of gives a design space of choices, but in practice, for mobile platforms, the chip area is a very important constraint because it adds a lot of cost to the device. So we've imposed a sort of slightly arbitrary constraint of a 3 millimeters squared area. Okay, and we can then pick the best designs that have less than 3 millimeters square area. And here we've sort of cherry-picked a design that has high energy efficiency. So the throughput is similar to the baseline, actually, around 1.7 tops. But the energy efficiency is significantly better, around 22.7 tops per watt. This is around 3.8 times improvement in energy efficiency over the baseline. Okay, so that's improvements in the hardware, but that's only of use if we can actually use this hardware for a range of data sets that we're interested in. So to explore that, we trained the fixed weight feature extractor using ImageNet data, and then we fine-tuned the back end on 6 different tasks. So again, we use mobile NetV1 architecture for this. So the plot on the right here shows those 6 transferred data sets in terms of the accuracy, and the bars show the number of layers that we fix, so fixing 0 layers is the baseline. And you can see most of these data sets are fairly flat on the top, which shows we can actually fix a lot of layers without degrading the accuracy. There were 2 outlier data sets which do drop off, and these actually are for data sets which have very specific images in, like aircraft or road signs. So for these networks, we're not actually able to maintain accuracy when we fix a large number of layers. So instead, we sort of fall back to just taking the activations from an earlier output in the fixed front end. So over the 4 of the 6 networks, we can use all 11 fixed layers, and we get energy improvement of 3.8 times. For those 2 slight outliers we studied, then we can still take the output after 4 layers and get a 50% energy efficiency improvement. And actually, what we haven't had time to do yet is to consider if there's actually a better methodology for training the fixed front end. I think that's quite an interesting research question, and certainly one for future work. Okay, so here's a summary of this paper. So I described how improvements in computer vision are driving new mobile computing applications, and there's an exploding compute requirement due to the move to bigger CNN models to get that accuracy. And this has led to an energy efficiency gap, especially on mobile battery-powered devices. FixCNN is a sort of first attempt to try and think about co-designing the neural network architecture in the hardware. The hardware consists of a front-end fixed-weight feature extractor and a back-end programmable accelerator. We then use sort of transfer learning to generalize that fixed front-end to new data sets and tasks. And we showed up to 3.8 times energy efficiency improvement. And as I mentioned earlier, we've open sourced the tools for this, so if you're interested in playing around with this, please download that. Okay, that concludes my talk.
Good. Just one quick thing, if you're doing demos, can you please line up here?
So for your fixed part, did you try any specific regularization terms?
No, so for the fixed part, we didn't do anything special. We basically took a trained model.
So in your case, making parameters sparse is very critical, right, to reduce silicon area.
I'm sorry, can you repeat that?
Making your parameters sparse is very critical to reduce silicon area, right?
Yeah, so we just did a simple magnitude-based thresholding.
I think you should then try L1.
Yeah,
right?
so you can, I think that was I did make a remark, you can definitely do a lot better in terms of optimizing the model for the
So
the
this
fixed.
is without any L1.
That's right, that's right.
So you looked at a variety of data sets for classification. Do you think this would hold for other types of computer vision tasks?
That's a good question, yeah. I was talking a lot about computer vision, but I kind of did a bait and switch and then talked about image classification. I don't know, I haven't really looked at that yet, but I guess some of those tasks, image classification is kind of like the basis for those, so possibly, but we need to do that, I think.
Thanks. All right, let's thank our speaker, and let's thank the speakers in this session. All right.
One of the demo chairs, so all of the hard work that was done by Che and Theo. Unfortunately, they couldn't be here. So the demo track, the goal of this was to expose researchers and practitioners to the tools and frameworks that are being developed as a part of the SysML community. This was the first year that the demo track was introduced. The proposals were not archival. And there were 32 submissions that we got, and out of them, 15 submissions were accepted for presentation. There's a healthy mix of demos from both academic institutions and from industrial labs. Going forward, the hope is that we would expand this demo track to have more demonstrations in the next year. And also the plan is to make it archival, similar to the process used in the database conferences like VLDB and SIGMOD. So without further ado, I realize this is the last thing between you and drinks and dinner. Let's get started with these demo previews. The format is going to be a 1-minute overview of the demo for each demo that is going to be there. And we will start off with ML.NET.
Hi, my name is Matteo, and this evening I will present a demo about ML.NET and how you can basically implement intelligent application with machine learning inside. ML.NET is a C# framework that be recently open sourced by Microsoft. Although it has been recently open sourced, it's actually being used by several here within Microsoft, and have been used by several products and services. In the demo, I will particularly show how you can implement automatic labeling for GitHub issues, and I will basically run through all the process that you need to do the data preparation, to build the model, to train the model, and then how to basically use their model within the application. Thank you. A few seconds for questions.
Hello, my name is Alex Ormanishan. I'm a PhD student with KTH Stockholm, and the demo will feature our platform called HopsWorks, which allows you to run end-to-end machine learning pipelines. We provide you with the tools for each of these stages, from data ingestion, data prep, model training, model serving, so that you can run predictions on your trained models. At the core of our pipeline sits the feature store, which is the place for verified, validated, and well-organized data that can be shared and reused among different pipelines. This is a data management layer that is governed, can be controlled, versioned, and is searchable. You can write all the pipeline in Python, and you can write it in Jupyter notebooks. And then with the help of Airflow, you can schedule it as repeatable, long-running jobs. We also provide you with logs in Kafka so that you can monitor the performance of your model. We've been running this in production in Luleå on our cluster, where our industrial partners and academic courses has been using it. You are free to come to our poster for the demo, where we'll show you this whole pipeline. Thank you.
Hello, everyone. I'm Daniel from UBC, and before I go to dinner, I would like to ask you a question today. So how do you actually debug a machine learning circuit? How do you actually know there is something wrong in there? Now, let me make this question a little bit harder. What if you can only observe this bug when you're running things at speed on chip? What do? Well, the current solution for this is actually to trace the raw values and then observe waveforms. This is bad because you can only observe the circuit for a very short period, and no one likes looking at waveforms. They are hard to understand, especially if you use some sort of compiler to generate the circuit, like some of the ones that you've seen today. So what we're doing is a little bit different. We created on-chip debug instrumentation, which allows you to store more useful information on chip. And we also created an offline analysis tool, which allows you to visualize this data in a way that makes sense for a machine learning expert. For our demo today, we used our TensorFlow to Verilog compiler to generate a circuit that can classify different drawings of fruits. We then got the circuit, added some bugs, and we used it to demonstrate how our approach can help you finding bugs that will otherwise be very, very hard to catch. Hope to see you at our demo today. Thank you.
Hello, I'm Hung-Seok Park from, I'm Hung-Seok Park from South Korea, Naver Corporation. And we design and develop a visual analytics system for supporting the user-driven hyperparameter tuning process. So we mainly applied a human-in-the-loop approach to iteratively and progressively refine neural network models. And our system enables users to gain insight from the various levels of analysis within multiple coordinate view, such as hyperparameter level analysis and model level analysis and method level analysis. So based on this, we will demonstrate visual hypertuner with some example in our live. So stop on by and enjoy, please. Thank you.
Hi, I'm Eddie Yan from the University of Washington, and we'll be demoing our AutoTVM system, which automatically generates deep learning libraries for not just mobile devices, but all kinds of hardware platforms from CPUs, GPUs to embedded systems. And basically, we're going to focus on mobile devices to kind of show just the coverage of our system. And the high-level idea is that today, a lot of deep learning libraries are handcrafted and rely on human engineering effort for performance. And so in between the front end of your typical deep learning framework, there is a big gap between the number of possible operators that you want to support and the libraries that end up supporting them. And in this case, instead of using or relying on human engineering effort to generate these libraries, we want to use a machine learning algorithm to explore a search space of possible implementations. And so the middle figure is kind of an example of a research algorithm that improves the performance of operators over time as it does measurements on real hardware. So I'll be demoing this approach of going from an input model to generating an optimized library for a specific hardware device. Thank you.
Hello, my name is Supun Nakandala. I'm a PhD student at UC San Diego. And this demonstration will be about CNN explainability. So CNNs are now widely used in many image analytics tasks, but one of the important aspects of using CNN technology is the explainability of the CNN predictions, especially in critical applications like in healthcare and radiology. So CNN explainability itself is an open problem. It's an active research field. But in the literature, one of the widely used approaches is the occlusion-based explainability. So in occlusion-based explainability, one would essentially occlude parts of the image and see what happens to the prediction and then get an understanding on what the model is looking into. But the problem is it is essentially very compute intensive because you have to perform a lot of reinference requests. So in this work, we have identified that many of these reinference requests share redundant computations, and we perform incremental and approximate inference to accelerate this workload. So in this demonstration, you will be able to use our system, Krypton, to interactively diagnose CNN predictions. Thank you.
Hello, I'm Eunji from Seoul National University. Today I'll demonstrate Genus, a system that unifies the performance of symbolic deep learning frameworks like TensorFlow or MixNet and the programmability of imperative deep learning frameworks like PyTorch or TensorFlow Eager. We do this by transparently converting imperative programs into symbolic graphs. We also solve a challenge regarding the discrepancy between dynamic Python programs and the static data flow graphs by exploiting the speculative graph generation and execution approach, just like the managed runtimes of other dynamic languages like Java or JavaScript. Our demonstration will show the programmability, performance, and the correctness of our system. And we are also starting collaboration with Google Brain TensorFlow Autograph team who has similar goals with us. Thank you.
Hello, everyone. I'm Daniel Kang from Stanford University. I'm co-advised by Professors Peter Bayless and Matej Zaharia. Today, I'll be demonstrating the Blazed visual query engine using specialized neural networks. So as we all saw in the past session, video is a rapidly growing source of data. But the question for us is how can we actually process this? And we focus on the batch video setting. We propose a system, Blazed, which is a data management system for video analytics at scale. And we enable non-expert users to query video by using a declarative query language. We also have a set of novel optimizations to enable queries to run extremely quickly. And if you're curious, please find me at my demonstration. Thank you.
Hello, I present, need to stop your video. Okay. So I present deep learning out of IBM Research AI Cambridge. And rather than isolated visualizations, this is a full visual interpretability system for understanding convolutional neural networks. This is based on 4 pillars. And one, you see that for a target class like cars, you can see, for an input class, you can see what the examples for the target classes look like, primarily to see misclassifications, as well as the confusion metrics to get a global overview of which classes are getting mixed up. In 2, we display the network topology. In 3, for each layer, we project down the activation vectors into a 2-dimensional representation, so you can see how they evolve as you step through the network. And you can also see on the right-hand side the saliency map where we see what the network pays attention to. Finally, we have a so-called what-if mode where we can modify the activation vector, backpropagate that into input space, and so see what the actual image for that would have looked like. And if you would like to see how we can explain with Y and 4 this car gets misclassified as a dog, then please come over and see our demo. Thank you.
Hi, everyone. I'm Gregory Fursen. I'm from the Collective Tuning Foundation. And I'm sure most of you find it very easy to rerun your own experiments 1 year later, or if your student is gone, or if you want to try a new CUDA version, or try a new TensorFlow, or try a different data set or model. However, if you're struggling with this kind of tasks, we created a simple and open source workflow framework which can help you automate such kind of tasks, particularly focusing on software hardware co-design and auto-tuning. And if you're interested to see some real use cases from General Motors, ARM, Intel, IBM, from MLPerf, and actually from some of the papers here, please come and see our demo. Thank you.
Hi everyone, I'm Gennady Pichimenko, and today I'm going to present a benchmark suite and tools for deep neural networks that we built together with my students at the University of Toronto. So the major questions we try to answer in our work is how we can effectively identify the key bottlenecks, performance bottleneck in all these different models. And as you all guys know, it can be very poor models. So for example, in ResNet, it can be bottleneck by compute on the GPU, and other models can be bottleneck by the memory capacity. So how do we effectively identify what are the right bottlenecks in the particular workload? So we definitely need to have proper tools. So our benchmark suite provide those tools, and they will help you to measure the key metrics and discover interesting novel optimizations using these tools. And as an example of what we discovered with them, we built like networking profiler that led to publications here at SysML that were presented by Anand early in the morning. We also built memory profiler on top of MXNet that also led to publications at MicroSRC last year. So if you're interested on how those tools work and how you can load them and use them, please come to our post demo session. Thank you.
Hello, my name is Garrett Smith. I'm the project lead of Guild AI. Guild AI is an open source toolkit to run and optimize machine learning experiments. So I'm part of the reproducibility story here, hopefully. The tool is designed for individuals and small work groups to make them more productive. So the emphasis of the feature set is on productivity. But we're going to be talking today, demoing today, the features of reproducibility. And the thinking is to minimize or eliminate any of the tax or the friction points or barriers to entry to reproducibility, and further incent researchers and engineers to use a tool for automation to help them get their work done better and faster with the side effect of having reproducibility. So we're going to be demoing two famous characters here, Arya and Clegane. Arya is a published researcher, and I'm going to demo how she would use Guild to help develop a state-of-the-art model, publish that model. Clegane is another researcher doing a survey paper. He is going to be interested in Arya's work to obtain the trained artifacts, to rerun or recreate her experiments, do comparison, and then deepen his understanding of her work. So if you're interested in reproducibility and productivity features, come by and check out Guild AI. Thanks.
Hi everyone, my name is Xiaoshen and we are from Georgia Tech. Today we're gonna demo run real-time object detection on a cluster of Raspberry Pis in a distributed fashion. So the highlight of our demo is we will do real-time object detection, and all the computations will run on Raspberry Pis. And our framework will partition and distribute the model onto multiple devices. And if you are interested, please come to our demo. Thank you.
Good evening. I'm Corey. I'm a software engineer at Databricks, and today I'll be demoing MLflow, an open source platform for the complete machine learning lifecycle. MLflow is built to address three main challenges in data science and model development. Those are experimentation, which is the observation that data scientists want to leverage a wide variety of machine learning tools and algorithms, and oftentimes machine learning platforms struggle to support the wide variety of tools that data scientists require. The second challenge is reproducibility. See, it's not enough for all of these tools to run properly on a single machine. They need to execute well and reproducibly across different environments. And the third is productionization. This is the challenge of taking a model through training and deploying it to satisfy a research or business use case. So in today's demo, we're going to take a look at each of MLflow's three components: tracking, projects, and models, which are all built to address each one of these challenges. And we'll see how MLflow can develop an image classification pipeline, ultimately integrating with a live web app. Thank you.
There we go. Hi, I'm Rob Earhart from Intel AI. At Intel, we really are interested in integrating with all the different frameworks. We are framework agnostic. We also want to integrate with a whole bunch of different types of hardware, including hardware that's not necessarily our own, right? So to do that, we've built a library, ngraph, that takes at its front end all these different frameworks, and then for its back end, it's got all these different hardware, kernel library type things. And alongside ngraph, we've also got PlatyML, my part, a tensor compiler. And if you were at the keynote, you know how cool tensor compilers are. And we'll be demoing this running some style transfers on a commodity MacBook Pro. Thanks.
That concludes the demo preview and the sessions for the day. Off to the demo sessions and poster now. Thank you.